Statistical methods date back at least to the 5th century BC. Statistics was originally called state arithmetic and has strong roots in real-world applications. For example, the Roman Empire reached its greatest expanse during the reign of Trajan, with a population of roughly 60 million people. In 117 AD, it stretched from Britain to Syria and from the north coast of Africa to the centre of Europe. That's an enormous number of people to collect, organise and interpret information about. Statistics has grown and developed since Roman times and has been influenced by the following areas. Biostatistics is a specialised field of statistics in general. There are two main branches of statistics. One is focused on describing and communicating information simply. The other on drawing conclusions from data and inferring them to different but often related situations. Information is collected by observing or measuring something. One observation is referred to as a datum, while a collection of observations or measurements are called data. Let's take a closer look at descriptive statistics. Both of these figures are examples of descriptive statistics. Each blue dot in figure 1 represents one of tens of thousands of confirmed cases of Lyme disease in 2011. Rather than examining CDC records for every county of every state in the US, these statistical maps summarise, organise and simplify the data into a form that's more easily communicated and understood. Think about the sheer volume of data summed up in these two figures. We can readily appreciate areas associated with high or low risk of contracting Lyme disease just by looking at them. Here are two further examples of descriptive statistics that summarise, organise and simplify tens of thousands of Lyme disease data. What information is being communicated here? Researchers usually study a sample, but they're really interested in answering a question about a specific group of individuals. In statistical terminology, the entire group that a researcher wishes to study is called a population. Populations can obviously vary in size, from extremely large to very small, depending on how the investigator defines the population. Populations don't even need to consist of people. It could be a population of rats, businesses, components manufactured in a factory, really anything an investigator wants to study. Populations are typically very large, and it's usually impossible for a researcher to examine every individual. It's also far too expensive and it would take too long. Instead, researchers select a smaller, more manageable group from the population and focus their studies on these individuals. This sample of people is intended to be representative of its population. Just as we saw with populations, samples can vary in size. There's likely to be hundreds or thousands of people in these samples. Or one study might examine a sample of only 18 people, let's say from New Haven. Samples should be representative and generalisable. Remember that the research started with a general question about the population. To answer the question, a researcher studies a representative sample and then generalises the results from the sample to the population. If we studied sample 1 here, could whatever we learned be applied to the larger population of New Haven? What if we use sample 2 instead? Or how about sample 3? Same question. If we studied this sample, could whatever we learned be applied back to New Haven? If we had to choose one of the three, sample 3 is the most representative in terms of sex and race. A characteristic that describes a population, usually a numerical value, is referred to as a parameter, while a characteristic that describes a sample is called a statistic. Here are some examples of both. Typically, Every population parameter has a corresponding sample statistic, and a substantial amount of biostats is concerned with the relationship between sample statistics and the corresponding population parameters. For the purposes of statistical notation, Greek letters such as mu or sigma are used to indicate parameters, while Roman letters, like the ones we use in the English alphabet, indicate statistics. Now let's take a closer look at inferential statistics. As I said earlier, inferential statistics consist of techniques that allow us to study samples and then make generalizations about the populations from which they were selected. Sticking with 1st century Romans, let's say we wanted to measure how long a typical Roman citizen lives. Rather than determining that for millions and millions of people, we could select and observe a smaller, more manageable sample of 60 individuals, then calculate their average life expectancy. The average of 25 years we calculated from the sample of 60 forms our estimate for the whole Roman population. We're inferring from our sample data that the life expectancy at birth of a Roman citizen is 25 years. However, if the actual life expectancy is 28 years, there would be a discrepancy of 3 years between the true population parameter and the sample statistic. We call this discrepancy sampling error. If we wanted a better, more accurate estimate, we could select a larger sample of 120 individuals and calculate their average life expectancy. This time around we get a discrepancy, or sampling error, of 1 year between the true population parameter and the sample statistic. We don't expect the statistics from a sample to be perfect. There always will be some margin of error when sample statistics are used to represent population parameters. So sampling error is normal and can be minimized by using sufficiently large and randomly selected samples. Researchers are typically interested in specific characteristics of the individuals in the population or sample, or they're interested in outside factors that may influence the individuals. Something that can change or have different values is called a variable. Constants are characteristics that are fixed for each individual and cannot change. There are a handful of different types of variables that we consider in research. Two necessary for good research are independent variables and dependent variables. The variable that is manipulated by the experimenter is called the independent variable. The dependent variable is the one that is observed to assess the effect of the independent variable. To help you identify which is which, here are some quick tips. The independent variable is the thing that is being controlled, or decided, or manipulated, or assigned by the researcher. The dependent variable is what's being measured. The manipulation of the independent variable usually comes before the measurement of the dependent variable, so looking at what comes before is another way to help you find which is which. Let's talk through an example. A researcher examines the effects of two variables in memory. One variable is beverage, let's say coffee or water, and the other variable is the aspects of a story to be remembered. Drinking the beverage comes before the study participants listen to the story and then try to recall its aspects. The researcher decides who gets a coffee and who gets water. So the beverage is the independent variable. That's the thing that the researcher is manipulating. It also comes first. The aspects of the story, that's the dependent variable. That's what's being measured to help us assess the effects of beverage on memory. Two other types of variables are between subjects and within subjects variables. Between subjects variables change from person to person to person. For example, I have B negative blood. My brother has B positive. I'm 6 years older than he is. So age and blood type differ between us. They're between subjects variables. Within subjects variables are characteristics of one person that change over time. For example, my heart rate is different when I'm sleeping than when I'm exercising, or the number of vaccinations I've had will change over the course of my life. So measuring a characteristic of an individual at different time points, that's a within subjects variable. The names for these variables are fairly descriptive. Some research studies are conducted simply to describe individual variables as they exist naturally. But most research is intended to examine the relationship between variables. 3 important types of study to help us do this are correlational studies, experimental studies, and quasi-experimental studies. In the correlational method, 2 different variables as they exist naturally are observed to determine whether there is a relationship between them. The results from a correlational study can demonstrate the existence of a relationship between 2 variables, but they do not provide an explanation for the relationship. For example, supervisors' sense of humour and people's job satisfaction. Is the funny boss the cause of the job satisfaction? Maybe, maybe not. There are many possible explanations for the relationship, and we don't know exactly what factor or factors are responsible here. Maybe it's the work environment. Maybe it's very relaxed and comfortable. That work environment is the cause of the sense of humour and the cause of the job satisfaction. How about the number of DVRs in a household and a student's SAT scores? Does owning more DVRs cause you to have a better score? Or is something else, a third factor, something related to the other 2, is that the cause? A family that's well balanced, functional, and that has a high socio-economic status is probably going to have more DVRs and provide more resources for the educational needs of their children than families who struggle financially or who are dysfunctional. Correlational studies can only tell us a relationship exists between 2 variables. They cannot in any way demonstrate cause and effect. To demonstrate a cause and effect relationship between 2 variables, researchers must use the experimental method. That's its goal. An experiment attempts to show that changing the value of one variable will cause changes to occur in the second variable. For example, is there a cause and effect relationship between administering the polio vaccine and the number of people in the population who have polio? In other words, does giving the vaccine cause a decrease in the incidence of polio? To accomplish the goal of demonstrating cause and effect, the researcher must use manipulation and control. The researcher has to manipulate the giving of the vaccine, giving it to some people and not to others, or increasing the number of people it's given to. They will then measure the number of polio cases in the population or sample. The researcher must also exercise control over the research situation to ensure that other unrelated variables do not influence the relationship being examined. We call these confounding variables. Confounding variables are the enemy of good research. In this case, age and nutritional status of participants in the experiment may be confounding variables. Very young and very old people are more susceptible to disease. Likewise, people who are underfed or malnourished. An observed difference in polio incidence may be due to variation in these characteristics rather than the vaccinations. Whenever a research study allows more than one explanation for the results, the study is said to be confounded because it's impossible to reach an unambiguous conclusion. In informal conversation, there's a tendency for people to use the term experiment to refer to any kind of research study. You should realise, however, that the term only applies to studies that satisfy the specific requirements outlined earlier. As a result, there are a number of other research designs that are not true experiments but still examine the relationship between variables. One of these is the quasi-experimental method. This is a non-experimental study because it lacks the rigorous control needed. This type of study compares pre-existing groups, so the researcher cannot control the assignment of participants to the groups or ensure equivalent groups. If you're studying the relationship between sex and seasonal affective disorder, You can't randomly assign half of your participants to be male and half to be female. You could separate them into male and female groups based on their pre-existing sex, but you cannot manipulate that between subjects variable. In other words, the researcher cannot manipulate their genetic sex and then measure how well they do in terms of depression during the winter months. In the second example, it would be unethical to manipulate and assign people to two different groups that receive their medication via the old or via the new system, and then step back to observe the number of medication-related adverse events that result. Ethics restrict our level of control here, and mean that this study is also considered non-experimental. Let's go through some examples to practice identifying the type of study involved. Example 1. An occupational therapist is interested in the relationship between dog owners and number of household falls among older people. A total of 530 subjects with an average age of 77 years are recruited primarily before discharge from selected hospital wards. The OT records those who have pet dogs and observes the number of falls, ascertained over a 12-month follow-up period using a monthly falls calendar. What kind of study is this? The things to consider are the number of variables measured or manipulated and the degree of control. This chart can help you. In example 1, the OT is recording, or in other words measuring, two variables: those subjects who have dogs and the number of household falls. There is no manipulation or control. The OT is not giving dogs to some people and taking them away from others. This is a correlational study. Example 2. A researcher is testing the effect of alcohol on memory performance. He gives one group of subjects a bottle of vodka, and another a non-alcoholic substance that tastes like vodka. Each group then learns a list of words and attempts to recall them. The number of words correctly recalled for each group is recorded. What kind of study is this? The researcher manipulates one variable, the beverage. One group of people are assigned vodka to drink, and the other group are assigned a non-alcoholic fake vodka. Then after this manipulation, the researcher measures one variable, the number of words recalled from a list. This is an experimental study. Example 3. A social psychologist is interested in sex differences in math performance. She randomly selects men and women from New Haven and has them solve a series of equations. The number of equations correctly solved for each participant is recorded. What kind of study is this? The psychologist is measuring one variable, the number of equations solved correctly. She can't manipulate the pre-existing sex of the subjects. This is a quasi-experimental study. Example 4. A clinical psychologist is interested in the effectiveness of a new antidepressant drug. He collects scaled depression scores from a group of individuals diagnosed with depression at time 1. All individuals then take the drug and are measured again a month later at time 2. What kind of study is this? The psychologist manipulates one variable, the antidepressant drug. It's being controlled and assigned, in this case to all the participants. One variable is being measured, the depression scores. This one variable is being measured twice, before they take the drug and then 1 month later. This is an experimental study. It's important to know the types of variables you're dealing with in order to choose the correct statistical techniques to analyze your data. The variables researchers measure can also be characterized by the types of values that can be assigned to them. Researchers use both discrete and continuous numerical observations to quantify variables. Discrete observations can only take on whole numbers, not values in between, so no values with fractions or decimals. For example, in terms of British politics, you can be a member of the Liberal Democrats, or the Scottish National Party, or the Conservative Party, but you can't be 3/15 of one and 12/15 of another. Similarly, individuals have whole numbers of vaccinations, not 3.43 vaccinations of tetanus and 0.74 vaccinations of hepatitis B. On the other hand, continuous variables can take on a full range of values. Numbers out to several decimal places are fine. In other words, an infinite number of potential values exists. For example, one person might complete a task in 12.839 seconds. Someone else might complete it in 14.870 seconds. The possible values are continuous, limited only by the number of decimal places we choose to use. Let's take a closer look at continuous and discrete variables. It's rare for continuous variables to be identical for two different individuals. Each measurement category is really an interval defined by boundaries. If we measure blood pressure to 4 decimal places, we'll observe that every person is different from the next. Those values to 4 decimal places fall on a continuous line that can be divided into specific categories defined by boundaries. 118, 119, 120, 121, and so on. Let's look at this concept in another way, in terms of physical location in Connecticut. We can be present in many different physical locations in Connecticut, and yet still be authentically in Connecticut. Physical location within Connecticut is a continuous variable. One person can be in North Haven, one in Mystic, another in Danbury, yet all three are genuinely within Connecticut. Connecticut is adjacent to Massachusetts. They share a border. Both states are actually intervals within New England that are defined by boundaries. Although physical location is continuous, the category location we call Connecticut is a fixed interval defined by the New York, Massachusetts, and Rhode Island borders. Or another way of explaining this, the I-95 can be thought of as a continuous highway running between Florida and Maine. Physical location on I-95 is also a continuous variable. And state borders divide the I-95 into discrete sections. When driving from North Haven to New York City, you cross the Connecticut-New York border going over the Byram River. The arterial pressure category of 120 milligrams of mercury is an interval that is defined by two borders, or two real limits, a lower limit of 119.5 and an upper limit of 120.5. 119.7, 120.2, and 119.5 all fall within the real limits of 120 milligrams of mercury, but 119.4 or 120.7 don't. Data collection requires that we make measurements. Measurement involves assigning individuals or events to categories. The categories can simply be names, such as male, female, or employed, unemployed, or they can be numerical values, such as 68 inches or 175 pounds. The complete set of categories makes up a scale of measurement, and the relationships between the categories determine different types of scales. The distinctions among the scales are important because they identify the limitations of certain types of measurements, and because certain statistical procedures are appropriate for data collected in some scales, but not on others. The word nominal means having to do with names. Measurement on a nominal scale involves classifying individuals into categories that have different names but are not related to each other in any systematic way. For example, cell phone or social security numbers. They don't represent quantities of anything. They're just numerical names. Other examples of nominal variables include nationality or eye colour. The measurements from a nominal scale allow us to determine whether two individuals are different, but they do not identify either the direction or the size of the differences. Rooms or offices in a building may be identified by numbers. Room 109 is just a name and doesn't reflect quantitative information. Room 109 is not necessarily bigger than room 100. is certainly not 9 points bigger. Averaging nominal data is either impossible or meaningless. Adding up the shirt numbers of the 5 hockey players currently on the ice and calculating their average, it doesn't represent anything meaningful. Similarly, you can't calculate an average by adding apple plus peach plus orange plus lemon plus peach plus apple and then dividing by 7. The categories that make up an ordinal scale not only have different names, but also are organised in a fixed order corresponding to differences of magnitude. Often an ordinal scale consists of a series of ranks, first, second, third, and so on, like the order of finish in a race. Sometimes the categories are identified by verbal labels, like small, medium, or large. The fact that the categories form an ordered sequence means there's a directional relationship between categories. With measurements from an ordinal scale, you can determine whether two individuals are different, and you can determine the direction of difference. So for example, person A is taller than person B. However, ordinal measurements do not allow you to determine the magnitude of difference between the two individuals. So you can't tell by how much taller is person A than person B. An interval scale consists of ordered categories that are all intervals of exactly the same size. Equal differences between numbers on the scale reflect equal differences in magnitude. However, the 0 point on an interval scale is arbitrary and does not indicate a zero amount of the variable being measured. For example, you know that a measurement of 80 degrees Fahrenheit is higher than 60 degrees Fahrenheit, and you know it's exactly 20 degrees higher. But a temperature of 0 degrees Fahrenheit does not mean that there's no temperature, and it does not prohibit the temperature from going even lower. The value 0 is assigned to a particular location on the scale simply as a matter of convenience or reference. Because of this, the ratio between 2 points on an interval scale are meaningless. A ratio scale is an interval scale with the additional feature of an absolute 0 point. With a ratio scale, ratios of numbers do reflect ratios of magnitude. A ratio scale is anchored by a 0 point that is not arbitrary, but rather is a meaningful value representing none, or a complete absence of the variable being measured. For example, an individual who required 10 seconds to solve a problem, so 10 more than 0, has taken twice as much time as an individual who finished in only 5 seconds, or 5 more than 0. With a ratio scale, we can measure the direction and size of the differences between two measurements, and we can describe the difference in terms of a ratio. For biostatistics, scales of measurement are important because they influence the kind of statistics that can and cannot be used. Let's go through some examples and practice identifying scales of measurement. What scale of measurement is used here? Nominal, ordinal, interval, or ratio? And are the variables discrete or continuous? Marital status is a nominal category, and it's discrete. The sizes of McDonald's drinks and fries are ordinal and discrete. Weight is ratio and continuous. The number of dreams recalled is ratio and discrete. Golf scores are interval and discrete. The time it takes for a light bulb to burn out is ratio and continuous. The measurements obtained in research studies provide the data for statistical analysis. Most statistical analyses use the same mathematical notation and basic arithmetic you learned in school. That said, there is some additional notation that's used for statistical calculations. It's useful to specify how many scores are in a data set. We use the uppercase letter N to represent the number of scores in a population, and a lowercase n to represent the number of scores in a sample. Let's say the data in Table 2.1 are from a student clinic run by nursing and medical students. One of the licensed physicians who supervises the clinic would like to know how many non-diabetic, pre-diabetic and diabetic patients were screened during the past week. The next step would be for you to organise the scores into some comprehensible form so that any patterns in the data could be easily seen and communicated to the attending physician. This is the job of descriptive statistics, to simplify the organisation and presentation of data. One of the most common procedures for organising a set of data is to place the scores in a frequency distribution. Table 2.2 is a frequency distribution representing only part of the data in Table 2.1. A frequency distribution takes a disorganised set of scores and places them in order from highest to lowest, grouping together all the individuals who have the same score. A frequency distribution allows the researcher to see at a glance the entire set of scores. It shows whether the scores are generally high or low, whether they're concentrated in one area or spread out across the entire scale, and generally provides an organised picture of the data. The purpose for constructing a table is to obtain a relatively simple, organised picture of the data. This can be accomplished by grouping the scores into intervals, and then listing the intervals in the table instead of each individual score. The result is called a group frequency distribution table, and the groups are called class intervals. Table 2.3 has a class interval size of 20. Table 2.3 is much simpler, better organised and more easily understood than Table 2.2, and it's much better than Table 2.1. You've probably come across group frequency distributions already, perhaps without even realising it. When researchers summarise larger data sets with thousands or millions of numbers, they often distribute the relative frequency of scores rather than counts. A relative frequency describes the proportion of the data in each interval. It's often easier to list the relative frequency of scores because a list with very large counts in each interval can be more confusing to read. Table 2.4 summarises the entire set of data originally shown in Table 2.1. When researchers want to describe frequencies above or below a certain value, they often report a cumulative frequency distribution. A cumulative frequency distributes the sum of frequencies across a series of class intervals. We can sum the frequencies beginning with the bottom and adding up the table. Here we can see how to calculate the cumulative frequency. In Table 2.5, look at the column in the middle representing relative frequency. We begin with the frequency in the bottom interval, 44%. 44% plus 32% gives us a cumulative frequency of 76%. In order to get the next cumulative frequency, we add 44% plus 32% plus 16% to give us a cumulative frequency of 92. We keep doing this, adding up the table. 44 plus 32 plus 16 plus 0.5 gives us a cumulative frequency of 92.5. 44 plus 32 plus 16 plus 0.5 plus 0.5 gives us a cumulative frequency of 93. This is repeated until all the frequencies are summed. This type of summary is useful if we want to discuss data in terms of less than, or at or below a certain value, or at most. For example, people with normal blood sugar levels are those who report a fasting blood glucose less than 100 mg per deciliter. Table 2.6 shows frequency, relative and cumulative distribution tables in a more quick glance, summarised form. The patterns present in the Table 2.1 student clinic data are more readily comprehended and communicated to the supervising physician or nurse when they're organised using descriptive statistics into the form of Table 2.6. Even more than tables, graphs help us see our data at a glance. The most common methods for graphing data are the polygon, histogram, bar graph and pie chart. However, the type of graph that is appropriate to display a distribution depends on the scale of measurement used. Group data, which measure continuous variables on an interval or ratio scale, can be summarized graphically using the frequency polygon. This is a dot and line graph, where the dot is the midpoint of each interval and the line connects each dot. A dot and line graph can also be used to summarize cumulative percents. This type of graph, called a cumulative frequency polygon, is used for continuous data. Another graph that can be used to summarize group data that is continuous and measured on an interval or ratio scale is the histogram. Histograms distribute the intervals along the horizontal or x-axis and list the frequency of scores in each interval on the vertical or y-axis. A histogram and a frequency polygon are equally effective at summarizing their particular types of data. The choice between which of the two to use comes down to personal preference. Bar graphs are much like histograms, except that the rectangular bars are separated from one another, while those in histograms touch. The separation between bars reflects the separation or break between the whole numbers or categories being summarized. For this reason, bar graphs are appropriate for distributions of discrete interval or ratio data, as well as data measured on a nominal or ordinal scale. The pie chart is another graphical summary used almost exclusively for discrete or nominal and ordinal data. To construct a pie chart, we typically distribute data as relative percents. Converting a distribution to a pie chart is simply a matter of finding the correct angles for each slice of pie. Rather than drawing a complete frequency distribution graph, researchers often simply describe its characteristics. There are three characteristics that completely describe any distribution: shape, central tendency, and variability. Think of it another way. When you're calling a pizza place, there's really only three things that you need to describe to the person on the other end of the phone: the size of the pizza, the type of crust or base, and the toppings. In this module, we'll provide you with the language that describes data in terms of shape. The shape of a distribution provides distinctive information. Let's take a sample of 10 individuals, have them take an IQ test, then graph the data with a histogram. Look at the overall shape. Most scores are close to 100, with a few people scoring below or above this. Let's increase the sample size to 20 individuals. Look at the overall shape in this histogram. Again, the highest frequency value is close to 100, with fewer people above or below. Let's increase the sample size to 60. Again, it's big in the middle, with fewer scores at either side. As the sample size increases, here we have n of 100, the more triangular or pyramid shaped the frequency distribution becomes. Here's n of 1000, and here's an n of 10,000. Increasing the sample size until it gets closer and closer to something like a large population, the more the distribution exhibits this shape. If we could give a population of infinite size an IQ test and graph the data, it would look like this. This is called a normal distribution. It's also sometimes called a Gaussian or bell-shaped distribution. Statisticians use the word normal to describe this particular shape of distribution. It's symmetrical, with the greatest frequency in the middle and relatively smaller frequencies as you move towards either extreme. The normal distribution occurs in most but not all research situations. Reality is not always normally distributed, which means that the distributions describing those particular observations are not shaped normally. So we need a new term to help us describe such distributions: skew. In a symmetrical distribution, it's possible to draw a vertical line through the middle so that half of all scores fall above the line and half fall below. Unlike the normal distribution, which is symmetrical, skewed data have an ever-thinning tail in one direction or the other. So a skewed distribution is a distribution in which one of the tails is pulled away from the center. When a distribution is positively skewed, the tail extends to the right in a positive direction. In other words, away from the 0 point where the x and y axes usually meet. Negatively skewed data have a distribution with a tail that extends to the left, in a negative direction. The way to remember the difference is to pay attention to the tail. If it's extending towards zero, and therefore the negative side of the x-axis, the distribution has a negative skew. If the tail is extending away from zero, and therefore towards the positive side of the x-axis, the skew is positive. In a similar way to the concept of skewedness, kurtosis is a descriptor of the shape of a distribution. Kurtosis measures and describes the peakness of a frequency distribution. A mesokurtic distribution is the same as the normal distribution. Leptokurtic distributions have more kurtosis, more peakness. They're thinner and more pointy. Platykurtic distributions have less kurtosis, or less peakness. They're broader and flatter. Although the primary purpose of a frequency distribution is to provide a description of an entire set of scores, it can also be used to describe the position of an individual within the set. By themselves, raw scores don't provide much information about their position in the overall data distribution. Because of this, they're usually transformed into a more meaningful form. One transformation that we will consider changes raw scores into percentiles. If you're told that your score in an exam is 43, you can't tell how well you did compared to your classmates. To evaluate your score like this, you need more information, such as the average score in the test, or the number of people who had scores above and below you. With this additional information, you would be able to determine your relative position in the class. The rank or percentile rank of a particular score is defined as the percentage of individuals in the distribution with scores at or below that particular value. When a score is identified by its percentile rank, the score is called a percentile. Notice that percentile rank refers to a percentage, and that percentile refers to a score. That sounds kind of confusing, right? Let me try and clarify. Percent rank and percentile are like two sides of the same coin. They're two descriptions of the same thing, which is the exact position of an individual score within the distribution. For example, I ran in the very first Geist half marathon near Fishers, Indiana. My friend Jane actually won the women's competition with a time of 1 hour and 23 minutes. That's me in the middle, runner 1186. This is Jane, giving the ice cream cone big licks. Over 4,000 people registered, but only 2,766 finished. It was easy for Jane to know her position in the overall race. She won. But what about me? I came in at 1 hour and 48 minutes, 823rd. My time of 1 hour and 48 minutes and my rank of 823 are linked together. They describe my position in the overall race. Like I said before, they're like two sides of the same coin. Compared to all 2,766 runners, the moment that I cross the finish line, that specific moment, can be described by my time and my rank. 823rd isn't easy for most people to get their heads around. It's better to convert that into a percentage. Let's say I was in the 80th percentile. 80% of the runners had a score of 1 hour and 48 minutes or slower. 1 hour and 48 minutes is my position as a score, while 80% is my position as a percentage. The cumulative frequency polygon and cumulative frequency distribution both illustrate the concept of percent rank, which states the percentage of scores that fall below any particular value. Percent ranks provide a way of giving information about one individual score in relation to all the others in a distribution. For example, say a person from the student run clinic with a fasting blood glucose level of 210 mg per deciliter lies at the 95th percentile. Roughly 5% of the scores in the sample are higher than this. Percentile ranks are one member of a family of values called quantiles, which divide distributions into an equal number of parts. Percentiles, or sometimes just called centiles, they divide into 100 equal parts. Quartiles divide into 4 equal parts. Quintiles divide into 5, and deciles divide into 10. Transforming a baby's height, weight, and head circumference information into percentiles allows paediatricians and paediatric nurses to monitor the health of infants. These percentile descriptive statistics enable nursing staff and physicians to compare a child with its past percentile measurements, as well as the overall infant population. In statistics, the concept of an average or representative score is called central tendency. By way of introduction to this, let's say I come home every day to a backyard covered in holes. I have 2 dogs, a beagle and a German shepherd. Which one is the hole digger? A friend contends that the sneaky beagle is responsible, but my neighbour swears it's a characteristic of German shepherds. To settle the debate, I decide to do a research study using the experimental method. I buy 10 new German shepherds, 10 new beagles, and 20 new backyards. I randomly assign the dogs to the yards, go to work, and count the holes when I return. Figure 3.1 is a histogram of the data. Notice that there's a difference between the 2 breeds. The beagles seem to dig more holes than the German shepherds. But this conclusion is based on a general impression or a subjective interpretation of the figure. In fact, this conclusion is not always true. There's an overlap between the 2 groups. Some of the shepherds actually dig more holes than some of the beagles. What we need is a method to summarise each group as a whole, so that we can objectively describe how much difference exists between the 2 groups. A measure of central tendency will identify the average or typical number of holes dug to serve as a representative value for each dog breed. Then we can use the 2 averages to describe the 2 groups and to measure the difference between them. Central tendency is the second of the 3 characteristics used to completely describe any distribution. Central tendency refers to the descriptive statistic that best describes the centre of a dataset, the particular value that all the other data seem to be gathering around. In everyday language, the goal of central tendency is to identify the average or typical individual. This average value can then be used to provide a simple description of an entire population or sample. Because central tendency characterises what is typical for a large population, it makes large amounts of data more digestible. The expression number crunching illustrates this aspect of data description. In other words, we take a distribution consisting of many scores and crunch them down to a single value that describes them all. Unfortunately, there's no single standard procedure for determining central tendency. The problem is that no single measure will always produce a central representative value in every situation. The 3 distributions on the right should help demonstrate this. The first distribution is symmetrical, with the scores forming a distinct pile centred around x equals 5. For this type of distribution, it's easy to identify the centre, and most people would agree that the value x equals 5 is an appropriate measure of central tendency. In the second distribution, however, problems begin to appear. Now the scores form a negatively skewed distribution, piling up at the high end of the scale around x equals 8, but tapering off to the left all the way down to x equals 1. Where is the centre in this case? Some people might select x equals 8 as the centre, because more individuals had this score than any other single value. However, x equals 8 is clearly not in the middle of the distribution. In fact, the majority of the scores, 10 out of 16, have values less than 8, so it seems reasonable that the centre should be defined by a value that is less than 8. Now consider the third distribution. Again, the distribution is symmetrical, but now there are two distinct piles of scores. Because the distribution is symmetrical with x equals 5 as the midpoint, you may choose x equals 5 as the centre. However, none of the scores are located at x equals 5, or even close, so this value is not particularly good as a representative score. On the other hand, because there are two separate piles of scores with one group centred at x equals 2 and the other centred at x equals 8, it's tempting to say that the distribution has two centres. But how can one distribution have two centres? To deal with these problems, statisticians have developed three different methods for measuring central tendency: the mean, the median, and the mode. The most commonly reported measure of central tendency is the mean, which is the arithmetic average of a group of scores. The mean is calculated by summing all the scores in a data set and then dividing this sum by the total number of scores. The mean for a population is symbolized by the Greek letter mu, and the mean for a sample by x bar. The summation sign sigma indicates that we're summing a list of scores. These symbols are part of the language of statistics and help us to communicate with other statisticians. You're likely to have calculated means many times in your life. Nonetheless, here are a couple of quick examples of calculating the arithmetic mean. In the first example, 7 houses were sold last week in Hamden, Connecticut. Here are the selling prices. Adding these 7 prices together and dividing by 7 gives us the mean selling price of $264,914.29. In example 2, a student got the following scores in his 5 statistics exams. Adding those 5 exam scores together and dividing by 5 gives us the mean exam score of 82.2. Often it's necessary to combine two sets of scores and then find the overall mean for the combined group. In example 3, a biologist measures the length of lobsters caught off the coast of Maine. On day 1, the average score is 15 inches for 12 animals. On day 2, the average score is 18 for 8 animals. What's the overall mean? This overall mean is not halfway between the two original sample means. Because the samples are not the same size, one makes a larger contribution to the total group and therefore carries more weight in determining the overall mean. For this reason, the overall mean is called the weighted mean. To calculate the weighted mean, we need two values: the combined sum of scores, so sigma x1 plus sigma x2, and secondly, the total number of scores in the combined group, so n1 plus n2. On day 1, the biologist caught 12 lobsters with an average length of 15 inches, so sigma x1 equals 180. On day 2, they caught 8 lobsters with an average length of 18 inches, so sigma x2 is 144. The weighted mean is 180 plus 144 divided by 12 plus 8, which is 16.2 inches. It's possible to calculate a weighted mean for more than two groups. In example 4, emergency room wait time is a 4-hour rolling average that represents the time it takes to see a qualified medical professional. You can Google emergency room wait time and see different values for different hospitals. What was the overall mean waiting time for this 24-hour day? 24 hours divides into 6 periods of 4 hours each. Here are the data listed for those 6 periods. We first want to calculate the combined sum of scores, so need to figure out sigma x1 through sigma x6. We also need to calculate the total number of patients, so adding together n1 through n6. The weighted mean is the combined sum divided by the combined n, which equals 36.8 minutes. The mean has many characteristics that result from the fact that every score in the distribution contributes to the value of the mean. Changing the value of any score will always change the mean. Changing this 2 to a 12 alters the mean to a 6. Adding or removing a score will usually but not always change the mean. The exception to this is when the score added or removed is equal to the mean. So removing this 2 alters the mean to 4.5. Adding or subtracting a constant value to or from each score will add or subtract the same constant from the mean. So adding 2 to each of these scores is the same as adding 2 to the mean. Multiplying or dividing each of the scores will produce a mean that is multiplied or divided by the same factor. So multiplying each score by 2 is the same as multiplying the mean by 2. The second most common measure of central tendency is the median. The median is the middle score when all the scores in a sample are arranged in ascending order from lowest to highest. We can think of the median as the 50th percentile. To find the median, put the scores in ascending order from lowest to highest and find the middle value. If the n number is odd, the median is the middle score. If the n number is even, the median is the mean of the middle 2 scores. If we were to identify the median for this previous example, it would be $100,900. It's the middle of the 7 prices when they're arranged from lowest to highest. The mode is perhaps the easiest of the 3 measures of central tendency to calculate. The mode is the most common score of all the scores in a sample. It's easy to spot on a frequency distribution table, histogram, or frequency polygon. In these examples, 6 is the most frequent score and therefore the value of the mode. Next, for these nominal measurements, male is most common and therefore the mode. And lastly, the mode for the pain scores is 2. Some data sets have more than one specific mode, where 2 or more different scores are the most common. When a distribution of scores has one mode, we refer to it as unimodal. When a distribution has 2 modes, we call it bimodal. When a distribution has more than 2 modes, we call it multimodal. A bimodal distribution is often an indication that 2 separate and distinct groups of individuals exist within the same population or sample. For example, if you measured shoe size for each person in a set of 100 college students, the resulting distribution would probably have 2 modes, one corresponding primarily to the males in the group, and one corresponding primarily to the females. Technically, the mode is the score with the absolute highest frequency. However, the term mode is often used more casually to refer to scores with relatively high frequencies. That is, scores that correspond to peaks in a distribution, even though the peaks are not the absolute highest points. When 2 modes have unequal frequencies, researchers occasionally differentiate the 2 values by calling the taller peak the major mode and the shorter one the minor mode. We have identified 3 different measures of central tendency, and often a researcher calculates all 3 for a single set of data. Because the mean, the median, and the mode are all trying to measure the same thing, central tendency, it's reasonable to expect that these 3 values should be related. In fact, there are some consistent and predictable relationships among the 3 measures of central tendency. Specifically, there are situations in which all 3 measures will have exactly the same value. On the other hand, there are situations in which the 3 measures are guaranteed to be different. In part, the relationships among the mean, median, and mode are determined by the shape of the distribution. We'll consider 2 general types of distribution. For a perfectly symmetrical distribution with one mode, all 3 measures of central tendency, the mean, the median, and the mode have the same value. A bimodal distribution that is symmetrical will have a mean and median together in the centre, with modes on each side. A rectangular distribution has no mode, because all the scores occur with the same frequency. Distributions are not always symmetrical. Quite often they're lopsided or skewed. In positively skewed distributions, the order of the 3 measures of central tendency from smallest to largest is the mode, then the median, then the mean. Negatively skewed distributions are lopsided in the opposite direction. Therefore, The measures are also ordered in the opposite direction. Changes in kurtosis have no effect on measures of central tendency. How do you decide which measure of central tendency to use? The mean is used in the majority of cases. The mean is often the most appropriate measure because it takes into account all scores in the data set. But the mean cannot be used for nominal scales of measurement. The median serves as a better alternative to the mean when a distribution has a small number of extreme scores, or contains undetermined values, or is open-ended. For example, according to the 2011 census, Bridgeport, Connecticut has a mean income of $40,947 and a population of roughly 145,638 people. What would happen to the mean if Bill Gates decided to relocate to Bridgeport? Bill Gates has an annual income of $3,710,000,000. Adding Bill Gates to Bridgeport's population would produce a new mean income of $66,417. This mean is no longer a representative measure. It's more than the majority of Bridgeport residents earn, and far less than Bill Gates. The second situation where the median is better than the mean is when a distribution contains undetermined values, in other words, scores for which there is no value on the scale. In example 1, sports scores, like in car racing or track or field, that have a category of did not finish. Or in the second example, a participant in a clinical drug trial who withdrew because of unpleasant side effects and did not finish the course of treatment under evaluation. It's important that we don't just delete this person's data. If a sample is to be representative of its population, this person is indicative of other people who are unlikely to tolerate the drug's side effects. This is very valuable information, but not something that can be communicated by the mean. It's also better to use the median when a distribution is open-ended. In other words, when there is no upper or lower limit for one of the intervals or categories. And lastly, it's better to use the mode in the other two measures of central tendency when the scale of measurement is nominal. Only the mode can be used here. We cannot use the mean or the median. And secondly, if the most typical case is to be identified, the mean and median often produce fractional values. To review, the mean is the arithmetic average. It's the sum of scores divided by the number of scores. It's most frequently used because it uses all scores in the set. The median is the middle score when scores are in order from lowest to highest. It corresponds to the 50th percentile and is appropriate for skewed or open-ended distributions and distributions with undetermined scores. And the mode is the most frequently occurring score and is appropriate for nominal data. Although the measures of central tendency from Module 3 were handy ways to summarise the data from our hole digging experiment, these measures don't tell the whole story. Looking at this histogram again, we can see that the typical beagle digs an average of roughly 8 holes, and the typical German Shepherd digs an average of roughly 3 holes. Yet some of the dogs depict atypical behaviour for their breed. In other words, not every dog is average. This is true for humans too. While many people perform near average, others do things that are far above or below average. Put simply, people are different. To study how different or similar people are from one another, or scores are from one another, we need a statistical method to measure and objectively describe the differences that exist within a set of scores. In statistics, this measure is called variability. Variability, along with shape and central tendency, allows us to describe the distribution. It tells us whether the scores are clustered close together or are spread out over a large distance. Variability also measures how well an individual score or group of scores represents the entire distribution. This aspect of variability is very important for inferential statistics, where relatively small samples are used to answer questions about populations. In this way, variability provides information about how much sampling error to expect. In simple terms, if the scores in a distribution are all the same, then there is no variability. If there are small differences between scores, then the variability is small. And if there are large differences between scores, then the variability is large. In this module, we consider three different measures of variability: the range, the interquartile range, and the standard deviation. Of these three, the standard deviation is by far the most important. The range is the easiest measure of variability to calculate. The range is the distance between the largest and smallest scores in a distribution. In determining this distance, you should also take into account the real limits of the maximum and minimum values. So the range is calculated as the difference between the upper real limit for x max and the lower real limit for x min. A less complicated way to do this calculation is to subtract your lowest score from your highest score, then add 1. Let's look at some examples. Consider the following scores: 13, 15, 12, 17, 14, and 16. The highest and the lowest values are 17 and 12. The upper real limit of 17 is 17.5, while the lower real limit of 12 is 11.5, and the difference between the two is 6. An easier way to do it is to subtract 12 from 17 and add 1, which also gives us 6. In example 2, consider these scores: 36, 42, 14, 68, 92, 12, 33, 43, 46, and 78. Here the highest and lowest scores are 92 and 12. 92 minus 12 plus 1 equals a range of 81. That's exactly the same as taking the upper real limit of 92, which is 92.5, subtracting off the lower real limit of 12, 11.5, which gives us a range of 81. Some researchers don't bother considering the real limits when calculating the range, and they're just wrong. We recommend that you do, because the range is typically used with interval or ratio scale measurements of a continuous variable, and the concept of real limits is necessary to divide continuous variables into quantifiable intervals. In example 3, let's take the first 17 scores from the fasting blood glucose example in Module 2. Fasting blood glucose is a continuous variable on a ratio scale. The highest and the lowest values here are 124 and 72. So the range is 124 minus 72 plus 1, which equals 53. The range is perhaps the most obvious way of describing how spread out the scores are. The problem with using the range as a measure of variability is that it's completely determined by just the two extreme values and ignores the other scores in the distribution. Thus, a distribution with one unusually large or small score will have a large range, even if the other scores are actually clustered close together. To illustrate this, imagine we chose a sample of n equals 73 people from the population of New Haven and drew a frequency distribution of their height measurements. The range here is calculated as 76 minus 60 plus 1. So the height distribution of the sample is spread out over 17 inches. If we added an unusually short person to this sample, the range would now be calculated as 76 minus 5 plus 1, so the height distribution of the sample is now spread out over 72 inches, even though 73 of our scores are closely clustered together near the mean and only one is extremely far away. Because the range does not consider all the scores in the distribution, it often does not give an accurate description of the variability for the entire distribution. For this reason, the range is considered to be a crude and unreliable measure of variability. One way to avoid the excessive influence of one or two extreme scores is to measure variability with the interquartile range. The interquartile range ignores extreme scores. Instead, it measures the range covered by the middle 50% of the distribution. We can divide a distribution into 4 equal parts using quartiles. Q1 is the quartile that represents the bottom 25% of the distribution. Q2 represents the bottom 50% of the distribution and is equivalent to the median, whereas Q3 indicates the boundary that separates the top 25% of the distribution from the rest. After the quartiles have been determined, the interquartile range is defined as the distance between the first quartile and the third quartile. Let's go through a couple of examples of how to calculate interquartile range from start to finish. It's slightly different depending on whether you have an odd or even number of scores. Example 1. So again, let's take the first 17 scores from the fasting blood glucose example in Module 2. The first step is to place these scores in order, from lowest to highest. What we want to do next is calculate Q2, which is the same as finding the median of these scores. So in this case, Q2 equals 96. It's the middle value. In order to identify Q1, we focus on these scores that begin with the first score and include Q2. Ignore the others for now. In order to determine Q1, we're going to find the median or the middle value of this subset. There's an even number of scores in the subset, so Q1 is the mean of the middle two. So 80 plus 82 divided by 2 equals 81. Next, to identify Q3, we focus on these scores that begin with Q2 and finish with the last score. Q3 is the median of this subset. Again, there are an even number of scores, so Q3 is the mean of the middle two. So 105 plus 111 divided by 2 equals 108. So our quartile values are 81 for Q1, 96 for Q2, and 108 for Q3. The interquartile range equals Q3 minus Q1, so 108 minus 81 equals 27. If you're calculating the interquartile range for an even number of scores, the procedure is almost, but not quite identical. Example 2. Let's take the next 16 scores from the fasting blood glucose example in Module 2. Again, the first step is to place these scores in order, from lowest to highest. We then want to determine Q2, which is the median of these scores. For an even number of scores, that means taking the mean of the middle two values. So 84 plus 85 divided by 2 equals 84.5. This time, in order to identify Q1, we focus on a subset of scores that begin with the first score and includes both of the two middle scores that were used to calculate Q2. Q1 is the median, or the middle value of this subset, so 76. Next, to identify Q3, we focus on these scores that begin with the two middle values that were used to calculate Q2 and finish with the last score. Q3 is the median of this subset, so 93. The interquartile range is then Q3 minus Q1, which is 93 minus 76, which equals 17. Because the interquartile range is derived from the middle 50% of a distribution, it is less likely to be influenced by extreme scores, and therefore gives a better and more stable measure of variability than the range. However, the interquartile range only considers the middle 50% of the scores, and completely disregards the other 50%. Therefore, it does not give a complete picture of the variability for the entire set of scores. Like the range, the interquartile range is considered to be a crude measure of variability. The standard deviation is the most commonly used and the most important measure of variability. Let's consider archery as a way to understand the concept of standard deviation. What would you expect a really good archer's target to look like after shooting 5 arrows at it? With a good archer's results, the arrows are clustered closely together and they're near the bullseye, while for a bad archer, the arrows are all over the place and they're far from the bullseye. Imagine the archer's target is a normal distribution. The bullseye represents the mean of a distribution of scores, while the arrows are the individual scores that make up the distribution. We can measure variability by how near to the bullseye each arrow is, or in other words, how near each individual score is to the mean. If the arrows, or scores, are clustered together near the mean, the variability is low. If the arrows or scores are far away from the mean, the variability is high. It would be better if we had a method to summarise the variability as a whole, so that we can objectively describe how much difference exists between the two archers. If we calculate the average distance of the arrows from the bullseye, we will have a simple single value that describes the variability within the distribution. Standard deviation is the average distance of the scores from the mean. It lets us describe the variation in a whole set of data with a single number. Going back to our dog's example, we wanted a method to objectively measure by how much the dogs had deviated from the typical hole digging behaviour of their breed. In other words, how much had they moved away from the mean? The standard deviation is the most important and commonly used measure of variability. Standard deviation uses the mean as a reference point and measures variability by considering the distance between each score and the mean. It determines whether the scores are generally near or far from the mean. In other words, are the scores clustered together or scattered? In simple terms, the standard deviation approximates the average distance from the mean. The characteristics of the standard deviation can be summed up by these 4 points. The standard deviation measures the typical or standard distance from the mean. The standard deviation allows us to visualize the distribution. The smaller the standard deviation, the more accurately a sample will represent its population. And in terms of transformation of scale, adding a constant means that the standard deviation does not change. When scores are multiplied by a constant, then the standard deviation is also multiplied by that constant. Although the concept of standard deviation is fairly straightforward, the actual equations appear complex. The vast majority of researchers will use statistical software like SPSS to calculate measures of variability, including the standard deviation. That said, we still think it's valuable to talk you through how the calculations are done by hand. Let's begin with the logic that leads to the equations for standard deviation. The first step is to calculate deviation scores for each value in your dataset. In other words, to determine by how much each score has deviated from the mean. The deviation score equals x minus mu. For example, if you have a distribution of scores with a mean of 40, and if your score is x equals 45, then its deviation score is 45 minus 40, which equals 5. Or example 2, if you have a distribution of scores again with a mean of 40, and your score is x equals 35, then this deviation score is 35 minus 40, which equals minus 5. There are 2 parts to a deviation score, the sign and the number. The sign tells the direction from the mean. In other words, whether the score is located above or below the mean. The number gives the distance from the mean. So for example, a deviation score of -2 is a score that is below the mean by 2 points. The next step is to calculate the mean of the deviation scores. So in other words, adding up the deviation scores and dividing by n. So for example, if we have a distribution of scores 10, 2, 0 and 4, their deviation scores will be 6, -2, -4 and 0. These deviation scores add up to 0. This always happens, no matter what the scores are. So the mean of the deviation scores will be 0 too, which means it is no value as a measure of variability. Step 3. The problem of the sum of the deviation scores equaling 0 results from the positive and negative signs. The solution is to get rid of the signs by squaring each of the deviation scores. Then we can calculate the mean squared deviation, which is also called the variance. So if we stick with this distribution of 10, 2, 0 and 4, the squared deviation scores are going to be 36, 4, 16 and 0. Adding these up gives us a total of 56. Now we want to get the mean squared deviation, so we're going to divide this 56 by 4 because we've got 4 scores. So 56 divided by 4 equals 14. That's the mean squared deviation, which we also call variance. The process of squaring deviation scores does more than simply get rid of the plus and minus signs. It results in a measure of variability based on squared distances. The concept of squared distance is not an intuitive or easy to understand descriptive measure. For example, it's not particularly useful to know that the squared distance from New York City to Boston is 26,244 miles squared. Therefore, we will continue the process one more step. Our goal is to calculate a measure of typical, or in other words, standard distance from the mean. We're not interested in squared distance. So we need to make one final step to correct for having squared all the distances. So to get to the standard deviation, we need to take the square root of the variance. And in the previous slide, we saw that our mean squared deviation, in other words the variance, equaled 14. So the standard deviation equals the square root of 14, 3.74. This is called the sum of squared deviations, or just the sum of squares. It's a key step in calculating the standard deviation. Sum of squares is a useful term that will come back to play in the inferential statistical techniques of hypothesis testing. For this reason, we want to spend a little bit of time on it here. There are two formulae for calculating sum of squares, and they're both algebraically equivalent. In other words, they always produce the same answer. The first is the derivational formula, and it's the most direct method. It's the one that we've just used. But it can be awkward to use, especially when the mean involves decimals. The second is called the computational formula, and it's easier to use. It calculates with the scores themselves, not the deviations, so it minimizes complications with decimals. Using the same distribution of 10, 2, 0 and 4, we're going to use the computational formula to calculate the sum of squares. The first thing we want to do is find the sum of x and the sum of x squared. So to find the sum of x, we're going to add up all the x values in our distribution. 10, 2, 0 and 4 add together to give us 16. Next we want to square these values. 10 squared is 100, 2 squared is 4, 0 squared is 0, and 4 squared is 16. Summing these values, 100 plus 4 plus 0 plus 16 gives us a value of 120 for the sum of x squared. So we're going to take this 16 and this 120 and substitute it into the computational formula. So the sum of squares equals 120 minus 16 squared divided by 4, because there's 4 scores in the distribution. That equals 120 minus 64, which is 56. So the sum of squares for this distribution of 10, 2, 0 and 4 is 56. With the definition and calculation of sum of squares behind you, the equations for variance and standard deviation become relatively simple. The population standard deviation uses the Greek letter sigma. So sigma equals the square root of the sum of squares divided by n. This is the population standard deviation. To emphasize the relationship between standard deviation and variance, we use the symbol sigma squared for population variance. So sigma squared equals the sum of squares divided by n. This is the population variance. To summarize the process for calculating standard deviation, first find the sum of squares. Then use this to calculate the variance. Then take the square root of the variance to find the standard deviation. The goal of inferential statistics is to use the limited information from samples to draw general conclusions about populations. The basic assumption of this process is that samples should be representative of the populations from which they come. This assumption poses a special problem for variability, because samples consistently tend to be less variable than their populations. An example of this general tendency is shown in this figure. Notice that a few extreme scores in the population tend to make the population variability relatively large. However, these extreme values are unlikely to be obtained when you're selecting a sample, which means that the sample variability is relatively small. The fact that a sample tends to be less variable than its population means that the sample variability gives a biased estimate of population variability. This bias is in the direction of underestimating the population value rather than being right on the mark. So far we've talked about populations. For samples the notation is different. We use Roman letters. S is the symbol for sample standard deviation, while S squared is the symbol for sample variance. But except for changes in notation, the method to calculate sum of squares is the same for populations and samples. Fortunately, the bias in sample variability is consistent and predictable, which means it can be corrected. For example, if the speedometer in your car consistently shows speeds that are 5 miles per hour slower than you're actually going, it does not mean that the speedometer is useless. It simply means that you must make an adjustment to the speedometer reading to get an accurate speed. In the same way, we will make an adjustment in the calculation of sample variance. This adjustment makes the resulting value for sample variance an accurate and unbiased representation of the population variance. The sample formula use n-1 instead of n. This corrects for the bias. The effect is to increase the value you obtain, compensating for the underestimation. So the sample standard deviation S equals the square root of the sum of squares divided by n-1, whereas the sample variance S squared equals the sum of squares divided by n-1. Let's go through an example. Let's calculate the sum of squares using the computational formula for a sample of scores 1, 6, 4, 3, 8, 7 and 6. So the first thing to do is to calculate the sum of x and the sum of x squared for this sample of scores. So 1, 6, 4, 3, 8, 7 and 6 add up to give us 35. That's the sum of x. We're going to square all the x values to give us 1, 36, 16, 9, 64, 49 and 36. Adding these together gives us a sum of x squared equal to 211. We're going to take 35 and 211 and substitute it into the computational formula. So the sum of squares equals 211 minus 35 squared divided by 7, because there's 7 scores in our sample. So the sum of squares equals 211 minus 175, which equals 36. Next, we're going to use the sum of squares value that we've just calculated to figure out the standard deviation for this sample of scores. We're going to start with the sample variance formula. So s squared equals the sum of squares divided by n minus 1. So substituting in the sum of squares in our n minus 1 value, we get 36 divided by 6, which gives us a sample variance of 6. We're then going to take the square root of this value, so the square root of 6, to give us a standard deviation of 2.45. This is the average distance of each score from the sample mean. Let's do another example. We'll calculate the standard deviation for the first 17 scores from the fasting blood glucose example in Module 2. The first thing we're going to do is calculate the sum of squares. To do that, we need to figure out the sum of x and the sum of x squared. So for example 2, the sum of x equals 1631, where the sum of x squared equals 160,549. We're going to substitute those two values into the equation for the sum of squares. So the sum of squares equals 160,549 minus 1631 squared divided by 17. This equals 160,549 minus 156,480.1, which gives us a sum of squares value of 4,068.9. We're then going to use the sum of squares to calculate the sample variance. So sample variance equals the sum of squares divided by n minus 1. So 4068.9 divided by 16 gives us a sample variance of 254.3. To get the standard deviation, we just take the square root of this. So the square root of 254.3 gives us a standard deviation of 15.9. Error bars are a graphical representation of the variability of data. Here in figure 4.2, the blue bar represents the sample mean of the first 17 scores from the fasting blood glucose examples in Module 2. The sample mean is 95.9. The error bar represents the standard deviation of 15.9. Error bars are used regularly in graphs to allow easy visual comparisons. A box plot, sometimes called a box and whisker plot, is a type of graph used to display patterns of quantitative data. A box plot splits the data into quartiles. The body consists of a box, where Q1 and Q3 are the edges, and Q2 is the line within the box. Two lines, called whiskers, extend from the front and back of the box. The front whisker goes from Q1 to the smallest non-extreme value in the dataset, and the back whisker from Q3 to the largest non-extreme value. If the dataset includes one or more extreme values, which we also call outliers, they are plotted separately as points on the chart. If you're interested in the spread of all the data, the range is represented in a box plot by the distance between the smallest value and the largest value, as we can see in figure A, which includes any outliers. This is the range. Sometimes researchers are interested in the spread of data excluding outliers, which is the range that we see represented in figure B, which extends from the front whisker to the back whisker. The interquartile range is represented in a box plot by the width of the box, as we can see in figure C. Box plots often provide information about the shape of a data set. Each of the above box plots illustrates a different skewness pattern. Figure 4.3 indicates a symmetrical box plot. Figure 4.4 represents a positively skewed box plot, whereas figure 4.5 represents a negatively skewed box plot. Without any frame of reference, a simple raw score provides relatively little information. To make raw scores more meaningful, they're often transformed into new values that contain more information. It would be useful to have a statistical technique that can identify and describe the exact location of every score in a distribution. The z-score combines the raw score, the mean and the standard deviation into a single number that precisely describes an exact location relative to the other scores in the distribution. It would also be useful to have a statistical tool that allows us to make meaningful comparisons between variables measured in different scales. For example, we measure height in inches but weight in pounds. In order to compare heights and weights, we need a way to put different variables in the same standardized scale. Z-scores also give us this ability to convert any variable to a standard distribution, allowing us to make comparisons among variables. Standardizing allows immediate familiarity and quick orientation. In statistics, scores and distributions of scores can differ widely. Standardizing scores and distributions can help to place data in a general context and allow us to directly compare them. Z-scores transform each x value into a signed number. The sign of a z-score tells you immediately whether the score is located above or below the mean, while the numerical value tells you the number of standard deviations from the mean. IQ tests are usually standardized to have a mean of 100 and a standard deviation of 15. In a distribution of IQ scores, a score of x equals 130 would be transformed into z equals plus 2. The z value indicates that the score is located above the mean by a distance of 2 standard deviations, i.e. 30 IQ points. This figure shows a population distribution with various positions identified by their z-score values. Notice that all z-scores above the mean are positive, and all z-scores below the mean are negative. A z-score of plus 1 corresponds to a position exactly 1 standard deviation above the mean. A z-score of plus 2 is always located exactly 2 standard deviations above the mean. The locations identified by z-scores are the same for all distributions, no matter what mean or standard deviation the distribution may have. The formula for transforming scores into z-scores is z equals x minus mu divided by sigma. The numerator of the equation, x minus mu, is a deviation score. It measures the distance in points between x and mu, and indicates whether x is located above or below the mean. The deviation score is then divided by sigma, because we want the z-score to measure distance in terms of standard deviation units. Although z-scores are most commonly used in the context of a population, the same principles can be used to identify individual locations within a sample, provided that you use the sample mean and the sample standard deviation. Let's run through 3 quick examples. Example 1. A distribution of scores has a mean of 90 and a standard deviation of 10. What z-score corresponds to a score of x equals 70? 70 minus 90 divided by 10 equals a z-score of minus 2. Example 2. A distribution of scores has a mean of 37 and a standard deviation of 4. What z-score corresponds to a score of x equals 39? 39 minus 37 divided by 4 equals a z-score of 0.5. Example 3. A distribution of scores has a mean of 40 and a standard deviation of 5. If we have a z-score of minus 1, what does that correspond to in terms of x? We need to rearrange the z-score formula so that x equals mu plus z times sigma, and then substitute in the values. Minus 1 times 5 equals minus 5. Minus 5 plus 40 gives us an x value of 35. It's possible to transform every x value in a distribution into a corresponding z-score. The result of this process is an entire distribution of z-scores. What effect does this z-score transformation have on the original distribution? Because each individual score stays in its same position within the distribution, the overall shape of the distribution does not change. The z-score distribution will always have a mean of 0 and will always have a standard deviation of 1. You can think of the z-score transformation as simply relabeling the values along the x-axis. That is, after a z-score transformation, you still have the same distribution, but now each individual is labelled with a z-score instead of an x value. Here's another example of this with a distribution of IQ scores. Let's look at a couple of examples to illustrate standardization in action. Example 4. Eric competes in 2 track events, standing long jump and javelin. His long jump was 49 inches and his javelin throw was 92 feet. He then measures all the competitors in both events and calculates the mean and standard deviation. The javelin competitors had a mean of 86 feet and a standard deviation of 10, while the long jump competitors had a mean of 44 inches and a standard deviation of 4. So which event did Eric do best in? Standardizing the jumping and throwing variables for these 2 different sporting events allows us to make a meaningful comparison between the 2. Eric's javelin result standardized into a z-score is 0.6, while his long jump z-score is 1.25. 1.25 is further away from the mean than 0.6. It shows us that Eric was more exceptional in the long jump event than in the javelin. Example 5. Rose has high blood pressure but exercises. She has a wellness score of 84 on a scale with a mean of 93 and a standard deviation of 4.5. Isabel is of normal weight but has high cholesterol. She has a wellness score of 332 on a scale with a mean of 312 and a standard deviation of 20. Using z-scores to standardize their different wellness variables, who's in better health? Standardizing their data into z-scores gives Rose a z-score of -2, while Isabel has a z-score of +1. Isabel is in better health because her score is above the mean, whereas Rose is below average by 2 standard deviations. So to sum up, z-scores combine information regarding the score, the mean and the standard deviation into a single number that precisely describes the location of a score relative to other scores in the distribution. And a second purpose for z-scores is to standardize an entire distribution, so we can have meaningful comparisons between different variables. In Module 1, we introduced the idea that research studies begin with a general question about an entire population, but the actual research is conducted using a sample. In this situation, the role of inferential statistics is to use the sample data as the basis for answering questions about the population. To accomplish this goal, inferential procedures are typically built around the concept of probability. How can we make a connection between samples and populations? Suppose we had 2 cubes that were each filled with blue and red marbles. The first cube has 50 blue and 50 red marbles, while the second cube has 90 that are blue and only 10 that are red. Think of the cubes as populations and the marbles as potential samples to be selected. If you were to close your eyes and pick a marble from each cube, what's the probability that you would select a blue or a red marble? Although we cannot guarantee the exact outcome of your choice, it's possible to talk about the likely outcome in terms of probabilities. With the first cube you have a 50-50 chance of getting either colour. In other words, you're just as likely to pick a blue marble as a red one. For cube 2, the probability is 90-10, or put more simply, 9-1. It's 9 times more likely that you pick a blue marble from this cube than a red one. Let's say we blindfolded you, randomly assigned one of the cubes, and allowed you to choose n of 4 marbles. Your task is to determine, based on your sample results, whether you've been given cube 1 or cube 2. You choose your 4 marbles one after the other, and they're all blue. Given your sample results, which cube would you conclude had been used? It should be clear that it would be relatively unlikely to obtain this sample from cube 1. The probability of this happening is low. In 4 draws, you almost certainly would get at least 1 red marble. On the other hand, this sample would have a high probability of coming from cube 2, where nearly all the marbles are blue. Your decision therefore should have been that the sample probably came from cube 2. Notice that you now have used the sample to make an inference about the population. Probability concerns proportions in populations. By knowing the makeup of a population, we can determine the probability of obtaining specific samples. The cube 1 population had 50 blue marbles and 50 red marbles. The proportions were 50-50, so the probability was also 50-50. Whereas the cube 2 population had 90 blue marbles and 10 red marbles, so the proportions were 90-10. Therefore the probability was also 90-10. Probability establishes a link between populations and samples. It allows us to predict which samples can be obtained given a certain population. Once we've established probability rules about the types of samples that likely would be obtained from a specific population, we can simply reverse those probability rules to allow us to move from samples back to populations. Let's talk through another way to illustrate this. A shark researcher has created an effective shark deterrent. It's an underwater beacon that gives off a sonic pulse humans can't hear, but that drives sharks away. As part of the developmental tests, he asked his assistant to deploy a beacon at one of 2 different beaches in Florida. However, the assistant loses his research notes and can't remember at which of the 2 beaches the beacon has been placed. To guess, he throws out a net of size n equals 6 and counts what is caught at both beaches. At beach A, the net catches 1 shark and 5 fish, while at beach B, the net catches 2 sharks and 4 fish. He then throws out bigger nets and counts what is caught at both beaches. With a net size of n equals 20, he catches 2 sharks and 18 fish at beach A, whereas at beach B he catches 8 sharks and 12 fish. Switching to a net size of n equals 100, he catches 6 sharks and 94 fish at beach A, whereas at beach B he catches 31 sharks and 69 fish. Given these sample results and the proportion of sharks to fish, it seems probable that the beacon was placed at beach A, which has by far the fewest sharks. To sum up what we've said so far, probability is used to predict what kind of samples are likely to be obtained from a population. Probability is to do with proportions in populations and establishes a mathematical connection between samples and their populations. Inferential statistics rely on this connection when they use sample data as the basis for making conclusions about populations. Probability is a huge topic, and we won't attempt to examine it all here. Instead, we'll concentrate on the few concepts and definitions that are needed for an introduction to inferential statistics. For a situation in which several different outcomes are possible, the probability for any specific outcome happening is defined as a fraction or a proportion of all the possible outcomes. In other words, probability equals proportion of outcome. If the possible outcomes are identified as A, B, C, D, and so on, then the probability of A happening equals the number of outcomes that we class as A divided by the total number of outcomes. For example, if you're tossing a coin, there are two possible outcomes, heads or tails. The probability of getting heads is 1 in 2 because only one outcome qualifies as heads, and there are two possible outcomes in total. The 1 in 2 or 50-50 probability can be expressed as a proportion, 0.5, or as a percentage, 50%. To simplify the discussion of probability, we use notation that eliminates a lot of the words. The probability of a specific outcome is expressed with a P for probability, followed by the specific outcome in parentheses. For example, the probability of selecting a king from a deck of cards is written as P brackets king. There are 4 outcomes that can be classed as king. In other words, there are 4 cards that can be identified as kings in a deck. The king of spades, the king of hearts, the king of clubs, and the king of diamonds. So the probability of selecting a king from the whole deck is 4 out of 52. Note that probability is defined as a proportion, or a part of the whole. This makes it possible to restate any probability problem as a proportion problem. For example, the probability problem, what is the probability of selecting a king from a deck of cards, can be restated as what proportions of the whole deck consist of kings. In this situation, the whole deck of cards can be considered the population, and the single card we select is the sample. By convention, probability values are most often expressed as decimals. Here, 4 out of 52 is 0.0769 as a decimal, or 7.69% as a percentage. Any of these forms, fraction, decimal, percentage, is an acceptable way to express probability. You should also note that all the possible probability values are contained in a limited range. At one extreme, when an event never occurs, the probability is 0, or 0%. At the other extreme, when an event always occurs, the probability is 1, or 100%. Thus, all probability values are contained in a range from 0 to 1, and they always have positive values. For our definition of probability to be accurate, it's necessary that the outcomes be obtained by a process called random sampling. A random sample requires that these two conditions must be met. First, each individual has an equal chance of being selected, and second, if more than one individual is selected, there must be constant probability for each selection. This requires sampling with replacement. Let me illustrate these two criteria with a deck of playing cards. First, the importance of each individual having an equal chance of being selected. Think of the deck of cards as the population, and the single card as an individual being selected as part of a sample. The deck is shuffled and the goal is to try and select a king. The chances of success are considerably different for the first selection than the second. It's obvious that the first attempt is not random because the cards are face up. However, the mathematical reason that it's not random is that the probabilities associated with each choice were not equal. The second criterion for a random sample requires sampling with replacement. Let's try again to select a king from the deck. We said earlier that the probability of success was 4 in 52. The first sampling results in a 4 of spades. Leaving that card to the side changes the probability of selecting a king from 4 in 52 to 4 in 51. The second sampling results in a 6 of clubs. Now the probability of choosing a king drops to 4 in 50. In order to maintain a constant probability for selection, the card that was drawn must be replaced back into the deck before the second sampling attempt. By doing this, we have kept the probability at 4 in 52 for both samplings. Let's think of this another way. Say we want to select a sample of n equals 50 people from Connecticut by having a computer randomly choose a Connecticut cell phone number. We can't give preferential treatment to AT&T customers over those in Verizon or Sprint. That wouldn't be giving each individual an equal chance of being picked. And secondly, after someone has been chosen, the number needs to be replaced back into the population of numbers before we select a second person. We can't leave them to the side. They should have the same probability of being picked again as any other individual in the population. This is sampling with replacement. Having truly random samples minimises error and bias, but can be challenging to achieve. The situations in which we are concerned with probability usually will involve a population of scores that can be displayed as a frequency distribution graph. If the graph represents the entire population, then different portions of the graph represent different portions of the population. Probability is equal proportions, so a particular portion of the graph corresponds to a particular probability in the population. The reverse is also true. The relationship between graphs and probabilities is demonstrated in example 3. For a simple population that contains only n of 10 scores, what's the probability that a random sample of n of 1 will have a score greater than 4? Using the definition of probability, there are 2 scores that meet this criterion out of the total group of 10 scores. So the answer would be 2 out of 10, which is a 1 in 5 probability, or 20%. If we were to answer this question by looking at the graph, the shaded part of the figure indicates the portion of the whole population that corresponds to a score greater than x equals 4. We're now defining probability as a proportion of area in the frequency distribution graph. This provides a very concrete and graphic way of representing probability. We introduced the normal distribution in Module 2 as an example of a commonly occurring shape for population distributions. Statisticians often identify sections of a normal distribution by using z-scores. It's possible to describe the normal shape by the proportions of area contained in each section of the distribution. This figure shows a normal distribution with several sections marked in z-score units. The graph shows the percentage of scores that fall in each of these sections. For example, the section between the mean and a z-score of 1 contains 34.13% of the scores. 13.59% of the distribution scores are located between z-scores 1 and 2. 2.28% fall between z-scores 2 and 3. The percentages shown apply to any normal distribution, regardless of the values for the mean and the standard deviation. The sections on the left of the distribution have exactly the same areas as the corresponding sections on the right side, because the normal distribution is symmetrical. Approximately 68% of the distribution falls within plus or minus 1 standard deviation of the mean. Approximately 95% falls within plus or minus 2 standard deviations of the mean, whereas 99.7% fall within 3 standard deviations of the mean. This figure sums up these 3 important proportions and the relationship to standard deviations of the mean. This allows us to solve problems like the following. Height has a normal distribution with a mean of 6 to 8 inches and a standard deviation of 6. If we select one person at random, what's the probability for selecting a person taller than 80 inches? Converting x equals 80 into a z-score, we get a value of +2. The proportion of scores in the tail beyond z equals 2 is roughly 2.28%. This is the percentage of the human population who are taller than 6'8". This graph shows proportion for only a few selected z-scores. A more complete listing of z-scores and proportions is provided in the unit normal table. This table lists proportions of the normal distribution for a full range of possible z-scores. The complete unit normal table is provided as a separate PDF. With the part that's reproduced here, notice that the table is structured into a 4-column format. The first column, A, lists z-score values corresponding to different positions in a normal distribution. If you imagine a vertical line drawn through a normal distribution, then the exact location of the line can be described by one of the z-score values listed in column A. You should also realize that a vertical line will separate the distribution into two sections, a larger section called the body and a smaller section called the tail. Columns B and C in the table identify the proportion of the distribution in each of these two sections. Column B presents the proportion in the body, and column C presents the proportion in the tail. Lastly, the fourth column, column D, identifies the proportion of the distribution that is located between the mean and the z-score. To make full use of the unit normal table, there are a few facts to keep in mind. The body always corresponds to the larger part of the distribution, whether it's the right-hand side or the left-hand side. Similarly, the tail is always the smaller section, whether it's on the right or the left. Because the normal distribution is symmetrical, the proportions on the right-hand side are exactly the same as the corresponding proportions on the left-hand side. For example, the proportion in the right-hand tail beyond z equals +1 is exactly the same as the proportion in the left-hand tail beyond z equals -1. Note that the table does not list negative z-score values. To find proportions for negative z-scores, you must look up the corresponding proportion for the positive value of z. Although the z-score values change signs, from positive to negative, from one side to the other, the proportions are always positive. Thus, column C in the table always lists the proportion in the tail, whether it's the right-hand tail or the left-hand tail. The unit normal table lists relationships between z-score locations and proportions in a normal distribution. For any z-score location, you can use the table to look up the corresponding proportions. Similarly, if you know the proportions, you can use the table to look up the specific z-score location. Because we have defined probability as equivalent to proportion, you can also use the unit normal table to look up probabilities for normal distributions. The following examples demonstrate a variety of different ways that the unit normal table can be used. Let's look at the step-by-step procedure with a generic example first. For a normal distribution with a mean of 500 and a standard deviation of 100, what's the probability of selecting an individual whose score is above 650? In other words, what's the proportion of the population with a score above 650? In order to solve this, you should first of all make a rough sketch and mark on it the mean and the standard deviation. Then locate and mark on your sketch the specific x-score. Shade the appropriate proportion you're trying to find, then transform the x value into a z-score. Then look up this z-score value for proportion in the unit normal table. Let's go through some specific examples from start to finish. Example 4. What proportion of the normal distribution corresponds to z-score values greater than z equals +1? First of all, make a rough sketch and mark on it the mean and the standard deviation. Then mark on it the z-score value that you're trying to find. In this case, z equals +1. Next, you should shade the proportion that you're trying to locate. The greater than wording in the problem means that the proportion we're trying to locate is to the right of the z-score. Then looking up z equals 1 in column A of the unit normal table and reading the information in column C, the proportion is 0.1587 or 15.87%. Example 5. For a normal distribution, what's the probability of selecting a z-score less than 0.15? So again, make a rough sketch, mark on it the mean and the standard deviation, and then mark on it the z-score value that you're trying to locate. In this case, z equals 1.5. The less than wording in the problem means that the proportion you're going to shade and then look up is to the left of the z-score. So it's a body. Then looking up z equals 1.5 in column A of the unit normal table and reading the proportion information from column B, the answer is 0.9332 or 93.32%. Example 6. What proportion of the normal distribution is contained in the tail beyond z equals negative 0.5? Again, make a rough sketch and mark on the mean and the standard deviation, and then mark on it the z-score value that you're trying to locate. So in this case, z equals negative 0.5. The beyond wording in the problem means that the proportion you're going to shade and then locate in the table is located in the left tail beyond z equals negative 0.5. The proportion in the left tail beyond z equals negative 0.5 is identical to the proportion in the right hand tail beyond z equals plus 0.5. So to find the proportion, look up z equals 0.5 in column A and then find the proportion information in column C. The answer is 0.3085 or 30.85%. Example 7. For a normal distribution, what z-score separates the top 10% from the remainder of the distribution? Again, start by making a rough sketch. To find this z-score value, you need to locate 10%. 10% as a decimal is 0.1, which you can look up in column C of the unit normal table. Alternatively, you could look up 90% or 0.9, which was going to be in column B because it represents a body. You probably won't find the exact proportion you're looking for, but you can use the closest value listed in the table. In our case, 0.1003. Reading across from this to the corresponding z-score value in column A, you find the answer. The z-score value that separates the top 10% is z equals plus 1.28. Example 8. For a normal distribution, what are the z-score values that separate the middle 60% of the distribution from the rest of the scores? Again, start by making a sketch. To find these z-score values, we begin with the known proportions, which is 60% in the centre and 40% divided equally between the two tails. 60% as a decimal is 0.6. The 0.6 in the centre can be divided in half, with exactly 0.3 to the right and the left of the mean. Looking in column D for a value of 0.3, you'll see that the exact proportion is not in the table, but the closest value is 0.2995. Then read across the row to column A and you should find a z-score value of z equals 0.84. Our answer is plus 0.84 and minus 0.84. These are the z-score values that separate the middle 60% of a distribution from the rest of the scores. When a variable is measured on a scale consisting of exactly two categories, the resulting data are called binomial. The term binomial can be loosely translated as two names, referring to the two categories in the measurement scale. Binomial data can occur when a variable naturally exists with only two categories. For example, People can be classified as male or female, and a coin toss results in either heads or tails. It's also common for a researcher to simplify data by collapsing the scores into two categories. For example, a psychologist may use personality scores to classify people as either high or low aggression. Binomial distribution is often used in genetic counselling. For example, Tay-Sachs disease is a metabolic disorder that is inherited as an autosomal recessive trait. Both recessive alleles are necessary for expression of the disease. Inheritance of a disorder such as Tay-Sachs disease follows a binomial distribution. There are two possible events: inheriting the disease or not inheriting the disease. Both are mutually exclusive. A person can't both have the disease and not have it at the same time, and these two possibilities are independent of each other. A physician could therefore use the binomial distribution to inform a couple who are carriers of the disease and that have 3 children what the probabilities of the following are: that all 3 children develop Tay-Sachs, that only 1 child develops Tay-Sachs, or that the 3rd child develops Tay-Sachs, given that the first 2 did not. In binomial situations, the researcher often knows the probabilities associated with each of the 2 categories. For example, with a balanced coin, the probability of getting heads is 0.5, and the probability of getting tails is also 0.5. The number of times each category occurs in a series of trials, or in a sample of individuals, is usually the question of interest. For example, what's the probability of obtaining 15 heads in 20 coin tosses? Or what's the probability of obtaining more than 40 introverts in a sample of 50 college freshmen? Or what's the probability of at least 12 patients recovering out of 20 who have contracted a stomach disease? To answer probability questions about binomial data, we need to examine the binomial distribution. To define and describe this distribution, we first introduce some notation. The 2 categories are identified as A and B. The probabilities or proportions associated with each category are identified as P brackets A, which is the probability of A, and Q brackets B, the probability of B. Notice that P plus Q equals 1 because A and B are the only 2 possible outcomes. The number of individuals or observations in the sample are identified by N, and the variable X refers to the number of times category A occurs in the sample. X can have any value from 0, which means that none of the sample is in category A, to N, which means that all of the sample is in category A. To construct a binomial distribution, we'll look at all the possible outcomes from tossing a coin twice. The complete set of 4 outcomes is listed below. The probability of getting 2 heads is 1 in 4, while the probability of getting 1 head and 1 tail is 1 in 2, and the probability of getting 2 tails is 1 in 4. Drawing the binomial distribution from the previous example, we get this figure. The binomial distribution can be used to answer probability questions. For example, what's the probability of obtaining at least 1 head in 2 coin tosses? According to the distribution, the answer is 3 out of 4. These binomial distributions show the probability for the number of heads in 2 tosses, 8 tosses, 16 tosses, and 64 tosses of a balanced coin. It should be obvious from the graphs here that binomial distributions tend towards a normal distribution shape, especially when the sample size n is relatively large. The binomial distribution tends to approximate the normal distribution as n gets large, or more precisely as p times n and q times n are greater than 10. Under these circumstances, the binomial distribution will approximate the normal distribution with the following parameters. The mean equals p times n, and the standard deviation equals the square root of n times p times q. This means that given p, q, and n, we can directly derive z-scores using this formula. The fact that the binomial distribution tends to be normal in shape means that we can compute probability values directly from z-scores in the unit normal table. It's important to remember that the normal distribution is only an approximation of a true binomial distribution. Binomial values are discrete, but the normal distribution is continuous. However, the normal approximation provides an extremely accurate model for computing binomial probabilities in many situations. This figure shows the difference between the binomial distribution, which is always a discrete histogram, and the normal distribution, which is a continuous smooth curve. Although the two distributions are slightly different, the area under the distributions is nearly equivalent. It's the area under the distributions that is used to find probabilities. Let's go through some examples. Example 9. Using a balanced coin, what's the probability of obtaining more than 30 heads in 50 coin tosses? The first thing to do is to write down the information for P, Q, N, and X. The probability of getting a head is 0.5, and the probability of getting a tail is also 0.5. Our N number is 50 because we're doing 50 coin tosses, but what about our X value? To get the maximum accuracy when using the normal approximation, you need to remember that each X value is a bar bounded by real limits. So X equals 30 is everything from X equals 29.5 to 30.5. The problem asks us about the probability of obtaining more than 30 heads. So we need to use the upper real limit of 30 for our X value, which is 30.5. Next we need to figure out the mean and the standard deviation. The mean equals P times N, or 0.5 times 50, which equals 25. The standard deviation is the square root of N times P times Q, which equals the square root of 12.5, which is 3.54. Then we're going to calculate a z-score value. So 30.5 minus 25 divided by 3.54, which equals 1.55. Looking up this z-score of 1.55 in the unit normal table and reading across the column C, the probability is 0.0606, or 6.06%. Example 10. A friend bets you that you can draw a king at least 9 times in 20 draws with replacement from a fair deck of cards, and he does it. Is this a likely outcome, or should you conclude that the deck is not fair and that your friend is cheating? Again, the first thing to do is to figure out the P, Q, N, and X information. The probability of choosing a king is 4 out of 52, or 0.077, while the probability of choosing any other card is 48 out of 52, or 0.923. Our N number is 20, and the X value that we're going to use is 8.5. The problem asks us to determine the probability for at least 9 times, so we need to include 9. Anything 9 or above, in other words. In order to do that, we need to use the lower real limit for the value 9, which is 8.5. Then we're going to calculate the mean and the standard deviation. So the mean equals P times N, which is 0.077 times 20, which equals 1.54. The standard deviation is the square root of N times P times Q, which equals the square root of 1.42, which equals 1.19. We're then going to convert this information into a z-score. So z equals 8.5 minus 1.54 divided by 1.19, which equals 5.85. Try to look up z equals 5.85 in the unit normal table, but it's not there. This means that the probability is essentially 0. In other words, your friend is cheating. It's very unlikely to obtain an individual from the original population who has a z-score beyond plus or minus 1.96. Less than 5% of any population fit into this area under the curve. Therefore, we classify an event as being unlikely to happen by chance. In other words, it's more likely to have had a deliberate cause if it is a less than 5% probability of occurring in a normal population. What the card magician did in example 10 was very unlikely. The probability was less than 5%. But the coin flip from example 9 can still be explained by chance. The probability is greater than 5%. Example 11. A new surgical procedure has a success rate of P equals 0.6. If the operation is performed 5 times, what's the probability that less than 2 are successful? Again, we need to first figure out P, Q, N, and X. So the probability of success is 0.6. This means that the probability of failure, Q, equals 0.4. We know this because P and Q always add up to 1. Our N number is 5, and the X value that we need to use is 1.5. This is because the question asks us for the probability that less than 2 are successful, so we need to use the lower real limit of 2. Then we're going to find the mean and the standard deviation. So the mean equals P times N, or 0.6 times 5, which equals 3. The standard deviation is the square root of N times P times Q, which equals the square root of 1.2, which is 1.1. Using this information to calculate a z-score, we get z equals 1.5 minus 3 divided by 1.1, which equals negative 1.36. Looking up 1.36 in the unit normal table and looking at column C, we get proportion of 0.0869, or 8.69%. That's the probability that less than 2 of the operations out of 5 are successful. Example 12. Let's stick with the same problem, but this time ask the question, what's the probability that exactly 4 out of 5 surgical procedures are successful? Again, we need to find P, Q, N, and X. So the probability of success is again 0.6, and the probability of failure, Q, is still 0.4. N is 5, and this time we need to use two X values, 3.5 and 4.5, because we're trying to find the probability of exactly 4, which is bounded by the lower real limit of 3.5 and the upper real limit of 4.5. Our mean and our standard deviation information are the same, but this time we need to calculate two z-scores. The first z-score is 3.5 minus 3 divided by 1.1, which gives us a z-score of 0.45. Looking up z equals 0.45 in the unit normal table and looking to column C, we get a proportion of 0.3264. Our second z-score value equals 4.5 minus 3 divided by 1.1, which is 1.36. Looking up z equals 1.36 in the unit normal table and looking to column C gives us a probability of 0.0869. Next, it's best if you make a rough sketch and shade the area that you're trying to find. So the area between the two scores is 0.3264 minus 0.0869, which equals 0.2395, or 23.95%. This is the probability that exactly 4 of the 5 operations are successful. So far we've considered the probability of obtaining single outcomes for given events. It's often necessary to calculate the probability of 2 or more outcomes for a given event. How we calculate probabilities for multiple outcomes depends on the relationship between each outcome. The addition rule of probability states that the probability of any one of several particular events occurring is equal to the sum of their individual probabilities, provided that the events are mutually exclusive, i.e., they cannot both happen. For example, the probability that someone in the human population has an AB blood type is roughly 0.08, while the probability for O-type blood is roughly 0.25. The outcomes type AB and type O blood are mutually exclusive. An individual can't have both blood types at the same time. But we can use the addition rule to find the probability that a person has either type AB or O-type blood. This probability is 0.08 plus 0.25, which equals 0.33, or in other words, 33%. The multiplication rule of probability states that the probability of two or more statistically independent events, all occurring, is equal to the product of their individual probabilities. For example, the lifetime probability of a person developing cancer is p equals 0.25, and the lifetime probability of developing schizophrenia is p equals 0.01. The outcomes, developing cancer or schizophrenia, are independent of each other. In other words, having one illness neither increases nor decreases the risk of having the other. We can use the multiplication rule to find the lifetime probability that a person might have both cancer and schizophrenia. This probability is 0.25 times 0.01, which equals 0.0025, or in other words, 0.25%. The z-scores and probabilities that we have considered so far are limited to situations in which the sample consists of a single score. Most research studies involve much larger samples, such as n equals 40 children with appendicitis, or n equals 500 people with seasonal pollen allergies. In these situations, the sample mean rather than a single score is used to answer questions about the population. We're going to extend the concepts of z-scores and probability to larger samples and introduce a procedure for transforming a sample mean into a z-score. In these situations, the sample mean rather than a single score is used to answer questions about the population. We're going to extend the concepts of z-scores and probability to larger samples and introduce a procedure for transforming a sample mean into a z-score. A researcher would then be able to calculate a z-score that describes an entire sample. As always, a z-score value near 0 indicates a central representative sample, while a z-value beyond plus or minus 2 indicates an extreme sample. Thus, it's possible to describe how any specific sample is related to all the other possible samples. In addition, we can use the z-score values to look up probabilities for obtaining certain samples, no matter how many scores the sample contains. It's usually possible to obtain thousands or even millions of different samples from the same population. Under these circumstances, how can we determine the probability for obtaining any specific sample? Additionally, although it's intuitively reasonable that sample size is an important factor in determining how accurately a sample represents its population, we need to quantify exactly how sample size influences the probabilities. In general, the difficulty of working with samples is that a sample provides an incomplete picture of the population. Suppose a researcher selects a sample of n equals 25 students from a state college. Although the sample should be representative of the entire student population, there will almost certainly be some segments of the population that are not included in the sample. Furthermore, samples are variable. They're not all the same. If you take two separate samples from the same population, the samples will be different. They will contain different individuals, they will have different scores, and they will have different sample means. Given that thousands of different samples can come from one population, it may seem hopeless to try to establish some simple rules for the relationships between samples and populations. Fortunately, however, the huge set of possible samples forms a relatively simple and orderly pattern that make it possible to predict the characteristics of a sample with some accuracy. The ability to predict sample characteristics is based on the distribution of sample means. The distribution of sample means is the collection of sample means for all the possible random samples of a particular size that can be obtained from a population. To illustrate this, let's consider a population that consists of only 4 scores: 2, 4, 6, and 8. We're going to use this population as the basis for constructing the distribution of sample means for n equals 2. For this example, there are 16 different possible ways to choose 2 values from this population of 4 scores. They're all listed in this table. The sample means for each of the 16 different possible samples is also listed. The 16 means can then be placed in a frequency distribution histogram. This is the distribution of sample means. We can use this distribution of sample means to answer probability questions about samples. For example, what's the probability of obtaining a sample mean greater than 7? Things to note about the distribution. The mean of the sample means equals the mean of the population. The shape looks normal, and we can use this distribution to answer questions about probabilities. The construction of this distribution of sample means is for an overly simplified situation with a very small population and samples that each contain only n of 2 scores. In more realistic circumstances with larger populations and larger samples, the number of possible samples will increase dramatically and will be virtually impossible to obtain every possible random sample. Fortunately, it's possible to determine exactly what the distribution of sample means will look like without taking hundreds or thousands of samples. Specifically, a mathematical proposition known as the central limit theorem provides a precise description of the distribution that would be obtained if you selected every possible sample, calculated every sample mean, and then constructed a distribution of those sample means. It's brilliant because it describes the distribution of sample means for any population, no matter what shape, mean, or standard deviation. And by the time the sample size reaches n equals 30, the distribution is almost perfectly normal. The essence of central limit theorem is that for any population with mean mu and standard deviation sigma, the distribution of sample means for sample size n will have a mean of mu and a standard deviation of sigma divided by the square root of n, and will approach a normal distribution as n approaches infinity. From our previous example, you can see that the distribution of sample means is centered around the mean of the population from which the samples were obtained. The mean of the distribution of sample means is equal to the mean of the population scores. In this example, they both equal 5. The mean of the distribution of sample means is called the expected value of x bar. To completely describe the distribution of sample means, we need one more characteristic: variability. Variability equals the standard deviation for the distribution of sample means. It's identified by the symbol sigma x bar, and it's called the standard error of the mean, or sometimes just the standard error. The standard error provides a measure of how much distance is expected on average between a sample mean and the population mean. Remember that a sample is not expected to provide a perfectly accurate reflection of its population. Although a sample mean should be representative of the population mean, there typically is some sampling error between the sample and the population. The standard error measures exactly how much difference should be expected on average between a sample mean and the population mean. In other words, the standard error provides a method for defining and measuring sampling error. The standard error is an extremely valuable measure because it specifies precisely how well a sample mean estimates its population mean. The magnitude of the standard error is determined by the size of the sample and the standard deviation of the original population the sample came from. The primary use of the distribution of sample means is to find the probability associated with any specific sample. The distribution of sample means presents the entire set of all possible sample means, so that we can use proportions of this distribution to determine probabilities. The formula for standard error expresses the relationship between standard deviation and sample size. The following examples demonstrate this process. Example 1. A population of SAT scores forms a normal distribution with a mean of 500 and a standard deviation of 100. If you take a random sample of n equals 25 students, what's the probability that the sample mean will be greater than 540? So the first thing to do is calculate the standard error, which is the standard deviation divided by the square root of n. So 100 divided by the square root of 25, which equals 20. We're then going to change the sample mean into a z-score. So 540 minus 500 divided by the standard error, which is 40 divided by 20, which gives us a z-score of plus 2. Looking up the z-score of 2 in the unit normal table gives us a probability of 0.0228, or in other words, 2.28%. This means that if you choose a random sample of 25 students, there's only a 2.28% probability that their SAT scores are going to have a sample mean greater than 540. Example 2. Let's say a population of IQ scores forms a normal distribution with a mean of 100 and a standard deviation of 15. What's the probability of obtaining a sample mean greater than 105 from a sample of n equals 9 people? So again, we calculate the standard error first. 15 divided by the square root of 9 equals 5. We're then going to change the sample mean into a z-score. So 105 minus 100 divided by the standard error equals 5 divided by 5, which is a z-score of 1. Looking at 1 in the unit normal table gives us a probability of 0.1587, or 15.87%. That's the probability of choosing a sample of 9 people who have a mean greater than 105 in terms of IQ. Example 3. Let's say again we have a population of IQ scores that forms a normal distribution with a mean of 100 and a standard deviation of 15. What's the probability of obtaining a sample mean greater than 105 from a sample this time of n equals 36 people? Again, the first thing is to calculate the standard error. 15 divided by the square root of 36 equals 2.5. We're then going to change the sample mean into a z-score. So 105 minus 100 divided by the standard error is 5 divided by 2.5, which gives us a z-score of plus 2. Looking 2 up in the unit normal table gives us a proportion of 0.0228, or 2.28%. This makes sense. Comparing example 2 and example 3, it should be less probable to have a sample of 36 people with an average IQ of greater than 105 than just having a sample of 9 people with an average IQ of greater than 105. Example 4. A population of heart rates form a normal distribution with a mean of 75 and a standard deviation of 10. If n equals 4 are selected as a sample, what proportion of the samples will have means less than 80? Again, our first step is to calculate the standard error. So 10 divided by the square root of 4 equals 5. Changing the sample mean into a z-score, 80 minus 75 divided by the standard error gives us a z-score of plus 1. Looking up plus 1 in the unit normal table gives us a probability of 0.8413, or 84.3%. It's quite probable that choosing 4 people from a sample, their average heart rate is going to be lower than 80 beats per minute. Example 5. Again, a population of heart rates form a normal distribution with a mean of 75 and a standard deviation of 10. If we choose n equals 16 people this time as a sample, what proportion of the samples will have means less than 67? Again, calculate the standard error first. 10 divided by the square root of 16 equals 2.5. We're then going to change the sample mean into a z-score, so 67 minus 75 divided by the standard error, which is negative 8 divided by 2.5. That's going to give us a z-score of negative 0.64. Looking up 0.64 in the unit normal table gives us a proportion of 0.2611, or 26.11%. That's the probability that if we choose a sample of 16 people, their average heart rate is going to be less than 67 beats per minute. In general, as the sample size increases, the error between the sample mean and the population mean should decrease. Notice that the size of the standard error decreases in these distributions as the sample size increases. With respect to visual displays of data, error bars are used to represent variation. Figure 7.2 is a bar graph of mean serum cholesterol levels from 3 separate samples of n equals 25 each. The bars have 3 different heights and the error bars have 3 different widths, which reflects the fact that all 3 samples, which were taken from the same population, have 3 different sample means and 3 different sample standard deviations. Figure 7.3 is a bar graph of combined mean serum cholesterol levels from these 3 samples. The bar height represents the overall mean, while the error bars reflect the standard error of the mean. The smaller the error bars, the smaller the variability. So the small error bars in Figure 7.3 indicate that the 3 samples of Figure 7.2 are fairly similar to each other. Hypothesis testing identifies whether an effect exists in a population. It does not, however, inform us of how big the effect is. Researchers tend to be interested in big effects, but hypothesis testing by itself can create an illusion of exaggerated importance. A very small difference found using a very large sample can be statistically significant because sample size strongly influences the outcomes of hypothesis testing. A small difference between a sample mean and a population mean might not be statistically significant with a small sample, but it could be statistically significant with a somewhat larger sample, and it would almost certainly be statistically significant with an extremely large sample. But just because a real difference exists does not mean it's a large or meaningful difference. In short, statistical significance does not indicate practical importance. So if we reject the null hypothesis, all we really see is that there's a significant effect of our treatment. In other words, the changes observed were not due to chance. This says nothing about how substantial or how big the effect is. For example, we could research into how quickly M&Ms melt in your hand. We run through the hypothesis testing procedure and do our experiment. Our results show that red M&Ms melt significantly faster than the other colours. We found a significant result. But how substantial an effect is it? Let's say it turns out that red M&Ms melt 0.74 seconds faster than any other colour. The effect size of the red colour is small. It's statistically significant, but nonetheless trivial. A statistically significant finding, particularly one from a study using a large sample, may indicate a genuine difference between groups, but a trivial one, with no real-world application. This is where effect size comes in. Effect size indicates the absolute magnitude of a difference, and is unaffected by sample size. It's recommended that whenever researchers report a statistically significant effect, they also provide a report of the effect size. There are many different effect size statistics, but they all neutralize the influence of sample size. One of the simplest and most direct methods for measuring effect size is called Cohen's d. It's named after Jacob Cohen, who was an American statistician and psychologist at NYU who proposed this method for measuring effect size. Cohen's d equals the difference between the sample mean and the population mean divided by the standard deviation. Cohen proposed these rules of thumb for interpreting effect size. However, Cohen also warned that they may be different for each field of study. Let's go through an example. A researcher is investigating the effectiveness of a new medication for lowering the blood pressure of individuals with a systolic pressure greater than 140 millimeters of mercury. For this population, systolic scores average 160, with a standard deviation of 20, and the scores form a normal shaped distribution. The researcher selects a sample of n equals 500 individuals and measures their systolic pressure after they take the medication for 60 days. He finds a sample mean of 157, and using an alpha level of 0.05, finds a statistically significant decrease. He's thrilled. With a sample of n equals 500, the standard error of the mean is 0.89, and our z-score is minus 3.37. For an alpha level of 0.05, the critical regions would begin at z equals plus or minus 1.96. The z-score is beyond the minus 1.96 boundary, so the researcher rejects the null hypothesis and concludes that there's a significant effect. Now consider the outcome if a sample of n equals 25 had been used instead. With a sample of 25, the standard error is 4, and our z-score is minus 0.75. This z-score fails to reach the critical region, so the researcher fails to reject the null hypothesis. Here the 3-point difference between the sample mean and the population mean is considered to be insignificant because it's being compared to a standard error of 4 versus a standard error of 0.89. Let's measure Cohen's d to measure the effect size of this treatment. Cohen's d equals 157 minus 160 divided by 20, which equals 0.15. Using Cohen's rules of thumb, this would be interpreted as a small effect size. And that makes sense. There's no real-life medical application for giving a population of hypertensive patients a drug that only lowers their blood pressure by 3 points. Going from 160 millimeters of mercury to 157 isn't going to help them. They're still going to be hypertensive. Hypothesis testing seeks to learn more about the value of a parameter in a population of interest by deciding whether to retain or reject a null hypothesis. We can also learn this information by using an alternative technique called estimation. Estimation does not require that we state a null hypothesis and decide whether it should be rejected. We use estimation to measure the mean in a sample, as we did in hypothesis testing, but instead of making a decision regarding a null hypothesis, we estimate the limits within which the population mean is likely to be contained. The use of estimation is common in the popular media. There are two types of estimation. The point estimate is a single number used to estimate the population parameter, whereas the interval estimate provides a range of plausible values. Let's go through an example. A research study has demonstrated that self-hypnosis can be an effective treatment for allergies. A sample of patients with moderate to severe allergic reactions were trained to focus their minds in a specific place where allergies do not bother them, such as a ski slope in winter. The participants were then tested for allergic reactions to pollen with and without using self-hypnosis. This sample of n equals 16 had a mean decrease in allergic reaction of 21%. We could use this data to estimate how much effect self-hypnosis would have on the general population of individuals with moderate to severe allergies. So a point estimate would take the sample mean of 21% and infer that the population would also see a 21% decrease in allergic reaction. Whereas the interval estimate would take the sample mean of 21% and infer that the population would see a decrease in allergic reaction of somewhere between 18 and 24%. In October 2012, Quinnipiac University's Polling Institute surveyed likely voters in Colorado, Virginia, and Wisconsin to ask them the following question. If the election for president were being held today, and the candidates were Barack Obama the Democrat and Mitt Romney the Republican, for whom would you vote? The following data were the results of surveying these samples. 47% of the Colorado sample said they would vote for Obama. 48% said they would vote for Romney. 2% said they would vote for someone else. And 2% said they didn't know who they would vote for. A point estimate would take the sample data and infer that the voting percentages would be true of all likely voters in Colorado, whereas the interval estimate would take the reported margin of error of plus or minus 2.8% and estimate a range of plausible values for this population of likely voters. In February 2013, Quinnipiac University's Polling Institute surveyed 1,011 Ohio registered voters to ask the question, from what you've heard or read, do you think the 2010 healthcare law will mostly help you personally, will mostly hurt you personally, or don't you think it will have much of an effect on you personally? The following data are the results of that survey. This figure represents some of the interval estimates that infer how the Democratic, the Republican, the Independent, the white, or the black populations of Ohio would respond to this question. Hypothesis testing and estimation both use sample statistics to find something out about an unknown population. Hypothesis testing provides yes-no information on whether an effect exists, whereas estimation provides information about the magnitude of an effect. Estimation should be used in the following circumstances. After a hypothesis test where the null hypothesis has been rejected, to find out the magnitude of the effect. Or when it's already known that there's an effect, but you want to find out how substantial it is. Or when you want to gather some basic information about a population. To review, a summary statistic such as the sample mean is used as a point estimate of the population mean. A more useful estimate is the interval estimate. This provides a range of plausible numbers for the population mean. The most commonly used interval estimate is the confidence interval, which can be created by subtracting and adding a margin of error from a mean, and is used to indicate the reliability of an estimate. The confidence interval is stated within a given level of confidence, for example, 80% or 90% or 95%. This is the likelihood that an interval contains the unknown population mean. Exactly how confident we are depends on the level of confidence chosen. The 95% confidence level is the most commonly used. A lot of similar sounding terminology surrounds confidence intervals. The confidence interval is the interval or range of possible values within which an unknown population parameter is likely to be contained. The level of confidence is the probability or likelihood that an interval estimate will contain an unknown population parameter, whereas confidence limits are the upper and lower boundaries of a confidence interval given within a specified level of confidence. So for example, a researcher reports from a sample of 35 individuals that 34% of Americans, plus or minus 3%, believe in ghosts. The 95% confidence interval is 31% to 37%. If independent samples are taken repeatedly from the same population and a confidence interval calculated for each sample, then a certain percentage of the intervals will include the unknown population parameter. This is what we mean by confidence level. Confidence intervals are usually calculated so that this percentage is 95%. But we can produce confidence intervals for the unknown parameter using any level of confidence, 90%, 99%, 99.9%, whichever we choose. For example, suppose an opinion poll predicted that 38% of Americans believe that professional athletes are good role models for children. The pollster might attach a 95% confidence level to the interval 38% plus or minus 4%. That is, they think it's very likely that if asked, between 34% and 42% of the whole US population would consider athletes as good role models. The width of the confidence interval gives us some idea about how uncertain we are regarding the unknown parameter. A very wide interval may indicate that more data should be collected before anything very definite can be said about the parameter. Confidence intervals are more informative than the simple results of hypothesis tests, since they provide a range of plausible values for the unknown parameter. confidence intervals get larger or wider the higher the level of confidence that's desired. On the other hand, they get smaller or narrower the larger the sample size. When we use estimation to find the confidence interval, we can also refer to the precision of the interval. Precision, or reproducibility or repeatability, is the degree to which repeated measures under unchanged conditions result in the same estimate. In other words, how free the estimate is from random variation. The wider the confidence interval, the less precise the estimate. High variability means a large standard error, and therefore an imprecise estimate of the true population mean. Precision should be distinguished from accuracy. Accuracy is the degree of closeness of an estimate to the population's true value. In other words, how free the estimate is from systematic error or bias. An estimate can be accurate but not precise. It can be precise but not accurate. It can be neither, or it can be both. The ideal situation is to have an estimate that has no systematic error or significant random variation, and therefore is both accurate and precise. The width of the confidence interval decreases in proportion to the square root of the sample size. So to double the precision of an estimate, sample size must be multiplied by 4. To triple precision, it must be multiplied by 9. And to quadruple precision, sample size must be multiplied by 16. Increasing the precision of research therefore requires disproportionate increases in sample size. Thus, very precise research is expensive and time-consuming. Averages and relationships and trends and graphs are not always what they seem. There may be more in them than meets the eye, and there may be a good deal less. The secret language of statistics, so appealing in a fact-minded culture, is employed to sensationalize, inflate, confuse, and oversimplify. Statistical methods and statistical terms are necessary in reporting the mass data of social and economic trends, business conditions, opinion polls, the census. But without writers who use the words with honesty and understanding, and readers who know what they mean, the result can often be semantic nonsense. For example, Table 10.1 displays the gross domestic product of the United States of America in billions of dollars, from the first quarter of 2011 to the first quarter of 2013. The GDP data can be represented visually. Figure 10.1 is fairly clear. It shows the growth in GDP between the first quarters of 2011 and 2013. The whole graph is in proportion, and there's a zero line at the bottom for comparison. The roughly 7.5% increase in GDP actually looks like 7.5%, an upward trend that is substantial but perhaps not overwhelming. But the graph can be simplified or truncated by chopping off the bottom. The data in figure 10.2 are the same, and so is the curve. Nothing has been falsified, except the impression that it gives. An undiscerning viewer sees a national income line that has climbed halfway up the paper in just over 2 years. A small rise has become visually a bigger one. Why stop with truncation? We can make the 7.5% look much livelier by simply changing the proportion between the x and y axes. Rather than a subtle increase, the visual impact of figure 10.3 is of something much more impressive. Yet the data used are still exactly the same. The visual representation of exactly the same numbers can be manipulated to give the impression that GDP has soared impressively in just over 2 years, or that GDP has remained relatively stable in just over 2 years. Like good writing, good graphical displays of data communicate ideas with clarity, precision and efficiency, whereas bad graphical displays distort or obscure the data, making it harder to understand or compare, or otherwise thwarting the communicative effect which the graph should convey. The essence of a graph is the clear communication of quantitative information. There are 6 aspects that determine the effectiveness of a visual display that portrays data. Apprehension asks, does the graph maximize understanding? Clarity, is it clear what's being communicated? Consistency, are all the graphical elements, like symbols and colours, consistent with their previous use in other graphs? Efficiency, is the graph easy to interpret? Necessity, is the graph actually the most useful way to represent the data? Would a table or simply written text be better? Truthfulness, are all the graphical elements accurately positioned and proportioned? Visual displays that obscure data can sometimes have very serious consequences.
T-minus 21 seconds, and the solid rocket booster engine gimbal now underway. T-minus 15 seconds. And liftoff of the 25th Space Shuttle mission, and it has cleared the tower.
Now controlling. Roll Challenger. Good roll program confirmed. Challenger now heading down range. Engines beginning throttling down now at 94%. Normal throttles for most of the flight, 104%. We'll throttle down to 65% shortly. Engines at 65%, 3 engines running normally, 3 good fuel cells, 3 good APUs. Velocity 2,257 feet per second. Altitude 4.3 nautical miles, downrange distance 3 nautical miles.
So the 25th Space Shuttle mission is now on the way after more delays than NASA cares to count. This morning it looked as though they were not going to be able to get off.
1 minute 15 seconds. Velocity 2,900 feet per second. Altitude 9 nautical miles. Downrange distance 7 nautical miles.
It was so cold on the morning of January 28, 1986, that icicles were hanging off the scaffolding surrounding the Space Shuttle Challenger. The night before, Morton Thiokol engineers and NASA officials had debated the data concerning the effect of cold temperatures on the giant rubber-like O-rings that seal the separate sections of the rocket boosters. The engineers had even sent NASA officials 13 tables and graphs that documented increasing damage to the O-rings in colder weather, trying to make a case to delay the launch. These 2 graphs contain the information that could have helped NASA delay the Challenger launch, but it was obscured in a few different ways. The key contains irrelevant symbols, and the rocket images distract the viewer from vital information. Vital information has been obscured here in a few different ways. First, the viewer's attention is not directed to the critical variables of interest, temperature and damage to the O-rings. Instead, attention is directed to all those cute little rockets, and only tangentially to the indicators of damage that appear to be randomly scattered among them. Second, the numbers revealing temperature have been turned sideways because the rockets are tall and narrow. Third, the other vital variable, indicating type of damage to the O-ring, was coded with arbitrary symbols, dots, diagonal bars and vertical stripes, rather than something intuitive, such as progressively darker marks, indicating progressively more damage. Tragically, the misleading tables and graphs were not persuasive, and NASA decided to go ahead with the shuttle launch. During the launch, a tiny gap in one of the Challenger's O-rings started leaking. Later, cameras revealed that puffs of black smoke were visible on the launch pad. That O-ring leak grew into a flame, and then, 73 seconds after launch, the billion-dollar Challenger exploded as it tried to leave Earth's atmosphere, killing all 7 of its astronauts. In retrospect, the Challenger disaster could have been prevented by a graph, such as the one shown in Figure 10.5, that clearly described the systematic relation between two variables, temperature and damage to the O-ring material. Unfortunately, the graphs presented to NASA both before the Challenger exploded and during the investigation that followed were not created in such a way that clearly demonstrated the relation between temperature and O-ring damage. The Morton Thiokol engineers who created the graphs didn't need fancy graphs, they needed clearer graphs. The data represented in Figure 10.5 show a strong correlation that indicates a relationship between low temperature at time of launch and substantial O-ring damage. One of the worst graphs ever created provides an opportunity to learn how to create, read, and interpret graphic information. This graph from the Ithaca Times seems to tell a story of increasing cost and decreasing quality. The line representing tuition goes up, and the line representing Cornell University's ranking goes down. But let's examine the variety of lies in this graph. Also, notice that the graph superimposes statistical information on a picture of Cornell University's campus, so the graph's underlying message gains credibility by being associated with this Ivy League institution. The graph appears to answer the question in the headline: why does college have to cost so much? That rising line represents rising tuition costs, as measured by the share of a student family's median income over 35 years. Now look for the timeline that corresponds to the plummeting lower line. The apparently falling line represents the ranking of Cornell University over only 11 years, but the graph does not clearly convey this critical information. The absence of critical information is a red flag. So lie number 1. The graph treats unequal scales as if they were equal. This lie uses identical distances, almost the width of the magazine cover, to represent very different time frames, 11 years versus 35 years. Lie number 2. The graph unites incompatible measures. This lie compares an ordinal measure, university rank, to a scale measure, tuition as a proportion of income. The two ways of measuring a variable are incompatible, yet they're treated as if they were the same. This lie also helps us set up and anticipate the next lie. Lie number 3. The graph uses misleading starting points. This lie arbitrarily begins the line representing quality of education, Cornell's rank compared to other institutions, lower than the line representing tuition costs as a proportion of income, suggesting that an institution already failing to deliver what students are paying for has, over the last 11 years, or perhaps 35 years, become dramatically worse. There's no reason except deception to start one line higher or lower than the other. The scales are not comparable and should not even be placed on the same graph. Lie number 4. The graph reverses the implied meaning of up and down. Cornell University's ranking did indeed change over this 11-year period. It improved from 15th place nationally to 6th place. Cornell's ranking didn't get worse, it got better. Why then does the line representing Cornell's ranking go down? This astonishing graphic lie reversed the direction of the numbers. In the business of rankings, a low number is good, but the graph maker made sure that the positive information about Cornell was portrayed by a line going down. If this graph were true to its data, the line representing quality of education would be rising rather impressively from 15th place to 6th place. Yet this line portrays Cornell's quality of education as falling dramatically. Taken at face value, the graph tells a negative story that might sell more newspapers. The most likely reason this misleading graph was created. A graph has a certain scientific aura, which makes us want to believe it. This makes us vulnerable to graphs that are actually misleading. Here are some of the most common ways to mislead viewers with statistical and graphic tricks. Number 1. The false face validity lie. Face validity refers to whether the method used to collect data seems on the face of it to represent what it says it represents. False face validity occurs when the method seems to represent what it says, but when we dig a little deeper, it doesn't. For example, a variable might be labelled aggression, even though what is actually being measured is how many times people shout at each other. Some fairly happy families shout almost all the time, and many quiet families exchange polite comments with lethal intentions. Number 2. The biased scale lie. A biased scale slants information in a particular way. For example, New York Magazine's restaurant reviewers use a scale of 0 to 5 stars. 5 stars indicate a restaurant's food, service, and ambience are ethereal, almost perfect. 4 stars mean exceptional, consistently elite. 3 means generally excellent. 2 means very good. And 1 means good. So what does 0 mean? Bad? Actually, no. The magazine's restaurant reviewers say 0 stars in a review doesn't necessarily mean a restaurant is bad. It means our critics don't recommend you go out of your way to eat there. Restaurant critics using this rating scale are likely to give more positive ratings because they don't actually have any negative choices to circle when they're at the restaurant. The scale is biased. It's pulling for a certain response. Number 3. The sneaky sample lie. A sneaky sample occurs when the people who participate in a study are pre-selected so that the data turn out in a particular way. For example, some students like to check out websites that rate professors, but the students most likely to participate in those rating sites are those who strongly dislike or strongly approve of a particular professor. It's not a representative sample of all students. Number 4. The interpolation lie. Interpolation occurs when we state that some value between the data points necessarily lies in a straight line between those data points. For example, in a 2007 report on national crime levels, Statistics Canada reported one of the lowest rates of property crime since the 1970s. Without the full set of data, however, it would be easy to assume that a gradual and steady decline in crime levels had occurred over 30 years. Actually, in between these two time points, the crime levels had experienced substantial fluctuations. To spot the interpolation lie, check to be sure that a reasonable number of in-between data points have been reported. Number 5. The extrapolation lie. This lie assumes knowledge of information outside the study. Extrapolation goes beyond the data by assuming a pattern will continue indefinitely. For example, CB or citizens band radios, a once popular communication device now used mostly by long-distance truckers, have long since been replaced by mobile phones. It's likely that most of today's students have never seen one. I've never seen one. Yet in 1976, the Complete CB Handbook declared that the popularity of CB radios would continue to increase to the point that CB instruction would become part of the elementary school curriculum. What happened? The CB radio book didn't take into account the invention of cell phones. So don't assume a pattern in the data will continue. Number 6. The inaccurate values lie. This lie can be subtly effective. Sometimes it involves telling the truth in one part of the data, but visually distorting it in another place. This figure from the New York Times purports to show the mandated fuel economy standards set by the US Department of Transportation. The standard required an increase in mileage from 18 miles per gallon to 27.5. That's an increase of 53%. But the magnitude of increase shown in the graph is actually 783%. Number 7. The outright lie. There are many examples of people making up data to lend an air of legitimacy to an otherwise weak argument. For example, Mitch Snyder, an advocate for the homeless, repeatedly cited a statistic in the early 1980s that there were 3 million homeless Americans, a number that would have meant that actually 1 in 75 Americans were homeless. Snyder eventually admitted that he had lied because he had been pushed by reporters to provide a specific number. During the Gulf War, Patriot missiles shot down 4 Iraqi Scud missiles, far fewer than the 41 successes in 42 engagements claimed at the war's end by the Defense Department. That meant that Iraqi missiles were intercepted only 9% of the time. John Conyers, a Democratic congressman from Michigan, said, "We have watched the claims for this missile drop from 100% during the war to 96% in official statements to Congress, to 80%, 70%, 52%, 26%, and now we're under 10% and dropping. The public and Congress have been misled." In 2011, several British news sources reported on the apparent widespread failure of Implanon, a contraceptive implant. The BBC said that nearly 600 women had become pregnant despite using this popular contraceptive implant. They went on to say, "There have also been more than 1,600 reports of adverse reactions to the Implanon device, which is designed to prevent pregnancy for 3 years. The National Health Service has been forced to pay compensation to several women because of the failures. 1.4 million women have used Implanon, according to the Department of Health. The implant maker, MSD, said no contraceptive was 100% effective. It added that unwanted pregnancies may occur if the implant was not correctly inserted, and said it had a failure rate of less than 1% if inserted correctly." You can read the whole of the short article for yourself here. Was this story using statistics fairly, or were readers being misled? 600 unplanned pregnancies would be shocking if it happened over a relatively short period of time. But the 600 device failures occurred over 10 years, between 1999 and 2009, so really it was only 60 per year. 1.4 million devices were implanted, and they each lasted for 3 years, so the failure rate is actually 1.4 out of 10,000, or 0.014%, which actually backs up what the device makers said. The BBC, Daily Express, Daily Mail and the other British news sources were using statistics to mislead and sensationalise a story that was otherwise fairly trivial. The goal of this module is to introduce you to the biostatistical concepts that underpin and are used in medical decision making. Clinical medicine often involves various kinds of tests or numeric data. The data are used for diagnosis, prognosis, and choosing and evaluating treatments. It's important to minimize errors in the evaluation and interpretation of the data so that they can be used to guide rather than mislead the individuals who provide the care. So what does that look like? How do data inform a diagnosis and guide the decisions being made by the healthcare provider? Let's consider an example involving whether or not to prescribe antibiotics for a patient who presents to you with a sore throat.
I have a terribly sore throat, which is getting worse. I've heard that strep throat is going about.
Have you been near anyone who has strep throat?
Yes. So, can I have antibiotics?
What do you do? Yay or nay? Well, there are advantages and disadvantages of prescribing antibiotics in this situation. If the patient does have strep throat, giving antibiotics will provide a quicker reduction of symptoms, shorten the duration of illness, and quickly and efficiently eliminate the possibility of spreading the infection to others. Now, although rare, serious consequences of streptococcal infections do occur. Rheumatic fever is associated with heart, joint and nervous system damage, and serious kidney disease may also be a consequence of strep infection. Both are preventable by rapid antibiotic treatment. However, antibiotics don't treat sore throats caused by allergies or by viruses such as the common cold, and in fact 70 to 85% of sore throats are caused by viruses. So, if your patient's sore throat is due to a viral infection, prescribing antibiotics will not help. Another substantial negative is that inappropriate use of antibiotics can lead to bacterial superbugs that are resistant to standard antimicrobial drugs. So is this sore throat due to a bacterial or viral infection? Or is it something else entirely? You conduct a focused history and physical exam of the patient to gather more data in order to further explore the suspicion of strep throat and guide your decision. The patient does have a really sore throat and has said they've been exposed to Streptococcus pyogenes, the bacterium that causes strep throat, but they have no fever, tonsillar exudate, or cervical lymphadenopathy. In other words, a sore throat with a fever over 38.5 Celsius or 101 Fahrenheit, together with inflamed and pussy tonsils and swollen lymph nodes of the neck, are common features of a strep infection, but they aren't present here. The absence of these clinical signs reduces the probability that the patient has strep throat, but doesn't eliminate it altogether. So, given that no single characteristic element of either your patient's history or physical examination discriminates between strep throat and non-strep throat, it's imperative to move on to laboratory evaluation, since, as we've said before, strep throat really should be treated with antibiotics, while relief of symptoms remains the mainstay of treatment for viral sore throats. There are two diagnostic tests that can be used to determine whether or not strep bacteria are present in the patient's throat. The traditional test has been a throat culture. Its major drawback is that the results take 2 to 3 days. This amount of time is necessary to allow enough streptococcal bacteria to grow in vitro to enable accurate identification. By comparison, the rapid strep test is much quicker. It's a relatively simple and inexpensive test for group A streptococcus and can produce results within minutes. A positive or negative result from a rapid strep test should help guide your decision regarding the patient's request for antibiotics.
So, can I have antibiotics?
What about situations where there are multiple test options available, which is the case for breast cancer, and you want to identify good options for screening versus diagnosis? Screening is the detection of disease at its earliest stages among asymptomatic persons in the general population, whereas diagnostic tests are used to confirm a diagnosis among persons with existing signs or symptoms of illness. We want to obtain objective evidence of the presence or absence of a particular condition to guide our medical decision making. So how can data and biostatistics help us evaluate which of these 6 tests would be more appropriate for screening rather than diagnosis? The breast self-exam, the clinical breast exam, mammography, ultrasound, and MRI or fine needle aspiration. Looking at them, you probably have some sort of impression or gut feeling about which would make better screening tests. But are you confident in your evaluation? Would objective scientific data support your opinion, or perhaps suggest that you'd been misled? Before we get to that, we should consider the broader question of which biostatistical concepts can help us decide if a test is going to be appropriate or even useful. Regardless of whether the test is a physical examination, a chest x-ray, an EKG, or a blood or urine assay, the same issue arises. How good is the test in separating populations of people with and without the disease in question? Two important biostatistical concepts that can be used to evaluate scientific tests or measurements or procedures are validity and reliability, which are also known as accuracy and precision. Validity is the degree to which the data measure what they were intended to measure. That is, the degree to which the results of a measurement correspond to the true state of the phenomenon being measured. Another word for validity is accuracy, two terms for the same thing. Let's consider a wristwatch as an example. So a watch is a technological instrument that is intended to measure time. A watch that tells the right time has high validity. It is accurate. A watch that runs correctly but is always 93 minutes fast is not valid. It's not accurately measuring the true state of the phenomenon of interest. Whereas a broken 12-hour watch will be valid twice a day. What about these other examples? How valid would you consider an oral thermometer to be for measuring body temperature versus a hypercolour t-shirt from the early 90s?
Guess what? Hypercolor clothing changes color with heat. Like this. Get it?
Which one is better at measuring the phenomenon it purports to measure? Or the arthritis functional scale to measure a patient's level of activity? Or something you'll be facing, or something you'll all be facing in a couple of years, the Step 1 exam's measurement of your medical knowledge. Quantifying hand strength is not recognised as a valid means of measuring intelligence. So remember, if a test is high validity, it measures the thing it's intended to measure. There are lots of nuanced subsets of validity: construct validity, criterion validity, face validity, predictive validity, that you'll no doubt encounter as your education and careers progress. But for now, there are just two that we want you to be clear on. The first is internal validity. In research, internal validity is the extent to which you're able to say that no other variables except the one you're studying cause the result. In other words, the test has no confounding factors. Here the word confounding means to mix up with something else, so that the individual elements become difficult to distinguish. So if you're trying to perceive a relationship between two things, two variables, your estimate of the relationship between them ends up being incorrect, because you fail to account for the presence of other confounding factors. You're left with an evaluation of the original two things that is spurious. In other words, it's not what it purports to be. It's apparently, but not actually valid. For example, reading comprehension is a confounding factor for IQ tests. Sean works for a large corporation, and they've hired someone to figure out if more money will mean more productivity for their workforce. In other words, they want to know if they pay Sean a higher salary, will he work more? At first glance, the answer appears to be yes. After all, the people who get paid the most at the company tend to be the ones that come in early and stay late. They are the hardest working people in the company, so it stands to reason that the more a person gets paid, the harder they will work. Right? Well, maybe, but it's actually a bit more complicated than that. Maybe those people get paid the most because they're already hard workers. Maybe they're motivated to work hard because they really like what they do, and the pay is incidental. Maybe they're hyper-competitive and don't want to be the first to leave the office. How do we know what the cause of their hard work is? If we're studying the independent variable of pay and the dependent variable of hard work, we want to be able to say that no other reason, no other confounding factors, cause the hard work. Not personality, not motivation, not competition. We want to say that pay, and pay alone, makes people like Sean work harder. Suppose an experimenter observes an increase in the probability of salivating after presenting the smell of delicious food, leading her to conclude that the food smell produces salivation. For this conclusion to be internally valid, the experiment must be designed so that conditions other than the food smell are ruled out as potential causes for the behaviour change. For example, if the sight of the food is presented along with its smell, then an alternative explanation could be that the sight of the delicious food, and not its smell, is responsible for the increased probability of salivating. External validity is related to generalizing. That's the major thing you need to keep in mind. External validity refers to the approximate truth of conclusions that involve generalizations. Put in more pedestrian terms, external validity is the degree to which the conclusions in your study would hold for the population that the sample was drawn from, and for other persons in other places and at other times. A threat to external validity is an explanation of how you might be wrong in making a generalization. For instance, you conclude that the results of your study, which was done in a specific place with certain types of people and at a specific time, can be generalized to another context, another place with slightly different people at a slightly different time. There are three major threats to external validity because there are three ways you could be wrong: people, places, or times. Your critics could come along and argue that the results of your study are due to the unusual type of people who were in the study, or they could argue that it might only work because of the unusual place you did the study in. Perhaps you did your educational study in a college town with lots of high-achieving, educationally oriented kids. Or they might suggest that you did your study at a peculiar time. For instance, if you did your smoking cessation study the week after the Surgeon General issues the well-publicised results of the latest smoking and cancer studies, you might get different results than if you'd done it the week before. Sarah is a psychologist who teaches and does research at an expensive private college. She's interested in studying whether offering specific praise after a task will boost people's self-esteem. If her hypothesis is correct, then giving someone a specific compliment on a job well done after a task will make them feel better about themselves. And if she can show that specific praise post-task boosts self-esteem, then managers at companies everywhere will be able to boost their employees' self-esteem by offering them specific praise. But here's a problem. The volunteers that Sarah gets for her study are all college students. Most of them are white, and most of them are from privileged backgrounds. Sarah worries that her results might not be applicable to people who are not in their late teens or early 20s, white, and relatively rich. Here's an example to think about yourselves. So say you're doing a randomised clinical trial of vitamin D supplements. What might be some threats to external validity? Let's consider another aspect of assessing tests or measurements or procedures, the question of whether a test is reliable or repeatable. Can the results obtained be replicated if the test is repeated? If the test results can't be reproduced, then the value and usefulness of the test are minimal. Reliability is the extent to which repeated measurements of a stable phenomenon get similar results. Reproducibility and precision are other words for this property. Let's think through some examples. When people take a vocabulary test twice, their scores on the two occasions should be very similar. If so, the test can then be described as reliable. To be reliable, an assessment measuring self-esteem should give the same result if given twice to the same person within a short period of time. IQ tests should not give different results over time, as intelligence is assumed to be a stable characteristic. The difference between accurate and precise, or valid and reliable, is commonly visualized using a dartboard or an archer's target. A method is precise when repeated measurements give very similar results. But note that a set of measurements could be quite precise without being accurate if the methodology is not working, or an instrument is not calibrated properly. This is the case for figure A. The blue dots are tightly clustered together, showing a high degree of precision. That is, repeated attempts produce similar results, but they have low accuracy because they're far from the bullseye. Figures B through D show the other three possibilities: that a measurement or a method to obtain measurements can be neither accurate nor precise, accurate but not precise, or accurate and precise. Here is another way to visualize these possibilities. The coloured area under the curve represents a series of repeated measurements. It's not a perfect straight line like this because there's always some variability to be expected. Variability in measurements can either be random or systematic. Validity/accuracy quantifies the degree to which measurements are free from systematic error, whereas reliability/precision quantifies the degree to which measurements are free from random error. So in figure A, the area under the curve is leptokurtic in shape, demonstrating a high amount of precision or reliability. In other words, the degree of random error is small. On average, the mean of these measurements, y, lines up faithfully with the true value, x. This means these measurements are free from systematic error or bias, such as a miscalibration. They are valid and accurate. On average, they are measuring the true state of the phenomenon of interest. In figure B, the series of measurements show a similar precision and reliability, but they're inaccurate. Some systematic error is pulling the mean y away from the true value x. In this situation, the validity is low. A laboratory balance, for example, may weigh very precisely, with very little variation between repeated weighings of the same object. But if it's not been zeroed properly, all its measurements may also be too high, causing all its results to be biased, and hence inaccurate and invalid. Figure C is similar to figure A, other than the fact that the area under the curve is more spread out, indicating a larger degree of random error and therefore reduced precision. And figure D is both lacking in precision and accuracy. Confidence intervals quantify precision. We looked at this back in module number 9. The width of the confidence interval reflects the precision. The wider the confidence interval, the less precise the estimate. Almost all results, proportions, relative risks, odds ratios, means, differences between means, slopes, rate constants, and so on, can and should be reported with a confidence interval. Whenever you see a value computed from data, ask for its confidence interval. The reliability of a test influences the extent to which a single measurement may be taken as a definitive guide for making a diagnosis. In the case of a highly reliable test, such as a patient's weight, one measurement alone may be sufficient to allow a physician to make a diagnosis, such as obesity. But if the test is unreliable in any way, this may not be possible. The inherent instability of many biomedical variables, such as blood pressure or blood glucose, often makes it necessary to repeat a measurement at different times, and to use the mean of these results to obtain a reliable measurement and make a confident diagnosis. A test's accuracy is considered in relation to some way of knowing whether the disease is truly present or not, a sounder indication of the truth, often referred to as the gold standard. The gold standard is a procedure that is generally accepted as being able to identify the true condition, disease or disease-free, of a patient. Because it's almost always more costly, more dangerous, or both, to use more accurate ways of establishing the truth, clinicians and patients prefer simpler tests to the rigorous gold standard, at least initially. For example, chest x-rays and sputum smears are used to determine the cause of pneumonia, rather than bronchoscopy and lung biopsy for examination of the diseased lung tissue. EKGs and blood tests are used first to evaluate the possibility of acute myocardial infarction rather than catheterization or imaging procedures. In practice, neither validity nor reliability are usually in question in routine medical lab testing. Standard laboratory tests have been carefully validated, and quality control procedures in the lab ensure reliability. Even while using a valid and accurate test, you will see a range of values across different people. Clearly, not all healthy people will get the exact same test result. There will be a range of scores. This range is called the normal range or reference range, and the limits of this range are the reference values, also called the upper and lower limits of normal. The physician will use these to interpret the values obtained from the patient. The range between the reference values is sometimes called the reference interval. The normal range of a biomedical variable is often arbitrarily defined as the middle 95% of the normal distribution. In other words, the population mean plus or minus 2 standard deviations. Now, there's nothing inherently pathologic about the 5% of individuals outside this quote-unquote normal range. Typically, there are some healthy people who have, again quote-unquote, abnormally high or abnormally low values. And it's also worth remembering that many biological variables turn out to be skewed rather than normally distributed in the population. For example, this figure is from a study concerning the hematological parameters of newborn umbilical cord blood. Umbilical cord blood is obtained when a mother donates her infant's umbilical cord and placenta after birth. It's a major source of hematopoietic stem cells. They can be used in a transplantation procedure to re-establish hematopoietic function in patients whose bone marrow or immune system is damaged or defective. On the right you can see the normal reference range values provided. Let's pause for a minute and see where we are thus far. The core intent of this module is the idea that clinical medicine often involves various kinds of tests or numeric data. The data are used for diagnosis, prognosis, and choosing and evaluating treatments. We've said that it's important to minimize errors in the evaluation and interpretation of the data so that they can be used to guide rather than mislead the individuals who provide the care, like when to give or not to give antibiotics for a sore throat. We've covered the fundamental biostatistical concepts of validity, reliability, the gold standard, and reference ranges, which are essential to the task of deciding how good tests are at separating populations of people with and without the disease in question. In a perfect world, medical tests would always be correct. For example, women could undergo a diagnostic test that would unequivocally determine whether breast cancer was present, and the test would have no side effects. A positive test result would indicate that cancer was present, and a negative test result would indicate that cancer was absent. In reality, however, every test is fallible. Clinical tests can report 2 possible results, normal or abnormal. There are 2 ways such a test can go wrong, false positive or false negative. Ideally, we would like all of the tested subjects to fall into one of 2 categories. People with the disease who are correctly called positive by the test, i.e. true positives, and people without the disease who are correctly called negative by the test, true negatives. Unfortunately, such is rarely, if ever, the case. Some people who do not have the disease are erroneously called positive by the test, these are false positives, and some people with the disease are erroneously called negative, these are false negatives. Why are these issues important? When we conduct a screening program, we often have a large group of people who screen positive, including both people who really have the disease, the true positives, and people who do not have the disease, the false positives. The issue of false positives is important because all people who screen positive are brought back for more sophisticated and more expensive tests. Of the several problems that result, the first is a burden on the healthcare system, and another is the anxiety and worry induced in those who have been told that they've tested positive. So why is the problem of false negatives important? Well, if a person has the disease but is erroneously informed that the test result is negative, and if the disease is a serious one for which effective intervention is available, the problem is pretty critical. For example, if the disease is a type of cancer that is curable only in its early stages, a false negative result could represent a virtual death sentence. Thus, the importance of false negative results depends on the nature and severity of the disease being screened for, the effectiveness of available intervention measures, and whether the effectiveness is greater if the intervention is administered early in the natural history of the disease. A false positive is an example of a type 1 error. The test, quote-unquote, found something that wasn't really there. A false negative is an example of a type 2 error. The test failed to find something that really was there. A simple mnemonic to help you remember this is that the word positive has one E in it, which corresponds to a type 1 error, whereas the word negative has two E's in it, corresponding to a type 2 error. Can we determine the false positive and false negative rates for a given test? To give us some sense of how likely it is that we might be misled, given that no test is infallible. Is it something that we can objectively quantify? The answer to that is yes. Remember that if a test is not measuring the true state of the phenomenon of interest, then it has validity/accuracy issues. The accuracy of a diagnostic test is quantified by its sensitivity and specificity. Sensitivity and specificity are both measures of a test's validity, its ability to correctly detect people with or without the disease in question. Sensitivity is the fraction of all those with the disease who get a positive test result. Sensitivity measures how well the test identifies those with the disease. If a test is high sensitivity, it will pick up nearly everyone with the disease. Specificity is the fraction of those without the disease who get a negative test result. Specificity measures how well the test identifies those who don't have the disease. If a test has very high specificity, it won't mistakenly give a positive result to many people without the disease. Let me try and illustrate these concepts visually. Hue is the property of colours by which they're seen as ranging from red through orange, yellow, green, blue, indigo and violet as determined by the dominant wavelength of light. One of these 81 squares has a different hue from its neighbours. Can you tell which one it is? Test sensitivity in this colourful analogy is how well your eyes identify the square with the abnormal hue. If you fail to identify the abnormal square, you will have generated a false negative. Let's look at a bunch of these and I'll make it progressively easier so you don't think I'm pulling your leg. So sensitivity is the fraction of all those with the disease who get a positive test result. Sensitivity measures how well the test identifies those with the disease. If a test is high sensitivity, it will pick up nearly everyone with the disease. The lower a test sensitivity, the greater is its chance of generating false negatives. The true positive rate is equal to sensitivity, whereas the false negative rate is equal to 1 minus the sensitivity. Now let's try and illustrate specificity. Specificity measures how well the test identifies those who don't have the disease. It's a measure of the true negative rate. Our cartoon guy is super freaked out about Lyme disease. Let's have him test all the animals he can find. He's trying to identify animals without Borrelia spirochetes, which in this silly example are non-squirrels. So we'll start off with him using a test with low specificity, In other words, it will fail to correctly identify non-squirrels. So in this low specificity example, the test struggled to correctly identify non-squirrels. It produced positive results for all the mammals, not just the pesky Borrelia-ridden squirrels. The lower a test specificity, the greater is its chance of generating false positives. For the sake of completeness, let's have him modify his test machine to give it high specificity and try again. This time, the high specificity test should have a high true negative rate. In other words, it should no longer identify non-squirrels as squirrels. The true negative rate is equal to specificity, whereas the false positive rate is equal to 1 minus the specificity. Now let's get to the actual calculation part of sensitivity and specificity. It's common to use a 2x2 table for these calculations. In other words, a 2x2 grid of 4 boxes. The horizontal rows indicate the test results. The top row is for the number of patients that receive a positive test result, and the bottom row for those who receive a negative test result. The vertical columns indicate the numbers for those who truly do or do not have the disease of interest. The left-hand column for those in which the disease is genuinely present, and the right-hand column for those in which the disease is genuinely absent. Sensitivity is the number of people with a positive test who truly have the disease, divided by the total number of people tested who truly have the disease, or A divided by A plus C. Specificity is the number of people with a negative test who truly don't have the disease, divided by the total number of people tested who truly don't have the disease, or B divided by B plus D. Let's go through a couple of examples. Let's consider the sensitivity and specificity of mammography and fine needle aspiration. These are the results from a study published in 1988. 63,459 women in total participated in the study. 1,117 had a positive mammogram, while 62,342 had a negative result. Of those who tested positive, 132 had cancer, these were the true positives, while 985 were false positives. In other words, women who received a misleading positive mammogram test result, but actually were cancer-free. Of those who tested negative, 47 had cancer, these were false negative results. Women in whom the mammogram indicated no disease when in fact they did have cancer, while 62,295 were true negatives, women who tested negative and were truly cancer-free. We can also calculate column totals of 179 women who had cancer and 63,280 women who had no cancer. Sensitivity is A divided by A plus C, which is 132 divided by 179, which equals 0.737, or 73.7%. Therefore, in this study, mammography has a true positive rate of 73.7% and a false negative rate of 26.3%. Specificity is D divided by B plus D, which is 62,295 divided by 63,280, which equals 0.984, or 98.4%. Therefore, in this study, mammography has a true negative rate of 98.4% and a false positive rate of 1.6%. Let's look at some numbers for fine needle aspiration. In this study, 114 women with normal physical examinations and abnormal mammograms received a fine needle aspiration, followed by a surgical excisional biopsy, which was the gold standard. These are the results from a study also published in 1988. 114 women in total participated in this study. 22 had a positive fine needle aspiration test, while 92 had a negative result. Of those who tested positive, 14 had cancer, true positives, while 8 were false positives, in other words, women who received a misleading positive fine needle aspiration result but actually were cancer-free. Of those who tested negative, one had cancer. This was a false negative result. A woman in whom the fine needle aspiration test indicated no disease, when in fact she did have cancer, while 91 were true negatives, women who tested negative and were truly cancer-free. We can also calculate column totals of 15 women who had cancer and 99 women who had no cancer. Sensitivity is A divided by A plus C, which is 14 divided by 15, which equals 0.933 or 93.3%. Therefore, in this study, fine needle aspiration had a true positive rate of 93.3% and a false negative rate of 6.7%. Specificity is D divided by B plus D, which is 91 divided by 99, which equals 0.919 or 91.9%. Therefore, in this study, fine needle aspiration has a true negative rate of 91.9% and a false positive rate of 8.1%. It's also possible to assign a numerical value to the accuracy of the test. This is the total number of tested people whose disease status was correctly identified, or A plus D divided by A plus B plus C plus D. This isn't commonly tested in step 1 compared to sensitivity and specificity, which definitely are. Tests with great sensitivity are useful clinically to rule out the presence of a disease. That is, a negative test result would virtually exclude the possibility that the patient has the disease of interest. A very sensitive test should be used when a false negative would have serious consequences. For example, to screen donated blood for HIV or pap smears for cervical cancer. A common mnemonic is the word snout to remind you that very sensitive tests are used clinically to rule out disease. I prefer to throw in an extra N to make it SNNOUT because it's a negative result of a very sensitive test that is used to rule out a disease. I recommend you use this modified mnemonic. Very specific tests are often used to confirm the presence of a disease. If the test is highly specific, a positive test result would strongly suggest the presence of the disease of interest. A very specific test should be used when the consequences of a false positive are serious. For example, in situations where the diagnosis may lead to the initiation of dangerous, painful, or expensive treatment, such as major surgery or chemotherapy. The common mnemonic for specificity is SPIN, to remind you that very specific tests are used clinically to rule in disease. Again, I prefer to throw in an extra P to make it SPPIN, because it's a positive result of a very specific test that is used to rule in a disease. Like I said before, I suggest you use this version to avoid potential confusion. Another factor that can influence the false positive and false negative rate is the cutoff level chosen for a given test. The cutoff point is the threshold at which a test result is considered to change from negative to positive. As an example, let's say we're measuring serum calcium levels to test for hyperparathyroidism, which is a calcium metabolism disorder. If we test a large number of people from the general population and plot the results, we'll produce a bimodal distribution. There are two peaks. One represents the non-diseased individuals who centre around 10 mg per deciliter, and the other represents those with hyperparathyroidism. Their distribution of serum calcium centres around 12 mg per deciliter. Notice that the two distributions overlap. We can be confident that a person with a calcium level below point A is unlikely to have hyperparathyroidism, while someone with a calcium level above point B is likely to have the calcium metabolism disorder. What about those in between A and B? More specifically, what about the folks with calcium concentrations between 10 and 11 mg per deciliter? Because of the overlap, we need to set some sort of cutoff point at which a test result is considered to change from negative to positive. Let's make it 10.7. This means we're going to choose to interpret a test result of 10.7 or higher as an indication of hyperparathyroidism, while a lower value, less than 10.7, is a negative result, and we will deem the patient disease-free. However, if a person who truly belongs to distribution A has a calcium concentration of 10.8, and is deemed by our cutoff to have the disease, this would be a false positive. This person came from the healthy population, but just happens to have serum calcium levels more than 2 standard deviations away from the average person in population A. The position of the cutoff value relative to the overlapping region influences the number of false positive or false negative test results generated when the test is used in the general population. On one hand, if the threshold is set high, some individuals with low test values or mild forms of the disease will be missed. The sensitivity will be low, but the specificity will be high. Few of the positive results will be false positives, but many of the negative tests will be false negatives. On the other hand, if the threshold is set too low, most individuals with the disease will be detected, but the test will also mistakenly diagnose many normal individuals as abnormal. The sensitivity will be high, but the specificity will be low. Few of the negative results will be false negatives, but many of the positive results will be false positives. To help determine an appropriate cutoff point for a positive test result, the relationship between sensitivity and specificity can be clarified by plotting a test's true positive rate, in other words its sensitivity, against its false positive rate, or 1 minus the specificity, for different cutoff points. Such a plot is a receiver operating characteristic curve. Why the odd name? ROC curves were developed during World War II within the context of determining whether a blip on a radar screen represented a ship or extraneous noise. The radar receiver operators used this method to set the threshold for military action. Each point on the ROC curve represents a sensitivity and specificity pair, corresponding to a particular cutoff point or decision threshold. Let me see that again. Each point on the ROC curve represents a sensitivity and specificity pair, corresponding to a particular cutoff point or decision threshold. It's a common mistake when you're seeing one of these curves for the first time to think we're plotting different test results for a bunch of patients. We're not. So in this example, we're plotting the different blood pressure values that we could choose to be the cutoff threshold in terms of sensitivity and false positive rate. So again, to stick with this example, a cutoff threshold of 160 millimeters of mercury for high blood pressure would result in the test having a sensitivity of 40% and a false positive error rate of approximately 5%. If instead we lowered the cutoff threshold value that separates normal from abnormal to 150 millimeters of mercury, the sensitivity would be roughly 57% and the false positive rate about 10%. The ROC curve shows how severe the trade-off between sensitivity and specificity is for a test, and can be used to help decide where the best cutoff point should be. Generally, the best cutoff point is at or near the shoulder of the ROC curve, unless there are clinical reasons for minimizing either false negatives or false positives. It's also possible to use ROC curves to help you evaluate the quality of multiple tests available for a given disease. So in this diagram we have plotted ROC curves for 4 different tests. A test that discriminates perfectly between the presence and absence of disease would have an ROC curve that passes through the upper left corner. In other words, it would be 100% sensitive and 100% specific. So the closer the curve is to the upper left corner, the higher the overall accuracy of the test. The curve represented by the black circles is the closest to this ideal. A completely random test, for example, tossing a coin to determine if a patient has hyperparathyroidism, would give an ROC curve represented by the white squares. It offers no benefit. The shape of the curve therefore reflects the quality of the test. The better the test, the more the curve moves to the upper left. this can be quantified in terms of the area under the curve. The worst case is 0.5 and the best is 1. A good test is one with a high rate of true positives and a low rate of false negatives over a reasonable range of cutoff values. In other words, it has a high AUC as the curve moves towards the upper left corner. As a rule of thumb, an AUC of 0.5 to 0.6 is almost useless. 0.6 to 0.7 is poor, 0.7 to 0.8 is fair, and 0.8 to 0.9 is very good. The AUC reflects the test's ability to discriminate between those with and without disease. ROC curves can be used for two purposes: to allow different tests and/or different cutoff points to be compared. Let's look at another clinical example. Here are two ROC curves for two emergency diagnostic tests for congestive heart failure. This is a common, costly, and potentially fatal condition that occurs when the heart is unable to pump sufficiently to maintain blood flow to meet the body's needs. BNP is both more sensitive and more specific, with a larger area under the curve of 0.89 than that for ejection fraction, which is an AUC value of 0.78. It's also easier and faster to obtain BNP levels in an emergency setting compared to determining the ejection fraction. When the sensitivity of a test is known, it answers the question: if the patient has the disease, what is the ability of the test to discover this? When the specificity of a test is known, it answers the question: if a patient is free from the disease, what is the ability of the test to discover this? These are the kinds of questions an epidemiologist might ask when screening for a disease. The epidemiologist wants to know, for example, how good a test is at detecting the presence or absence of HIV infection, and what percentage of women with breast cancer will be detected with a mammogram. However, these are not the kinds of questions that the practicing physician or the patient typically asks. When faced with a test result, they want to know how likely it is that the disease really is present or absent. That is, if the test is positive or negative, how likely is it that the patient really has or doesn't have the disease? This is a different question altogether, and answering it requires knowledge of the predictive value of the test. Sensitivity and specificity are descriptors of the accuracy of a test. Two measurements concerning the estimation of the probability of the presence or absence of disease are the positive predictive value and the negative predictive value. Knowing a test's positive predictive value allows us to answer the question: given that the patient's test result is positive, how likely is it that he or she really does have the disease? And knowing a test's negative predictive value allows us to answer the question: given that the test result is negative, how likely is it that the patient really does not have the disease? And once again, this is the kind of information a patient is concerned about. Calculating these values is similar to the calculations used for sensitivity and specificity. The PPV is the number of people with a positive test who truly have the disease, A, divided by the total number of people who tested positive, A plus B. MPV is the number of people with a negative test who truly don't have the disease, D, divided by the total number of people who tested negative, C plus D. Let's calculate the positive and negative predictive values for the mammogram and fine needle aspiration examples from earlier. The positive predictive value is 132 divided by 1117, which equals 0.118 or 11.8%. This means, for this particular study, if a patient has a positive mammogram result, the probability of them truly having breast cancer is only 11.8%. The negative predictive value is 62,295 divided by 63,342, which equals 0.999 or 99.9%. This means, for this particular study, if a patient has a negative mammogram result, the probability of them not having breast cancer is 99.9%. So for this particular study population, mammograms would be very effective screening tests. A physician could be confident that a patient with a negative result is very, very unlikely to have breast cancer. On the other hand, a mammogram would not make a good confirmatory test. If only 11.8% of those who tested positive truly have breast cancer, you would want to do additional testing before initiating treatment in order to distinguish the majority of false positives from the fewer true positives. Let's look at the predictive values for the fine needle aspiration. The positive predictive value is 14 divided by 22, which equals 0.636 or 63.6%. This means, for this particular study, if a patient has a positive fine needle aspiration result, the probability of them truly having breast cancer is 63.6%, close to 2/3 likely. The negative predictive value is 91 divided by 92, which equals 0.989 or 98.9%. This means, for this particular study, if a patient has a negative fine needle aspiration result, the probability of them not having breast cancer is 98.9%. Sensitivity and specificity can be considered inherent characteristics of the test being used and are relatively fixed. On the other hand, the predictive values, the positive predictive value and the negative predictive value of a test, are not a property of the test alone. They are determined by the sensitivity, the specificity, as well as the prevalence of disease in the population being tested. Prevalence is a measure of the commonness or rarity of a disease, and we'll talk more about that in module number 12.
A 51-year-old man presents to you with chest pain that he thinks is indigestion. He was well until 2 weeks ago when he noticed tightness in the center of his chest after a large meal and while walking uphill. The tightness stopped after 2 to 3 minutes of rest. A similar discomfort has occurred several times since then, sometimes during exercise and sometimes at rest. He gave up smoking 1 pack of cigarettes per day 3 years ago and has been told that his blood pressure is a little high. He is otherwise well and takes no medications, but he is worried about his health, particularly about heart disease. He lost his job 6 months ago and has no health insurance. A complete physical examination and resting electrocardiogram are normal except for a blood pressure of 150 over 96 millimeters of mercury. This patient is likely to have many questions. Am I sick? How sure are you? If I am sick, what's causing my illness? How will it affect me? What can be done about it? As the clinician caring for this patient, you have the same kinds of questions, although yours reflect greater understanding of the possibilities. 2 of the questions confronting you include, is the probability of serious, treatable disease high enough to proceed immediately? And how accurate are those diagnostic tests that we used? For example, how accurate will an exercise stress test be in either confirming or ruling out coronary artery disease? Clinicians need answers to these kinds of questions in order to make the best possible medical decisions for their patients. Diagnosis is an imperfect process, resulting in a probability rather than a certainty of being right. The doctor's certainty or uncertainty about a diagnosis has been expressed by using terms such as rule out or possible before a clinical diagnosis. That being the case, clinicians should be familiar with the mathematical relationships between the properties of diagnostic tests and the information they yield in various clinical situations. The goal of this module is to learn the statistical concepts that underpin and are used in medical decision-making. All screening and diagnostic tests have certain amounts of validity and reliability. We will learn what these words mean and how the validity and reliability of a test affect the usefulness of the test. Accurate tests are valid and precise tests are reliable. Validity and reliability are independent of each other. When we ask whether a test is valid, we are asking whether the test assesses what it purports to assess. We want to have confidence that we are measuring what we intend to measure. That's why we want to use valid tests. To test walking speed, you could use a small wearable speedometer, or you could choose to use a bathroom scale. Which of these two test devices has face validity for assessing walking speed? On the face of it, the speedometer is the more valid test. Let's say you have a test for blood glucose and you measure blood glucose in a group of 7-year-olds. You then wait and assess whether these children develop type 2 diabetes as adults. What you want to know is whether your childhood test for blood glucose predicts adult diabetes. If it does, your test has predictive validity. Here's another example of this. Think about the following. Let's say that a researcher knows that one of the symptoms of major depression is psychomotor slowing. Folks move more slowly than they used to. The researcher wants to use a mouse model of depression to test the effects of an experimental new drug. The symptom of depression that the researcher chooses to model with the mice is psychomotor slowing. Unbeknownst to the researcher, the particular mice that have been chosen to serve as the model have nerve damage, which causes them to walk slowly. A test using these mice would not have construct validity for depression because the mice walk slowly for reasons that have nothing to do with the reason that people with depression move slowly. The cause and effect of the construct are not the same as the cause and effect of reality. Here's another example of this. Tests or studies also have particular levels of internal and external validity. A test has internal validity if all potential confounding factors are controlled for. For example, if you want to examine the efficacy of a new pain reliever, you want the group that gets the drug and the control group that gets the placebo to be matched on all other factors such as age, sex, health status, etc. A test has external validity if its results can be generalized. For example, if your test included both men and women, then it can be generalized to the real population, which includes both men and women. If you'd only tested women, then your results could not be generalized to the real population. They would not be external validity. Here's another example of this. A reliable test gives the same or very similar result every time it is used to measure a variable that has not changed. Like validity and reliability, accuracy and precision do not depend on each other. A test can be accurate but not precise. A test can be precise but not accurate. All combinations of precision and accuracy are possible. The dartboards in the next slide illustrate this nicely. As you can see in example A, the dart thrower can be both accurate and precise as in A, accurate only as in B, precise only as in C, or neither accurate nor precise as in D. In this example, accuracy is shown by darts hitting the board with unbiased placement to one location. The test measured what you wanted it to measure. Precision is shown by the darts being tightly clustered. The test measured the same thing repeatedly. It was reliable. In example B, you can see that when there is bias, the errors are not random. They are biased towards a particular part of the board. Another way to think about accuracy and precision is by thinking about what is being shown in these curves. The test is accurate if the true value is at the peak of the curve. The test is precise if the curve is pointy and there is little spread. A test's accuracy is considered in relation to some way of knowing whether the disease is truly present or not. Sound or indication of the truth, often referred to as the gold standard or reference standard or criterion standard. Since there is variability among healthy people, there will be a range of normal values. The values within this normal range are the reference values. These values are set to cover 95% of the healthy population. That leaves 5% of the healthy population outside of the reference range, 2.5 with very low values and 2.5 with very high values. These values are false positives. You may think that a person with values in these ranges is ill, when in fact they are not. False positive and false negatives can both occur because there are a range of values for both the healthy and the diseased populations. You'll see this in the next slide. Decreasing false positives means increasing false negatives. This conundrum requires medical decision making. The physician has to decide when false positives are acceptable, since patients with positive test results will have to undergo further testing. Importantly, the physician also has to decide whether a false negative would be dangerous. Failing to find some diseases when they are really present could be dangerous. Let's move our person around on this figure and make decisions about the health status of the person. Let's have our person with a serum calcium concentration of 9.5 milligrams per deciliter. We could be pretty confident that that person does not have hyperparathyroidism. Now let's have our person with a serum calcium concentration of 10.5 milligrams per deciliter. If the person was really from population A, but we decided that he had hyperparathyroidism, we would be making a false positive. Physicians have to decide when false positives are acceptable, since patients with positive test results will have to undergo further testing and they might be made anxious by an initial positive result. Importantly, physicians also have to decide whether a false negative would be dangerous. Failing to find some types of diseases when they actually exist could be dangerous. In order to make these decisions, it is helpful for physicians to know a couple of important things about the test that was used to obtain the initial result. If you are relying on a test result to make a medical decision, you will want to know two things about the test itself. You'll want to know how sensitive it is. That is the test good at detecting what is really there? And you'll want to know how specific the test is. That is, does the test fail to detect something that is really not there? Knowing how sensitive and specific a test is can help a physician make decisions about the meaning of a positive or a negative test result. Both sensitivity and specificity can be quantified, and this helps us with decision making. There are 4 possibilities after a test has been run. The result could be a true positive, as in A. The person tested positive and the disease is really present. The result could be a false positive, as in B. The person tested positive but does not really have the disease. The result could be a false negative, as in C. The person tested negative but really does have the disease. Or the result could be a true negative, as in D. The person tested negative and really does not have the disease. When the numbers from actual tests are plugged into these 4 boxes, we will be able to calculate sensitivity and specificity according to the equations that are shown. We will do this in class. A very sensitive test should be used when failing to find a disease that really exists, that is, a false negative, is really dangerous or deadly. This is understandable. However, you will be following up on a higher number of false positives under these circumstances than you would had you used a less sensitive test. Sensitive tests are used for screening or to rule out the disease. You can rule out the disease in people who test negative on a sensitive test. Remember, sensitive tests are used to rule out the disease. A very specific test is used to correctly identify people who do not have the disease. A test with 100% specificity would be negative for every person without the disease. A positive result on such a test means that it is very likely that the disease is present. A test with high specificity results in few false positives and should be used when false positives could be dangerous or serious. For example, you would not want to start someone on chemotherapy unless you were very, very sure or certain that the person had cancer. A false positive for cancer that leads to the use of chemotherapy could be bad. Very specific tests are used to confirm or rule in a disease. These tests are called confirmatory or diagnostic tests. Well, sensitivity and specificity can help you make decisions about acceptable levels of false positives and false negatives. They do not tell you about the probability that a patient with a positive test result actually has the disease. Similarly, they do not tell you about the probability that a person with a negative test result really does not have the disease. To obtain these probabilities, we calculate the positive predictive value and the negative predictive value of the test. We can also use the 2x2 matrix to make calculations of positive and negative predictive value. To calculate positive predictive value, the number of people in box A will become the numerator in a ratio, and the total of the numbers in boxes A and B will become the denominator. This is the number of people with positive results who actually have the disease, true positive, divided by the total number of people with a positive test result. To calculate negative predictive value, the number of people in box D will become the numerator, and the total of the numbers in boxes C and D will become the denominator. This is the number of people who tested negative that really do not have the disease, true negative, divided by the total number of people who tested negative. We will make these calculations in class. Remember that even in a healthy population, 2.5% of the people will have values above and 2.5% will have values below the reference range. Think about what would happen if you were to move the cutoff to the right or the left in the figure. If we move it to the left towards the healthy population, we'll catch more people who actually have the disease. This would be important if the disease is particularly dangerous. However, the number of false positives will go up. More people might be made unnecessarily anxious and have to undergo another test. If you were to move the cutoff towards the disease population, the number of false negatives would go up, and we would miss people who really have the disease. Receiver operating characteristic, or ROC curves, can be used to decide what an appropriate cutoff for a particular test should be. We'll take a look at these curves in a moment. First, take a look at the history of the construction of these curves. It's pretty interesting, and it provides a great explanation for why such curves are used for making medical decisions. ROC curves plot sensitivity on the y-axis against the false positive error rate on the x-axis. Take a look at this ROC curve for a test for systolic blood pressure. You want to decide whether your patient who underwent this test has high blood pressure which should be treated. Which blood pressure would you decide is high enough to warrant treatment? 160 millimeters of mercury? 130 millimeters? How can you use this curve to make that decision? The sensitivity of this test for 160 millimeters of mercury is not that great. However, if you chose this as the cutoff for deciding that a patient has high blood pressure, there will be very few false positives. The sensitivity for 130 millimeters of mercury is pretty good. However, if you chose this as the cutoff, there will be a lot more false negatives. Different sensitivities and specificities can result in ROC curves that are differentially useful and good. When sensitivity and false positive error rate are always equal, you really get no benefit from the curve. The shape of the ROC curve reflects the quality of the test. The better the test, the more the curve looks like line A. It rises quickly and then describes a straight horizontal line. This can be quantified in terms of area under the curve. The worst area under the curve is 0.5, as in line C, and the best is 1.0, which is shown in line A. Generally, an area under the curve of 0.5 to 0.6 is practically useless. An area under the curve of 0.6 to 0.7 is the result of a poor curve. 0.7 to 0.8 is fair, and 0.8 to 1.0 is a very good area under the curve.
This 2x2 table template should be familiar to you from Module 11. I've added the equation for prevalence at the bottom right. You learned about and had practice calculating positive predictive values and negative predictive values last week in class. The predictive value of a test is not a property of the test alone. It's determined by sensitivity, specificity, and the prevalence of disease in the population being tested. We'll spend more time on the subject of prevalence in Module 12. Because predictive value is influenced by prevalence, it's not independent of the setting in which the test is used. Positive results, even for a very specific test, when applied to patients with a low likelihood of having the disease, are likely to be false positives. Similarly, negative results, even for a very sensitive test, when applied to patients with a high chance of having the disease, are likely to be false negatives. So in other words, the interpretation of positive or negative medical test results varies from setting to setting according to the prevalence of disease. It might not be intuitively obvious why prevalence should affect the interpretation of a test result, so it might help to consider how a test would perform at the extremes of prevalence. Remember, no matter how sensitive or specific a test might be, there will still be a small population of patients who are misclassified by it. Imagine a population in which no one has the disease. In such a group, all positive test results, even for a very specific test, will be false positives. Therefore, as the prevalence of a disease approaches zero, the positive predictive value of a test also approaches zero. In contrast to this, if everyone in a population tested has the disease, all negative test results will be false negatives, even for a very sensitive test. As prevalence approaches 100%, negative predictive value approaches zero. This figure illustrates the effect of prevalence and positive predictive value for a test at different, but generally high levels of sensitivity and specificity. When the prevalence of the disease in the population tested is relatively high, the test performs well. But at lower prevalences, the positive predictive value drops to nearly zero and the test is virtually useless. Notice that as sensitivity and specificity fall, the influence of prevalence on predictive value becomes more pronounced. Prevalence is usually more important than sensitivity and specificity in determining predictive value. One reason why this is so is that prevalence can vary over a much wider range. Prevalence of a disease can vary from 1 in 1 million to less than 1 in 10, depending on the age, gender, risk factors and clinical findings of the patient. In contrast, sensitivity and specificity of diagnostic tests usually vary over a much narrower range, from about 50 to 99%. So the take-home message is that diagnostic tests work best when used for patients with a high likelihood of disease. Likelihood ratios are an alternative way of describing the performance of a diagnostic test. They summarise the same kind of information as sensitivity and specificity and can be used to calculate the probability of disease after a positive or negative test result. Essentially, they combine information about sensitivity and specificity into a single clinically useful measure, and because of this, they don't depend on the prevalence of the disease, but are fixed, independent characteristics of the test itself, unlike predictive values. Different tests have different likelihood ratios, and the clinical implications of these vary, as shown by the rules of thumb in this table. A test with a high positive likelihood ratio is useful to rule in a disease, while a test with a low negative likelihood ratio is useful to rule one out. For example, say you have a patient with anemia and a serum ferritin of 60 millimoles per litre. You find in an article that 90% of patients with iron deficiency anemia have serum ferritins in the same range as your patient. This is the sensitivity. And that 15% of patients with other causes for anemia have serum ferritins in the same range. If you calculate the positive likelihood ratio, you get a value of 6. This means that your patient's result would be substantially more likely to be seen in someone with, as opposed to someone without, iron deficiency anemia. There's nothing to stop you from calculating the negative likelihood ratio instead. So if we stick with the same example, a negative likelihood ratio value of 0.12 means that your patient's result would be substantially less likely to be seen in someone without, as opposed to someone with, iron deficiency anemia. This is essentially saying the same thing as the positive likelihood ratio value, but from the opposite perspective. Previously in Module 11, we've covered important biostatistical concepts used to evaluate and choose useful and appropriate screening or diagnostic tests, as well as to objectively interpret their results, ultimately so that the data can guide rather than mislead medical decision making. In particular, sensitivity and specificity, false positives and negatives, and predictive values. We've also looked at how negative and positive predictive values vary according to the prevalence of the disease in question, which makes for an extra layer of consideration when interpreting test results. Likelihood ratios are an alternative way of describing the performance of a diagnostic test. They summarize the same kind of information as sensitivity and specificity and can be used to calculate the probability of disease after a positive or negative test result. Essentially, they combine information about sensitivity and specificity into a single clinically useful measure. Because of this, they do not depend on the prevalence of the disease, but are fixed, independent characteristics of the test itself, unlike predictive values. Likelihood ratios are being used with increasing frequency in the medical literature, especially within the context of evidence-based medicine, which is one reason why you need to know how to interpret them. Likelihood ratios come in two configurations, a positive likelihood ratio and a negative likelihood ratio. The positive likelihood ratio is the probability of obtaining a positive test result in a patient with the disease of interest, divided by the probability of a positive test result for a person without the disease. In other words, the probability ratio of getting a true positive versus getting a false positive. Likewise, the negative likelihood ratio is the probability of obtaining a negative test result in a patient with the disease of interest, divided by the probability of a negative test result for a person without the disease. In other words, the probability ratio of getting a false negative versus getting a true negative. Different tests have different likelihood ratios because, as we've covered before, they have different sensitivities and specificities. The clinical implications of a positive or negative test result vary according to the size of the likelihood ratio, as shown by the rules of thumb in this table. A positive likelihood ratio with a high value is useful to rule in a disease, while a negative likelihood ratio with a low value is useful to rule out a disease. Interpreting clinical screening or diagnostic tests requires combining what you know about the clinical context and what you learn from the test result. This involves Bayesian statistics. This is a field of statistics in which prior beliefs are quantified as probabilities and used as part of the calculations. These prior probabilities can be subjective or objective, in other words, based on informed opinion or based on solid data or well-established theory. For example, there are some situations in which the prior probabilities are well defined, like in the analyses of genetic linkage. The prior probability that two genetic loci are linked is known, but in many situations the prior probabilities are little more than a subjective feeling. Many, but not all statisticians think it's okay to convert these feelings to numbers, like 99% sure or 70% sure, which are then treated as probabilities. The actual calculation involves quantifying the prior belief as a pretest probability, expressing that probability as pretest odds, and then multiplying the pretest odds by the appropriate likelihood ratio, depending on whether the lab test result obtained was positive or negative. This will give you a measure of the post-test odds, which can then be re-expressed as a post-test probability. It's straightforward algebra, but even so, many people use a nomogram or online calculator to save time. Let's talk through an example of doing this. Mariah is a 17-year-old student who comes to you with concerns of general fatigue and occasional dizziness. She's no significant past medical history and is not on any regular medicines. She doesn't drink alcohol or smoke, and her parents are both healthy. On examination, she has strong peripheral pulses, and her cardiovascular system examination is normal. Her blood pressure is 115/75, and her pulse 90 beats per minute. She's a BMI of 19.5, as well as having pale skin, conjunctiva, and nail beds. Given her clinical symptoms, age, and the findings on the physical examination, you suspect that Mariah may have iron deficiency anemia and want to proceed by ordering a serum ferritin lab test. Iron deficiency anemia, as the name implies, is due to insufficient iron. Without enough to produce physiologically normal levels of hemoglobin, this form of anemia may leave you tired and short of breath. The lab test we're going to use measures the concentration of ferritin in Mariah's blood. Ferritin is a protein that helps store iron in your body. A low level of ferritin usually indicates a low level of stored iron. Here are the things we have to calculate or quantify. First up is the pretest probability. We need to quantify our prior belief, i.e. our clinical suspicion, that Mariah has iron deficiency anemia. We want to be as objective as we can by looking for a pretest probability based on solid published data. This paper has prevalence data from the CDC for iron deficiency anemia. Prevalence is the number of people who have the disease of interest throughout a given period of time in the general population. We'll learn more about it in Module 12. The prevalence for iron deficiency anemia for women in Mariah's age range is 12%, if we go with the more recent 1999-2000 numbers. This means that during that year, 12% of women aged 12 to 49 had iron deficiency anemia. So any female patient in Mariah's age group who walked into a clinic before ordering a test would have had a 12% pretest probability of iron deficiency anemia. Next, we need to convert the pretest probability into pretest odds. As a side note, odds and probability are two alternatives for expressing precisely the same concept, which is that of chance. Every probability can be expressed as odds. Every odds can be expressed as a probability. Some scientific fields tend to prefer using probabilities. Other fields tend to favour odds. There's no consistent advantage to using one or the other. This gives us a pretest odds of 0.136. To determine the post-test odds of iron deficiency anemia, we need to multiply the pretest odds by the positive likelihood ratio for serum ferritin. We're using the positive likelihood ratio because Mariah's test result was positive. You find an article that gives you sensitivity and specificity information for the serum ferritin test for iron deficiency anemia. This allows us to calculate a positive likelihood ratio of 6. This means that Mariah's test result would be substantially more likely to be seen in someone with, as opposed to someone without, iron deficiency anemia. Doing the calculation gives us a post-test odds of 0.816. Finally, we want to convert the post-test odds back to post-test probability, which is more clinically intuitive, which gives us a final post-test probability of 0.45 or 45%. The positive serum ferritin test increased the likelihood that Mariah does indeed have iron deficiency anemia. Let's look at the calculations and change in post-test probability if Mariah had had a negative serum ferritin test result instead. The pretest probability and odds are the same as before. This time we need to calculate a negative likelihood ratio, which gives us a value of 0.12. Doing the calculation gives us a post-test odds of 0.016. Converting the post-test odds back to a post-test probability, we have a final answer of 1.57%. So if Mariah's serum ferritin test had been negative, then the likelihood of iron deficiency anemia would have decreased. So to sum up, likelihood ratios are used to assess how good a diagnostic test is, and to help in selecting appropriate tests. They have advantages over predictive values because they're less likely to change with the prevalence of the disorder. They can be calculated for several levels of the presenting symptoms, and they can be used to calculate post-test probability for a disease of interest. Bayesian statistics is a field of stats in which prior beliefs are quantified as pre-test probabilities and combined with the likelihood ratio to calculate post-test probabilities. They allow interpretation of clinical screening or diagnostic tests within their clinical context.
Remember this patient from module number 11. As the clinician continuing to care for this patient, you have additional thoughts and considerations. Is he at risk for coronary artery disease? What is its occurrence and distribution in the population to which he belongs? If coronary artery disease is found, will the condition shorten his life? Will reduction of his risk factors, i.e. from cigarette smoking or hypertension, improve his outlook? Clinicians also need the answers to these kinds of questions in order to make the best possible medical decisions for their patients. Epidemiology is usually defined as the study of factors that determine the occurrence and distribution of a disease in a population. There are two important words that are used to describe how much of a specific disease exists. The first is incidence, the frequency of the occurrence of the disease, the number of new cases of the disease over the course of a study. The second is prevalence, which is the number of people who have the disease over a given period or interval of time or at a given point in time. Prevalence equals incidence times the average duration of the disease. Over the course of a study, each new case or incident goes into the prevalence pot. Each case in the pot can do one of two things. It can remain in the pot for the duration of the study, or it can come out of the pot, either because the person dies or because they recover from the disease. The rain coming into the puddle and the water evaporating from the puddle are another way to think about incidence and prevalence. An individual can represent an incident only once, but can be a prevalent case at a number of points in time. For example, case number 3 is a prevalent case both at mid-year, where the vertical line is, and at the end of the study on December 31st. Case number 5 is only a prevalent case at the end of the study. Incident rates and prevalence rates are both measures of morbidity. A number of factors contribute to specific diseases having high or low prevalence. Here's an example of diabetes prevalence, and another of HIV prevalence. Here you can see that the prevalence of AIDS increased steeply from 1981 to 1990. This was mostly due to new incidents. After 1990, the prevalence, while much higher than in 1981, levels off. The sharp rise is not continuing. That's not because the number of new cases level off. They do not. They continue to rise sharply. However, the number of people dying from AIDS begins to decrease. Therefore, the prevalence levels off. Certain events or factors put people at risk for the disease of interest over the course of a study. Attributable risk is the additional incidence above baseline that is caused by the risk factor or event. The absolute risk of getting a disease is equivalent to the incidence of the disease. While this makes sense, it is not always the most useful concept. Often what we want to know is what the relative risk of a person or a group getting the disease is. That is there something about a particular group or this situation that puts them at relatively greater risk than other persons are at? One example of relative risk factor is age. You might want to know what the relative risk of disease incidence is in people over 75 years compared to that in people under 45 years of age. You might want to also calculate the relative risk ratio for the incidence of broken legs in people who ski compared to those who do not. I'll bet you can think of a lot of relative risk factors. To find relative risk, we start looking at the incidence of the disease in the present and wait for time to pass. We look at one group that naturally lives with the risk factor and one that does not, and ask which group has more people who develop the disease over the course of the study. This is called a prospective approach to studying the role of risk. We are asking what happens going forward from the present time. In class, we will calculate absolute risk reduction and relative risk reduction. Take a look at the results of the study described by Glaser. During the study, 73 of the 3,293 men in the placebo group died from a cardiovascular event, and 30 of the 3,302 men in the pravastatin group died. Thus, 2.2% of the men in the placebo group died, and 1.5% of the men in the treatment group died of a cardiovascular event. The relative risk of death was then 1.5 divided by 2.2, which equals 0.68. Therefore, the relative risk reduction was 1 minus 0.68, which equals 0.32, or 32%. That's a pretty big number. It looks as if the pravastatin really lowers the risk of death. Absolute risk reduction is the difference between the absolute risk rate of the placebo and the drug groups. Here, that would be 2.2% minus 1.5%, which equals 0.7%. So the absolute risk reduction is pretty small. Given the numbers from this study, which do you think better reflects reality, relative risk reduction or absolute risk reduction? Absolute risk reduction also allows you to calculate a statistic called numbers needed to treat, NNT. NNT equals 100 divided by absolute risk reduction. Here, that is 100 divided by 0.7, which equals 143. The 143 represents the number of people you would need to treat to save one life. What if the NNT were 1,000,000? What if it was 3? How would you think differently about it? In a case control study, a group of people who already have the disease and a controlled disease-free group are identified, and we look back to see how many people in each group had been exposed to the risk factor for the disease in the past. Therefore, case control studies are retrospective studies because we're looking back from the present. When retrospective studies are conducted, odds ratios are calculated. An odds ratio is the odds that a person with the disease or a case was exposed to the risk factor divided by the odds that a person without the disease or the control was exposed to the risk factor. Obviously, if this ratio equals 1, then the odds that the two groups were exposed to the risk factor is equivalent. Rather than looking at the risk for a disease, we can also look at the rate of a disease. The rate is the number of people who get the disease during a given interval divided by the number of people who were at risk for the disease during that interval times a constant. Sometimes it's more informative to use rate than risk when examining a disease. In this figure, the percentage of people surviving at any given time is plotted against time. Over the year, the risk of death was 10% in all three populations, but if you wanted to know about survival at mid-year, you would see that the rate of death, which is calculated using the percentage of deaths at that time as the denominator, would be the highest in population A and the lowest in population B. We use something called confidence intervals to assess whether a risk ratio or an odds ratio differs significantly from 1. In class, we will use confidence intervals to determine whether specific risk and odds ratios are significantly different from 1. Hazard ratios are ratios of rates. They can be hazard rates, cure rates, or survival rates. To construct a Kaplan-Meier curve from survival data, you place time on the x-axis and the percentage of people who are progression-free and surviving on the y-axis. You can imagine two curves on this plot, one for a treatment group and one for a control group. This would help you see the difference in survival rates between the two groups. Remember this patient from module number 11. As the clinician continuing to care for this patient, you have additional thoughts and considerations. Is he at risk for coronary artery disease? What is its occurrence and distribution in the population to which he belongs? If coronary artery disease is found, will the condition shorten his life? Will reduction of his risk factors, i.e. from cigarette smoking or hypertension, improve his outlook? Clinicians also need the answers to these kinds of questions in order to make the best possible medical decisions for their patients. Epidemiology is usually defined as the study of factors that determine the occurrence and distribution of a disease in a population. There are two important words that are used to describe how much of a specific disease exists. The first is incidence, the frequency of the occurrence of the disease, the number of new cases of the disease over the course of a study. The second is prevalence, which is the number of people who have the disease over a given period or interval of time or at a given point in time. Prevalence equals incidence times the average duration of the disease. Over the course of a study, each new case or incident goes into the prevalence pot. Each case in the pot can do one of two things. It can remain in the pot for the duration of the study, or it can come out of the pot, either because the person dies or because they recover from the disease. The rain coming into the puddle and the water evaporating from the puddle are another way to think about incidence and prevalence. An individual can represent an incident only once, but can be a prevalent case at a number of points in time. For example, case number 3 is a prevalent case both at mid-year, where the vertical line is, and at the end of the study on December 31st. Case number 5 is only a prevalent case at the end of the study. Incident rates and prevalence rates are both measures of morbidity. A number of factors contribute to specific diseases having high or low prevalence. Here's an example of diabetes prevalence and another of HIV prevalence. Here you can see that the prevalence of AIDS increased steeply from 1981 to 1990. This was mostly due to new incidents. After 1990, the prevalence, while much higher than in 1981, levels off. The sharp rise is not continuing. That's not because the number of new cases level off. They do not. They continue to rise sharply. However, the number of people dying from AIDS begins to decrease. Therefore, the prevalence levels off. Certain events or factors put people at risk for the disease of interest over the course of a study. Attributable risk is the additional incidence above baseline that is caused by the risk factor or event. The absolute risk of getting a disease is equivalent to the incidence of the disease. While this makes sense, it is not always the most useful concept. Often what we want to know is what the relative risk of a person or a group getting the disease is. That is there something about a particular group or this situation that puts them at relatively greater risk than other persons are at? One example of relative risk factor is age. You might want to know what the relative risk of disease incidence is in people over 75 years compared to that in people under 45 years of age. You might want to also calculate the relative risk ratio for the incidence of broken legs in people who ski compared to those who do not. I'll bet you can think of a lot of relative risk factors. To find relative risk, we start looking at the incidence of the disease in the present and wait for time to pass. We look at one group that naturally lives with the risk factor and one that does not, and ask which group has more people who develop the disease over the course of the study. This is called a prospective approach to studying the role of risk. We are asking what happens going forward from the present time. In class, we will calculate absolute risk reduction and relative risk reduction. Take a look at the results of the study described by Glaser. During the study, 73 of the 3,293 men in the placebo group died from a cardiovascular event, and 50 of the 3,302 men in the pravastatin group died. Thus, 2.2% of the men in the placebo group died, and 1.5% of the men in the pravastatin treatment group died of a cardiovascular event. The relative risk of death was then 1.5 divided by 2.2, which equals 0.68. Therefore, the relative risk reduction was 1 minus 0.68, which equals 0.32, or 32%. That's a pretty big number. It looks as if the pravastatin really lowers the risk of death. Absolute risk reduction is the difference between the absolute risk rate of the placebo and the drug groups. Here, that would be 2.2% minus 1.5%, which equals 0.7%. So the absolute risk reduction is pretty small. Given the numbers from this study, which do you think better reflects reality? Relative risk reduction or absolute risk reduction? Absolute risk reduction also allows you to calculate a statistic called numbers needed to treat, NNT. NNT equals 100 divided by absolute risk reduction. Here, that is 100 divided by 0.7, which equals 143. The 143 represents the number of people you would need to treat to save one life. What if the NNT were 1,000,000? What if it was 3? How would you think differently about it? In a case control study, a group of people who already have the disease and a control disease-free group are identified, and we look back to see how many people in each group had been exposed to the risk factor for the disease in the past. Therefore, case control studies are retrospective studies because we're looking back from the present. When retrospective studies are conducted, odds ratios are calculated. An odds ratio is the odds that a person with the disease or a case was exposed to the risk factor divided by the odds that a person without the disease or the control was exposed to the risk factor. Obviously, if this ratio equals 1, then the odds that the two groups were exposed to the risk factor is equivalent. To calculate an odds ratio, we first need to understand what odds are. Odds equals the probability of an event occurring divided by the probability of the event not occurring. With a 6-faced die, the probability of tossing a 6 is 1 divided by 6, which is 0.167. The probability of not tossing a 6 is 5 divided by 6, which is 0.833. Therefore, the odds of tossing a 6 are 0.167 divided by 0.833, which equals 20%. So, an odds ratio is a ratio of two odds, and odds are ratios of two probabilities. Therefore, we need to calculate 4 probabilities to get the two odds that make up the numerator and denominator of the odds ratio. Let's look at a 2x2 table to see where the numbers for these ratios come from. In the matrix, we see that 176 people with the disease, asthma, were exposed to the risk factor, mold, and 108 people without asthma were exposed to mold. We also see that 98 people with asthma were not exposed to mold, while 211 people without asthma were not exposed to mold. Below the tables, you can see the 2 probabilities to calculate the odds of the disease in the risk group, as well as the 2 probabilities to calculate the odds of the disease in the no-risk group. Given the 2 odds that we just calculated, the odds ratio for this matrix is 3.5. Now, believe it or not, all of this is the same as A times G divided by B times C, as you can see in the equation below the matrix. What does this mean, however? It means that people with asthma were 3.5 times more likely to have been exposed to mold in the past than those without asthma. Rather than looking at the risk for a disease, we can also look at the rate of a disease. The rate is the number of people who get the disease during a given interval divided by the number of people who are at risk for the disease during that interval times a constant. Sometimes it's more informative to use rate than risk when examining a disease. In this figure, the percentage of people surviving at any given time is plotted against time. Over the year, the risk of death was 10% in all 3 populations, but if you wanted to know about survival at mid-year, you would see that the rate of death, which is calculated using the percentage of deaths at that time as the denominator, would be the highest in population A and the lowest in population B. We use something called confidence intervals to assess whether a risk ratio or an odds ratio differs significantly from 1. In class, we will use confidence intervals to determine whether specific risk and odds ratios are significantly different from 1. Hazard ratios are ratios of rates. They can be hazard rates, cure rates, or survival rates. To construct a Kaplan-Meier curve from survival data, you place time on the x-axis and the percentage of people who are progression-free and surviving on the y-axis. You can imagine 2 curves on this plot, one for a treatment group and one for a control group. This would help you see the difference in survival rates between the 2 groups. There are three major categories of quantitative study design that we will examine in this module. Experimental studies are randomized controlled studies or randomized controlled clinical trials. These studies have a dependent and an independent variable. It is easy to remember the difference between the two because the quantity of the dependent variable depends on whether the subject was in the experimental group or the control group. In other words, it depends on the level or amount of the independent variable that the subject was exposed to. These studies are used to test hypotheses. Studies are double-blind if neither the researcher nor the participant know which participants are in the treatment group while the study is going on. Here's an example of an experimental study in which the researcher wants to know whether weight-bearing exercise reduces osteoporosis. Here's a typical protocol for an experimental study in which the subjects are randomly assigned to treatment groups. Sometimes it is not practical or not ethical to randomly assign people to groups. When random assignment cannot occur, the study is a quasi-experimental study. The subjects are not randomized to the treatment groups. Other aspects of the design are the same as for a true experimental design. In observational studies, the researchers observe and record results without making a manipulation. There are many types of observational studies, and these are coming up next. In a cohort study, exposure to the risk factor is established, and the researcher follows people over time to record who gets the disease of interest. This is a prospective study. In a historical study, both the exposure to the risk factor and the disease status are known, and the researcher uses historical data to define a risk group. One might ask, what percentage of the people in the study that are known to have a disease had the risk compared to the percentage of people who did not have the disease? This is a retrospective study. In a case control study, exposure to the risk factor is not known, but the disease status is. The researcher then looks back to examine the proportion of people with the disease who were exposed to the risk factor and the proportion of those without the disease who were exposed. This is also a retrospective study. Case series studies are used to describe the presentation of a disease. A case report is a special kind of case series study in which the presentation is of a single patient. Prevalence surveys are conducted to assess the prevalence of a specific disease in a specific time and a specific place. In cross-sectional studies, both current exposure to the risk factor and current disease status are examined at the same time and only once. These are snapshots of the relationship between the risk factor and the disease. Longitudinal studies are cross-sectional studies in which the disease status of the patient is assessed repeatedly over a period of time. This can help to establish disease trends in a population. Ecological studies are studies in which populations rather than individuals are the participants. The next two slides are visual guides to observational study designs. Studies can also have a qualitative study design. To conduct qualitative studies, researchers use anthropological techniques such as ethnographic observations, open-ended questions, and focus groups. The researcher especially wants to avoid projecting her or his own biases into the study. The researcher really wants to learn from the participants and does not have a preconception of what the participants find important. Such studies are used to detect patterns in participants' responses and to utilize insights provided by the responses. Studies with different study designs can be used to either generate hypotheses or to test hypotheses as shown in this figure. The next three slides present the pros and cons of each type of study design.
Bias is a process at any stage of inference, tending to produce results that depart systematically from true values. It's an error in the conception and design of a study, or in the collection, analysis, interpretation, publication, or review of data, leading to results or conclusions that are systematically, as opposed to randomly, different from the truth. Bias usually produces deviations or distortions that tend to go in one direction. It becomes a problem when it weakens a true association, or produces a spurious association, or distorts the apparent direction of association between variables. For example, patients with inguinal hernia who get laparoscopic repair seem to have less post-operative pain and more rapid return to work than those who get the traditional open surgery. A careful clinician asks, are the results of laparoscopic surgery really better, or might they only appear better as a result of biases in the way the information was collected? Perhaps laparoscopic repair is offered to patients who are in better health, or seem to have better tissue strength because of age or general fitness. Perhaps surgeons and patients are more inclined to think that the procedure should cause less pain because it's new and the scar is smaller, and so the patients report less pain and the surgeons are less likely to ask about it or are less likely to record pain in the medical record. Perhaps patients who get laparoscopic surgery are usually instructed to return to work earlier than those who get open surgery. If any of these were so, the favourable results could be related to systematic differences in how patients were selected for the laparoscopic procedure, how they reported their symptoms, or how they were told what they could do, rather than a true difference in success rate. If any of these were so, the favourable results could be related to systematic differences in how patients were selected for the laparoscopic procedure, how they reported their symptoms, or how they were told what they could do, rather than a true difference in success rates. Observations in patients, whether for patient care or research, are particularly susceptible to bias. The process tends to be just plain untidy. As participants in a study, humans have the disconcerting habit of doing as they please, and not necessarily what would be required for producing scientifically rigorous answers. When researchers attempt to conduct an experiment with them, as one might in a laboratory, things tend to go wrong. Some people refuse to participate, whereas others drop out or choose another treatment. In addition, clinicians are inclined to believe that their therapies are successful. This attitude, which is so important in the practice of medicine, makes clinical observations particularly vulnerable to bias. Although dozens of biases have been defined, most fall into one of four broad categories, namely selection, allocation, measurement, or recall bias. Selection and allocation bias belong to the category of assembly bias, which arises when groups being compared are not equally susceptible to the outcome of interest, for reasons other than the factor under study. Allocation bias occurs if investigators choose a non-random method of assigning subjects to study groups, or if the random method that has been chosen isn't followed. For example, allocation bias would have occurred if patients chosen to receive the laparoscopic procedure were healthier than those who were chosen to have open surgery. The researchers might have done this because they favoured the intervention and wished to show that it was more effective than the control treatment. Selection bias is considered to have occurred when subjects are allowed to select the study group they want to be in. For example, more educated, or more desperate, or more influential people may lobby hard to be enrolled in the intervention group for a novel therapy. Detection bias is the result of failure to detect a case of disease, a possible causal factor, or an outcome of interest. It can be caused by the use of a particular diagnostic technique or type of equipment. For example, cancer rates may vary in different geographical regions, not because of an actual difference in the incidence of the disease, but because of different diagnostic technologies. Measurement bias occurs when the method of measurement leads to systematically incorrect results. For example, blood pressure levels are powerful predictors of cardiovascular disease. However, multiple studies have shown that taking a blood pressure measurement is not as simple as it seems. Correct measurement requires using appropriate procedures, including using a larger cuff size for overweight and obese adults, positioning the patient so that the upper arm is below the level of the right atrium, and so the patient does not have to hold up their arm, and taking the measurement in a quiet setting and multiple times. If any of these procedures is not done correctly, the resulting measurements are likely to be artificially and systematically elevated. Another factor leading to systematically higher blood pressure readings is sometimes called white coat hypertension. It often occurs when blood pressure is being measured by physicians, suggesting that visits to the doctor cause anxiety in patients. Also, clinicians who deflate the blood pressure cuff faster than 2 to 3 millimeters per second will likely underestimate systolic, but overestimate diastolic blood pressure. Studies have also shown a tendency for clinicians to record values that are the normal level in patients with borderline high blood pressures. Systematic errors in blood pressure measurements can, therefore, lead to overtreatment or undertreatment of patients in clinical practice. Clinical research based on blood pressure measurements taken during routine patient care can lead to misleading results unless careful standardized procedures are used. These kinds of biases led to the development of blood pressure measurement instruments that do not involve human ears and hands. Confounding can occur when we're trying to find out whether a factor such as behavior or drug exposure is a cause of disease in and of itself. If the factor of interest is associated with another second factor, which itself is also related to the outcome, the effect of the factor under study, the first factor, that can be confused with or distorted by the effect of the second factor. So in essence, confounding is the confusion of two supposedly causal variables, so that part or all of the purported effect of one variable is due to the other. The effect is to potentially obscure a true causal relationship. For example, supplements of antioxidants such as vitamins A, C, and E are popular with the lay public. Laboratory experiments and studies of people who choose to take antioxidants initially suggested that antioxidants prevent cardiovascular disease and certain cancers. However, careful randomized studies, which are able to avoid confounding, routinely found little effect of antioxidants. In fact, when results of these studies were combined, use of antioxidants, especially at high doses, was associated with small increases, not decreases, in death rates. How could the results of early studies be reconciled with the opposite findings of later, carefully controlled trials? Confounding has been suggested. People who take antioxidants on their own are likely to do other things differently than those who do not take antioxidants, such as exercise more, watch their weight, eat more vegetables, and not smoke. And it may be these activities, not the antioxidants, that led to lower death rates in the studies not randomizing the intervention. Most clinical research studies, especially studies that observe people over time, routinely try to avoid confounding variables in the analysis. Variables such as age, sex, and race are almost always analysed for confounding, because so many health outcomes vary according to them. Studies that involve human behaviour, such as taking antioxidants regularly, are especially prone to confounding, because human behaviour is so complex that it's difficult to analyse for all the factors that might influence it. It's worth noting that a study may involve several types of biases and confounders at the same time. For example, concerns have been raised that caffeine consumption during pregnancy may lead to adverse fetal outcomes. It would be unethical to determine if caffeine is dangerous to fetuses by an experiment assigning some pregnant women to drink high levels of caffeine and others not, so researchers have usually studied what happens during pregnancy according to the amount of caffeine ingested. However, several biases have been demonstrated in many of these studies. Measurement bias could have occurred because most studies relied on self-reported intake of caffeine. One study demonstrated recall bias, a type of measurement bias that refers to differential recall in people with an adverse outcome compared to those with a normal outcome. An association was found between caffeine consumption and miscarriage when women were interviewed after they miscarried, but not when women were questioned about caffeine consumption before miscarriage. If some women were recruited for caffeine studies during prenatal visits, women who are likely to be particularly health conscious, and others recruited towards the end of their pregnancy, the different approaches to recruitment could lead to selection bias that might invalidate the results. Finally, heavy coffee consumption is known to be associated with cigarette smoking, lower socio-economic levels, greater alcohol consumption, and generally less health consciousness, all of which could confound any association between caffeine and adverse fetal outcomes. The potential for bias does not mean that bias is actually present in a particular study, or, if present, would have a big enough effect on the results to matter. For a researcher or reader to deal effectively with bias, it's first necessary to know where and how to look for it, and what can be done about it. But one should not stop there. It's necessary to determine whether bias is actually present and how large it is likely to be, and then decide whether it's important enough to change the conclusions of the study in a clinically meaningful way. Bias and confounding present problems at different points in a clinical study. When selection bias, for example, exists in a study, irreparable damage results and eternal validity is doomed. By contrast, when confounding is present, this can be corrected, provided that confounding was anticipated and the requisite information gathered. Confounding can be controlled for before or after a study is done. But how do we deal with biased samples? Biased samples are unrepresentative, therefore, true randomization is the best proof against bias. How do we control for confounding? Well, there are 4 possibilities. The simplest approach is restriction, which is also called exclusion or specification. For example, if cigarette smoking is suspected to be a confounding factor, a study can enroll only non-smokers. Although this tactic avoids confounding, it also hinders recruitment, and thus power, and precludes extrapolation to smokers. Restriction might increase the internal validity of a study at the cost of poorer external validity. A second option to control for confounding is called pairwise matching. In a case control study in which smoking is deemed a confounding factor, cases and controls can be matched by smoking status. For each case who smokes, a control who smokes is also found. This approach, although often used by investigators, has 2 drawbacks. If matching is done on several potential confounding factors, the recruitment process can be cumbersome, and, by definition, one cannot examine the effect of a matched variable. A third option is called stratification. This is where investigators can control for confounding after a study has been completed. Stratification allows the association between exposure and outcome to be examined within different strata or levels of the confounding variable, for example age, sex, alcohol consumption. If we were conducting a study to examine the association between lung cancer and urban atmospheric pollution, controlling for smoking, the population could be stratified according to smoking status. The association between air pollution and cancer can then be assessed separately within each stratum. When the purpose of a study is to compare health status in different populations, i.e. exposed versus non-exposed, standardization of summary rates is carried out in order to take into account differences in characteristics between the 2 populations, such as age or gender. So for example, coronary heart disease rates increase with age. Let's say 12% of population A are over the age of 65, whereas in population B, only 6% are over the age of 65. Therefore, higher crude death rates would be expected in population A on the basis of age difference alone. Standardization allows for adjustment needed to negate the effects of a variety of confounding factors, including age, sex, race, or socio-economic status. So to sum up, dealing with confounding is reasonable if you know what the likely confounders are. However, dealing with unknown confounders is obviously much trickier. There's always a risk that an apparent association between a risk factor or an intervention and an outcome is being mediated by an unknown confounder. This is particularly true of observational studies, where patients may be selected to one treatment group or another, not according to any explicit criteria, but by some unknown process, such as a care provider's gut feeling. The best defense against unknown confounders is also randomization. This ensures that both known and unknown confounders are randomly distributed between treatment groups. We introduced hypothesis testing in module number 8. It's usually impossible or impractical for a researcher to observe every individual in a population. Therefore, researchers usually collect data from a sample and then use the sample data to help answer questions about the population. Hypothesis testing is a statistical procedure that allows researchers to use sample data to draw inferences about the population of interest. It's one of the most commonly used inferential procedures. In this module, the primary goal that we want you to achieve is to be able to choose appropriate tests for a given research situation. To help you do this, there are basically two things to consider. Number one, is your data parametric or non-parametric? Or in other words, is it normally distributed or not? And secondly, the number of groups being compared. 1, 2, or more than 2. This flowchart outlines the decision process to reach the appropriate hypothesis test. In the past, it was important to understand the mathematics and equations involved in each test because they were calculated manually with pen and paper. In the age of widespread computers and statistical software, it's more important to be able to recognize which hypothesis test you should be choosing to apply to your data, so as to avoid an erroneous or misleading conclusion. For t-tests and ANOVA tests, the maths and equations are focused on comparing means from sample groups before and after an experimental intervention. They are how we answer the question, did the manipulation of the independent variable cause a statistically significant change in the dependent variable? T-tests are appropriate when only two means are being compared, either a sample mean versus a population mean, or one sample mean with a second sample mean. The latter could be a comparison of the same sample group before and after an intervention, or a comparison between two distinct sample groups. There are distinct types of t-tests for those three situations, with different underlying mathematics. The one-sample t-test, the dependent t-test, which is also known as a paired t-test, and lastly the independent t-test, also known as the unpaired test. If you want to compare the effect of an intervention in more than two sample means, then you should be choosing an ANOVA test instead. ANOVA stands for Analysis of Variance. The term analysis in statistics means to break down. There are also distinct types of ANOVA for different study designs. The three that we want you to learn to recognize are the one-way independent ANOVA, the one-way repeated measures ANOVA, and the two-way ANOVA. The one-way and two-way language refers to the number of independent variables that have been manipulated in the experiment, 1 for one-way and 2 for two-way. Another name for the independent variable when talking about ANOVA is factor. so we can legitimately also refer to these tests as the one-factor independent ANOVA, the one-factor repeated measures ANOVA, and the two-factor ANOVA. It's possible to have multiple independent variables, i.e., more than two factors. The test for this design is called a factorial ANOVA. Their design and application are complex and beyond the scope of the SRCC Biostatistics curriculum. Another special ANOVA term is level. Levels are the degrees of manipulation of the independent variable. For example, a study that examined the effect of a new drug at 3 different doses would have 3 levels of the factor. It's worth having a small sense of how the approach and underlying maths work for t-tests compared to ANOVA. For t-tests, the maths and stats equations are focused on comparing the actual difference in sample means before and after an experimental intervention with the difference expected by chance alone. In other words, does our manipulation of the independent variable cause the central tendency of the dependent variable to increase, decrease, or stay the same? T-tests quantify this as a single numerical value called a t-statistic, whereas ANOVA is focused on comparing the extent of variance in sample means before and after an experimental intervention with the difference expected by chance alone. Or in other words, did our manipulation of the independent variable cause the standard deviation of the dependent variable to increase, decrease, or stay the same? ANOVA quantifies this as a single numerical value called an F ratio. The F ratio is really just comparing the variance between treatment groups with the variance within those groups. The variance between treatment groups is composed of the differences due to the treatment effect of the independent variable being manipulated, as well as the individual differences of the study participants and differences due to chance. Whereas the variance within treatment groups is made up of just the individual differences of the study participants and those due to chance. As I said before, ANOVA stands for analysis of variance, and the term analysis in statistics means to break down. ANOVA breaks down or analyses data in the following way. It takes the total variability of a data set and separates out and quantifies the between treatments and within treatments variance. Analysis of between treatments variance starts by quantifying how different samples A, B, and C are from one another, whereas the analysis of the within treatments variance starts by quantifying how different individuals within a given sample group are from one another. Further analysis breaks down the between and within treatment variances to allow us to separate out and quantify the effect of the treatment, individual differences, and chance. Because the individual differences and differences due to chance feature in both the numerator and denominator of the F ratio, if we know their numerical values, we can cancel them out, leaving us with a measure of just the treatment effect. Let's look at how this would play out in 2 scenarios. Firstly, let's consider a situation where your manipulation of the independent variable has no effect. We'll therefore assign it the numerical value of 0. The individual differences have a value of 10, and the contribution from chance alone has a value of 5. I'm just making these numbers up for the sake of illustration. In reality, the ANOVA test in your statistical software would derive the pertinent values from your starting dataset. Here, the F ratio would simplify down to 1, and we would use p-values to interpret this result in the conventional way, and accept or fail to accept the null hypothesis accordingly. If, on the other hand, your manipulation of the independent variable does have a genuine effect, what happens? Again, let me make up some numbers for the sake of illustration. Let's say the treatment effect has a value of 155, and we'll keep the values of 10 and 5 for the individual differences and those due to chance. Here, the F ratio would simplify down to 11.33. And again, we would use p-values to interpret this result in the conventional way, and accept or fail to accept the null hypothesis accordingly. ANOVA compares all the individual sample group mean differences simultaneously within a single test. Unfortunately, when you obtain a significant F ratio, and therefore fail to accept the null hypothesis, it simply indicates that somewhere among the entire set of mean differences, there's at least one that's statistically significant. In other words, the overall F ratio only tells you that a significant difference exists. It does not tell exactly which individual sample groups are significantly different and which are not. Post hoc tests are additional hypothesis tests that are done after an ANOVA to determine exactly which mean differences are significant and which are not. Data that are observations of nominal or ordinal scales, or have deviations in skew or kurtosis, are not normally distributed, and therefore non-parametric. If you have data that's non-parametric, and you wish to compare means, then you would go through the same decision process, but switch to an equivalent non-parametric test with different underlying mathematics. For data where you want to compare differences in proportion between samples, rather than means, we want you to know about these two test options, the chi-square test and Fisher's exact test. Here are three examples. How does the number of surgeons who are women compare with the number who are men? Of the two leading brands of NSAID, which is preferred by most Americans? In the past 10 years, has there been a significant change in the proportion of non-traditional medical students matching in the specialty of their choice? Note that each of the examples asks a question about proportions in the population. We're not measuring a numerical score for each individual. Instead, the individuals are simply classified into categories, and we want to know what proportion of the population is in each category. The data for these sorts of tests are usually organised into something called a contingency table, big enough to accommodate all the individual sample groups involved. The 2x2 tables we've used for sensitivity and specificity calculations are examples of contingency tables. There, the table represents the proportion of positive and negative test results in relation to disease status. Let's look at another example. If we were investigating whether there's a relationship between extroversion and introversion and the amount of weekly exercise a person gets, we might represent our gathered data in this contingency table. We have 100 study participants who are proportionally categorized into 6 boxes or cells in the contingency table. The chi-square test can be used for research studies with large sample sizes, whereas the Fisher's exact test should be used for small sample sizes. If we return to our introversion-extroversion example, the values in each cell of the contingency table are large enough to warrant the use of the chi-square test. If, on the other hand, the data looked like this, then we would switch to Fisher's exact test. A good rule of thumb to help you decide when a sample size is too small for chi-square is that when the value of any individual cell of a contingency table is less than 5, you should use a Fisher's exact test. The cholera epidemic of 1854 claimed an estimated 19,000 lives across the United Kingdom. The number would have been much higher without the statistical genius of the physician John Snow. The first London victims all lived around Broad Street, which is pretty close to Oxford Street and Regent Street and not too far away from Soho and Golden Square in modern London. It also happened to be very close to the Frith Street office of Dr. John Snow, who had spent years trying to determine how cholera was communicated from one person to another. Nobody knew where the disease came from, and nobody knew why it left. All they knew was that death was sudden, vicious, and apparently random. In just 10 days, the death toll in Snow's neighbourhood climbed from 127 to 500, approximately 37 new deaths every day. As the death toll climbed, Snow had a specific idea he wanted to test. To do this, he identified each cholera victim and where that person lived. On a map of London, he marked with a dot the location of each cholera victim's home and placed an X to indicate where the water wells were. Almost all the deaths were near the Broad Street water well, the X circled in red on the map. The visual presentation of these data revealed that the closer a home was to the well, the more likely it was a death from cholera had occurred there. Correlation is a statistical technique that is used to measure and describe a relationship between two variables. These scores normally are identified as X and Y. The pairs of scores can be listed in a table, or they can be presented graphically in a scatter plot. The value of the scatter plot is that it allows you to see any patterns or trends that exist in the data. A relationship exists between X and Y for these data. Generally, as X increases, so does Y. John Snow's map of London was essentially a scatter plot that allowed him to see the relationship between proximity to the Broad Street well and cholera infection. A correlation is a numerical value that describes and measures three characteristics of the relationship between X and Y. The first of these three characteristics is direction. The sign of the correlation, whether it's positive or negative, describes the direction of the relationship. So in these two examples, beer sales and temperature are positively correlated, which means as temperature increases, so do beer sales. On the other hand, coffee sales and temperature are negatively correlated. More coffee sold when it's colder. The second characteristic is the form of the relationship. In the previous coffee and beer examples, the relationships tend to have a linear form. That is, the points in the scatter plot tend to form a straight line. Notice that there's a line drawn through the middle of the data points in each figure to help show the relationship. The most common use of correlation is to measure straight line relationships. However, you should note that other forms of relationships do exist and that there are special correlations used to measure them. In the first scatter plot of figure 16.3, we see the relationship between reaction time and age. In this scatter plot, there's a curved relationship. Reaction time improves with age until the late teens when it reaches a peak. After that, reaction time starts to get worse. In the second scatter plot, we see the relationship between mood and drug dose. This is a dose-response relationship, and again it's not a straight line. In this graph, the elevation in mood increases rather rapidly with dose increases. However, beyond a certain dose, the amount of improvement in mood levels off and reaches a plateau. In fact, many types of measurements exist for correlation. In general, each type is designed to evaluate a specific form of relationship, but in this module we're going to concentrate on the correlation that measures linear relationships. Finally, the correlation measures the consistency or strength of a relationship. For a linear relationship, for example, the data points could fit perfectly on a straight line. Every time X increases by 1 point, the value of Y also increases by a consistent and predictable amount. However, relationships are usually not perfect. Although there may be a tendency for the value of Y to increase whenever X increases, the amount that Y changes is not always the same, and occasionally Y decreases when X increases. In this situation, the data points will not fall perfectly on a straight line. The consistency of the relationship is measured by the numerical value of the correlation. A perfect correlation is always identified by a correlation of 1 and indicates a perfect consistent relationship. For a correlation of 1, or negative 1, it doesn't matter, each change in X is accompanied by a perfectly predictable change in Y. At the other extreme, a correlation of 0 indicates no consistency at all. For a correlation of 0, the data points are scattered randomly with no clear trend. Intermediate values between 0 and 1 indicate the degree of consistency. Here are some examples of different values for linear correlations. In each example, I'll sketch a line around the data points. This line is called an envelope because it encloses the data and often helps you see the overall trend in the data. As a rule of thumb, when the envelope is shaped roughly like an American football, the correlation is around 0.7. Envelopes that are fatter than an American football indicate correlations close to 0. If a correlation is round or spherical, like a soccer ball, then there's not really any relationship at all. Shapes narrower than an American football indicate correlations closer to 1. Here are some examples of data representing different degrees of linear relationship. In the first figure, the data shows the relationship between IQ and shoe size. In this case, the correlation is 0, and you have no ability to predict a person's IQ based on his or her shoe size. We can draw an envelope around the data, which is roughly spherical, which again indicates that the correlation value is close to 0. Knowing a person's shoe size provides no information about the person's IQ. In this case, shoe size provides no information to help explain why different people have different IQs. Now let's look at the data in the second figure. These data show a moderate positive correlation of positive 0.8 between IQ scores and college grade point averages. Students with high IQs tend to have higher grades than students with low IQs. From this relationship, it's possible to predict a student's GPA based on his or her IQ. However, you should realize that the prediction is not perfect. Although students with high IQs tend to have high GPAs, this is not always true. Thus, knowing a student's IQ provides some information about the student's grades, or knowing a student's grades provides some information about the student's IQ. In this case, IQ scores help explain the fact that different students have different GPAs. Specifically, you can see that part of the difference in GPA is accounted for by IQ. Lastly, we consider the data in the third scatter plot. This time we show a perfect linear relationship with a correlation value of 1. The data here examine the relationship between monthly salary and yearly salary for a group of college employees. With an R value of 1, there's 100% predictability. If you know a person's monthly salary, you can predict perfectly that person's annual salary. If two people have different annual salaries, the difference can be completely explained by the difference in their monthly salaries. Although correlations have a number of different applications, here are 4 specific examples. First of all, prediction. If two variables are known to be related in some systematic way, it's possible to use one of the variables to make accurate predictions about the other. Secondly, validity. How can you show that a test is truly measuring what it claims? One common technique for demonstrating validity is to use a correlation. If X is supposed to be related to Y, then X and Y should be correlated. Thirdly, reliability. In addition to evaluating the validity of a measurement procedure, correlations are used to determine reliability. A test is considered reliable to the extent that it produces stable, consistent measurements. That is, a reliable measurement procedure produces the same scores, or nearly the same, when the same individuals are measured under the same conditions. One way to evaluate reliability is to use correlations to determine the relationship between two sets of measurements. When reliability is high, the correlation between two measurements should be strong and positive. And lastly, theory verification. The prediction of a theory could be tested by determining the correlation between two variables. By far the most common correlation is the Pearson correlation, which is sometimes called the Pearson product moment correlation, which measures the degree of straight line relationship. The Pearson correlation is identified by the letter R. Conceptually, this correlation is computed by the degree to which X and Y vary together divided by the degree to which X and Y vary separately, or in other words, the covariability of X and Y divided by the variability of X and Y separately. When there's a perfect linear relationship, every change in the X variable is accompanied by a corresponding change in the Y variable. The result is a perfect linear relationship, with x and y always varying together. In this data set of 5 pairs of observations, we can plot a scatter plot. If we draw an envelope around these data, we see that it's thinner than an American football, giving us a good working estimate that the correlation between x and y is strong. Actually calculating the Pearson correlation gives us an exact value of r equals 0.875. In this example, a researcher measures the relationship between computer use in hours per day and daily exercise in minutes per week. Is there actually a relationship between these two variables? And if so, how strong is it? If we calculate the Pearson correlation, we get an R value of 0.894, which indicates there's a strong positive correlation. As computer use increases, so does daily exercise. In this second example, a researcher measures the relationship between sleep medication, measured in times used per week, and time spent working, in hours per week. Is there a relationship between these two variables? And if so, how strong is it? If we calculate the Pearson correlation, we get an R value of negative 0.869, which tells us that there's a strong negative correlation. So as sleep medication increases, time spent working decreases. When you encounter correlations, there are 4 additional considerations that you should bear in mind. First of all, correlation simply describes a relationship between two variables. It does not explain why the two variables are related. Specifically, a correlation should not and cannot be interpreted as proof of a cause and effect relationship between the two variables. This is really important. Secondly, the value of a correlation can be affected greatly by the range of scores represented in the data. Thirdly, 1 or 2 extreme data points, often called outliers, can have a dramatic effect on the value of a correlation. And lastly, when judging how good a relationship is, it's tempting to focus on the numerical value of the correlation. For example, a correlation of plus 0.5 is halfway between 0 and 1, and therefore appears to represent a moderate degree of relationship. However, this correlation should not be interpreted as a proportion. Although a correlation of 1 does mean that there's a 100% perfectly predictable relationship between x and y, a correlation of 0.5 does not mean that you can make predictions with 50% accuracy. One of the most common errors in interpreting correlations is to assume that a correlation necessarily implies a cause and effect relationship between the two variables. We constantly are bombarded with reports of relationships. Cigarette smoking is related to heart disease. Alcohol consumption is related to birth defects. Carrot consumption is related to good eyesight. Does a correlation value mean that cigarettes cause heart disease or carrots cause good eyesight? The answer is no. Although there may be a causal relationship, the simple existence of a correlation doesn't prove it. To establish a cause and effect relationship, it would be necessary to use an experimental study design. Suppose that we select a variety of different cities and towns throughout the United States and measure the number of serious crimes and the number of churches for each. A scatter plot showing this hypothetical data is presented here. Notice that the scatter plot is showing a strong positive correlation between churches and crime. You should also know that these are realistic data. It's reasonable that the smaller towns would have less crime and fewer churches, and that the large cities would have large values for both variables. Does this relationship mean that churches cause crime? Does it mean that crime causes churches? It should be clear that the answer to both is no. Although a strong correlation exists between churches and crime, the real cause of the relationship is the size of the population. An outlier is an individual with X and or Y values that are substantially different, larger or smaller, from the values obtained for the other individuals in the dataset. The data point of a single outlier can have a dramatic influence on the value obtained for the correlation. This effect is illustrated in figure 16.7. Part A shows a set of n equals 5 data points for which the correlation between x and y values is nearly zero. The actual Pearson correlation value is negative 0.08, whereas in Part B, one extreme data point has been added to the original data set. When this outlier is included in the analysis, a strong positive correlation emerges of r equals positive 0.85. Note that the single outlier drastically alters the value for the correlation and thereby can affect one's interpretation of the relationship between variables x and y. Without the outlier, one would conclude there is no relationship between the two variables. With the extreme data point, the r value equals positive 0.85 and implies that as x increases, y will increase and do so consistently. The problem of outliers is a good reason why you should always look at a scatter plot instead of simply basing your interpretation on the numerical value of the correlation. If you only go by the numbers, you might overlook the fact that one extreme data point inflated the size of the correlation. Whenever a correlation is computed from scores that do not represent the full range of possible values, you should be cautious in interpreting the correlation. Suppose, for example, that you're interested in the relationship between SAT scores and GPA. If you select a sample of your fellow college students, your data probably will represent only a limited range of SAT scores. The correlation within this restricted range could be completely different from the correlation that would be obtained from a full range of SAT scores. So to be safe, you should not generalize any correlation beyond the range of data represented in the sample. For a correlation to provide an accurate description for the general population, there should be a wide range of x and y values in the data. Regression is a procedure that identifies and defines the straight line that provides the best fit for any specific set of data. The resulting straight line is called the regression line. Whenever there's a linear relationship, and therefore a Pearson correlation, between two values, it's possible to compute an equation that provides a precise mathematical description of the relationship. With this equation, it's possible to plug in the known value for one variable, for example, your SAT score, then calculate a predicted value for the second variable, your college GPA. The general statistical process of finding and using a prediction equation is known as regression. Let's look at these data. Notice the line. Is this the best line of fit? What about this one? Or this one? Or this one? The straight line produced by regression helps make it easier to see the relationship between two variables. The line itself represents central tendency. It's a simplified description of the relationship. The line can be used for prediction. If x is the predictor variable, then y equals the predicted criterion. The statistical technique for finding the best fitting straight line for a set of data, as I've said already, is called regression. In general, a linear relationship between two variables, x and y, can be represented by the equation y equals b times x plus a, where a and b are fixed constants. B represents the slope or gradient of the line, a equals the y-intercept, or the point at which the line crosses the y-axis. For example, let's say you're a talent scout looking for new boxers to train. You observe a group of 6 professional boxers and record their reach in inches and the percentage of wins over their careers. You can then create a regression equation to predict the success of a boxer given his physical reach, using the equation y equals b times x plus a. Using the data in this table, we can create a regression equation where y equals 3.62 times the reach minus 206. We can then use this prediction equation to predict the winning percentage for T-Rex arms Timmy, who has a reach of 62 inches. So if we plug in 62 into the regression equation, we get y equals 3.62 multiplied by 62 minus 206, which gives us a predicted y value of 18.44. So our equation would predict that 18.44% of Timmy's fights would be wins. What winning percentage could we predict for Ape Arm's Arnie, who has a reach of 84 inches? So if we plug 84 inches into the regression equation, we get a y value that equals 3.62 times 84 minus 206. So the y value equals 98.08. Therefore, we would predict that 98.08% of Arnie's fights would be wins. How about a medical example? Let's assume that age is related to bone density in milligrams per centimetre squared, with a Pearson correlation of negative 0.19. What bone density would we predict for Iris, who's 55 years old, and Suzanne, who's 48 years old? We could create a regression equation where y equals negative 1.52 times age plus 1000. For Iris, negative 1.52 times her age of 55 plus 1000 equals 916.4 milligrams per centimetre squared. Whereas for Suzanne, negative 1.52 times 48 plus 1000 equals 927.4 milligrams per centimetre squared. So far we've looked at regression in situations in which one variable is being used to predict a second variable. For example, IQ scores can be used to predict academic performance for a group of college students. However, a variable such as academic performance is usually related to a variety of other factors. For example, college GPA is probably related to motivation, self-esteem, SAT score, rank in high school graduating class, parents' highest level of education, and many other variables. In this case, it's possible to combine several predictor values to obtain a more accurate prediction. For example, IQ predicts some of academic performance, but you can probably get a better prediction if you use IQ and SAT scores together. The process of using several predictor variables to help obtain more accurate predictions is called multiple regression. Although it's possible to combine a large number of predictor values in a single multiple regression equation, we're going to limit our brief discussion here to the two predictor case. So for two predictor regression, the equation would be b1 times x1 plus b2 times x2 plus a. In short, the goal of the multiple regression equation is to produce the most accurate estimated values for y. For example, a researcher computes a multiple regression equation for predicting annual income for 40-year-old men based on their level of education and their social skills. x1 equals the number of years after high school, and x2 is a score from a self-reported questionnaire. In this example, the regression equation y equals 8.3 times x1 plus 2.1 times x2 plus 3.5. So if we select two individuals, person A has an x1 value of 0 and an x2 value of 16, whereas person B has an x1 value of 3 and an x2 value of 12. What's the predicted income for each person? If we plug these values into our multiple regression equation, person A has a final y value of 37.1, which represents $37,100 as their predicted annual income, whereas person B has a y value of 53.6, so their predicted annual income is $53,600. How good are these predictions? Or in other words, how close are the actual y values to the regression equation? The standard error of estimate gives a measure of the distance between a regression line and the actual data points. So it's possible to add on the end of the regression equation an error term, and that error term is what we call the standard error of estimate. In figure 16.9 we see two scatter plots. In the first one, the data points are further away from the regression line, which indicates more error, and in the second one, they're closer to the regression line, telling us that there's less error. If we created a standard error estimate for ape-arms Arnie, we'd get a plus and minus value of 3.59%, which we could add to the regression equation. So our prediction of 98.08% wins is accurate plus or minus 3.59%.
Hello, you've reached Arnold's Pizza Shop. I'm not here now. I'm out killing pepperoni. If you want to reach me, if you want a pizza, I don't care, because I'm not here.
The statistical tests we learned in previous modules are parametric tests. We use the t-test and ANOVA to compare sample means from different populations, and the Pearson correlation coefficient to measure the strength of the linear relationship between two variables. Underlying these test statistics were assumptions of a continuous scale, normality of distribution, homogeneity of variance, and linearity. Also, when using the test statistics, we were interested in obtaining an estimate of a population parameter, such as the mean mu and correlation rho. These statistical tests are referred to as parametric tests. When the assumptions for these tests are not satisfied, there are alternative tests referred to as nonparametric tests. Sometimes nonparametric tests are referred to as distribution-free tests because the distribution does not need to take a specific form. Nonparametric tests are often used when a variable is measured on a nominal or ordinal scale. An example is the nominal variable sex, where calculating a mean is nonsensical. If you wanted to know if groups differ on sex, you would not calculate the mean sex for each group. Another example is disease stage of kidney function, which is an ordinal variable. Again, comparing means between groups would not be appropriate. Whenever you have ratings, you are working with an inherently ordinal variable. Even when a variable is on an interval or ratio scale, it might not be normally distributed, and thus would violate an assumption necessary for parametric tests. Sometimes variables are skewed, such as household income. The mean would not be a good representation of the center of such a distribution. Comparing groups on income, it is possible a couple of households could make a test between groups statistically significant, even if the groups are mostly comparable. Another type of deviation from normality is kurtosis. For example, a leptokurtic distribution has heavy tails, and so the probability of observing a value more than 2 standard deviations away from the mean is greater than 0.05. Applying a parametric test to leptokurtic data can result in an inflated type 1 error rate. Conversely, a platykurtic distribution can result in a conservative test. Another possibility that can affect parametric tests are outliers. An outlier has an undue influence on the mean by moving the mean away from the center of the distribution and towards the outlier. For example, most APGAR scores to measure the health of a newborn are around the score of 9, but a stillborn would have a score of 0. Because of outliers, parametric tests regarding means are not best for making group comparisons. The same applies to correlation or regression, where an outlier can change the relationship between two variables. Some of the shortcomings of parametric tests mentioned in the previous 2 slides can be overcome with large samples. By the central limit theorem, a non-normal distribution can still have a normally distributed sampling distribution of the means. In addition, outliers have less influence when it is just one value among many. However, when the sample is small, we cannot rely on the central limit theorem. Moreover, sometimes when working with small samples, we do not know the population distribution and so cannot assume it is normal. Applying parametric tests in such situations can lead to wrong conclusions since the reported p-values are inaccurate. For example, the pictured frequency distribution is from 12 observations and does not look normal. The sample is too small to invoke the central limit theorem, and if nothing is known about the population from which the sample came from, then we don't know the behavior of the sampling distribution. The t-test in ANOVA requires data that is quantitative, and so is not appropriate for qualitative variables. For qualitative variable, we can calculate frequencies, but we cannot calculate parameters, such as the mean and the standard deviation. For example, we can count the number of hypertensive and normotensive patients, but we can't calculate an average hypertensive. When interest is in knowing if there is a relationship between two qualitative variables, the chi-square test is employed. A relationship would indicate the level of one of the qualitative variables occurs regularly with the level of the other qualitative variable. An example of a relationship between two qualitative variables is sex and baldness. Baldness is much more common in men compared to women. Recall to display a relationship between two quantitative variables, a scatter plot is used. While for two qualitative variables, a contingency table is used, which shows the number of people that possess the attribute for each of the levels of both variables. Let's go through an example. Suppose 300 people who exercise are asked what type of exercise they perform. We want to know, is there an association between sex and exercise preference? We learn of the 100 men asked, 40 perform weight training, 30 do yoga, and 30 aerobics. And of the 200 women queried, 20 use weights, 120 do yoga, and 60 aerobics. We can display these frequencies in a contingency table. In order to calculate the chi-square statistic, we need to find the marginal totals. The marginal totals give the frequencies for each level of one variable, summed over the levels of the second variable. For instance, the marginal total for weights is 40 plus 20 equals 60. And so we know just focusing on the variable exercise type, irrespective of sex, 60 people in the sample prefer weights. We do this for each level of exercise type. Similarly, the marginal totals for men is 40 plus 30 plus 30 equals 100. And we learn when just looking at sex, there are a total of 100 men in the sample. Lastly, the bottom right-hand corner gives the total sample size. It can be found by summing the row totals or summing the column totals. Using the marginal totals in total sample size, we can find the expected number of people in each cell if the row and column variables are independent. From the marginal row totals, we see that 100 out of 300, or 33% of the sample, is male. If there is no association between sex and exercise type, then we would expect about 33% of the people who use weights, 33% of people who do yoga, and 33% of the people who do aerobics to be male. Similarly, if the variables are independent, then we would expect 67% of the people who prefer each type of exercise to be women. There are 60 people who use weights. If the number of males who use weights is proportional to the number of men in the sample, then we would expect 33% of 60, or 20 of the people who use weights, to be male. Likewise, females represent 67% of the sample, and so the expected number of women who use weights, if the variables are independent, is 67% of 60, or 40 women. The previous procedure is done for every cell to find the expected frequencies assuming independence. Notice in calculating the expected cell frequencies, we take the row total and divide it by the sample size to obtain the proportion of men or women, and then we multiply this by the column total to arrive at the expected cell size. This simplifies to the row total times the column total divided by the sample size. For instance, to find the expected cell frequency for women who do yoga, we multiply the row total for women, which is 200, by the column total for yoga, which is 150, and divide by the sample size, which is 300. This gives us 100, and so we would expect if there's no relationship between sex and exercise type, 100 women would prefer yoga. If the variables are truly independent, then the expected cell frequencies should be close to the actual or observed cell frequencies. On the other hand, if the variables are not independent, but rather dependent, then there will be large differences between the observed and expected frequencies. The chi-square statistic involves calculating the difference between the observed and expected frequencies. For each cell, the difference between the observed and expected is first squared, and this squared difference is then divided by the expected cell size. The reason for this latter adjustment is so large cell sizes do not have undue influence on the statistic. Finally, these adjusted square differences are summed across all cells to arrive at the chi-square value. If there is a relationship between the two variables, then the square differences will be large, and this in turn will result in a large chi-square value. Thus, the larger the chi-square value, the stronger the evidence for an association. In our example, chi-square equals 42. The calculated chi-square is affected by the number of cells in the table. With more cells, it's easier to attain a large chi-square. So we need to take into consideration the number of cells, or degrees of freedom, since this will affect the probability of observing a specific chi-square value. The degrees of freedom is the number of cell frequencies that are free to vary given the marginal totals. In the example, we know there are 100 men, 200 women, 60 people who use weights, 150 who do yoga, and 90 who do aerobics. These are the marginal totals. Now suppose we assign the frequency of 50 for the cell men who use weights. Then the number of women who use weights is not free to vary because we know 60 people use weights. The number of women who weight train must be 60 minus 50, or 10 women. Next, suppose we assign the frequency 100 to women who do yoga. Then the frequency of men who do yoga is not free to vary. It must equal 150 minus 100, or 50 men. Now that we have the frequencies for men who use weights and do yoga, the number of men who do aerobics is not free to vary. Given that there are 100 men total, the number doing aerobics is 100 minus 50 minus 50, or 0 men. Similarly, the frequency of women who do aerobics is not free to vary and must equal 90. Thus, the degrees of freedom in this example equals 2. A general formula for the degrees of freedom for the chi-square test is the number of rows minus 1 multiplied by the number of columns minus 1. Here it is 2 minus 1 multiplied by 3 minus 1, which gives us the 2 degrees of freedom. Now that we know the chi-square value and degrees of freedom, we can test the hypothesis of no association. One way to do this is to compare the calculated chi-square to the critical value chi-square. The critical value can be obtained from a chi-square table. Using an alpha level of 0.05, we could see from the table that the critical value for 2 degrees of freedom is 5.99. The calculated chi-square of 42 is greater than 5.99, so we reject the null hypothesis of no association and conclude sex and exercise type are related. Also, the p-value is less than 0.001, meaning the probability of observing a chi-square of 42 or more, if there was no relationship, is less than 0.001. The chi-square test statistic actually just approximates a chi-square distribution and works well for large samples. However, when the sample size is small, the p-value reported is not accurate. This could possibly lead to a wrong conclusion when using chi-square in situations when it is not appropriate. Assumptions for the chi-square test include no cells should have expected cell counts near 0, and the percent of cells with expected counts less than 5 should not exceed 20%. For example, if a contingency table contains 8 cells and 2 cells, or 25%, had expected cells less than 5, then the chi-square cannot be trusted. In such situations, in place of chi-square, one should use an exact test. An exact test computes the probability directly of observing a particular set of frequencies in a contingency table without relying on approximation to the chi-square distribution. The Fisher exact test is most often used for a 2x2 table where there are 4 cells, but it can be extended to tables with more cells. But because it's easiest to understand with a 2x2, we'll work with such a table. Let's label the cells in the table from A to D. This will help with understanding the calculation. The statistician, R.A. Fisher, devised the test and showed the probability of a specific configuration of cell frequencies can be calculated from the hypergeometric distribution, which simplifies to the formula shown on the slide. As seen, the formula takes the factorials of the marginal totals, sample size, and cell frequencies. Let's do an example. Suppose a study of 10 patients, each receiving 1 of 2 treatments, are followed for 2 years, and the survival is recorded for each patient. Out of the 6 patients who received treatment A, 5 were still alive at the end of the study, while 1 died. Of the 4 patients who received treatment B, 3 died and 1 was alive. The sample is very small, and the expected frequencies are below 5 for all 4 cells, so the chi-square test is not appropriate. Using Fisher's exact test, we see the probability of this particular cell frequency configuration, given the marginal totals, equals 0.114. However, we need to find the probabilities for more extreme tables and sum all the probabilities to arrive at the p-value. Recall, a p-value tells you the probability of observing the sample data, or data more extreme. For example, the p-value less than 0.001 from the earlier chi-square of 42 was the probability of observing a chi-square value of 42 or greater. Here, a more extreme table would be if all 6 people from treatment A survive. The probability of this particular configuration equals 0.005. And so the p-value for the test of dissociation between treatment and living status is 0.114 plus 0.005 equals 0.119. Since the p-value is greater than the alpha level of 0.05, we would not reject the null hypothesis. We cannot conclude there is a difference between treatment A and treatment B. Notice in this calculation, there is no reference to a distribution, such as z, t, or chi-square, in arriving at the p-value. The Mann-Whitney-U test is used to test the null hypothesis that there is no difference between 2 population distributions. Some researchers interpret this as comparing the medians between 2 populations. It corresponds to the t-test for independent samples without the assumption of normality or equality of variances. It is employed when the outcome variable is measured on an ordinal scale, or the distribution of a continuous variable does not meet the assumptions for a t-test. The test is also referred to as the Wilcoxon rank sum test, and it can be shown that the formula for the Mann-Whitney-U and Wilcoxon sum are equivalent and result in the same exact p-value. As an example, suppose heart rate is measured in a sample of 12 patients, and the interest is in knowing if there is a difference between males and females. Since the sample size is only 12, we cannot rely on the central limit theorem to assume normality in the sampling distribution of means, and thus a nonparametric method is used. Notice there are 7 males and 5 females, and so, like the t-test, equal group size is not required to use the Mann-Whitney U-test. The Mann-Whitney U-test is calculated by converting scores to ranks and comparing the ranks between groups. Thus, the first step is to combine the groups and order the entire sample of scores in ascending order from lowest to highest. This is followed by placing the rank adjacent to each score. Notice by replacing scores by ranks, if there are any outliers, their influence would be reduced. For instance, if the heart rate reading of 93 was changed to 103, it would still have the same rank of 12. Next, assign the group membership to each rank. It is the ranks that are used to calculate the test statistic. Once the ranks for each group are known, the Mann-Whitney U-test is calculated by summing the ranks for one group and testing if it differs from what would be expected if the groups were the same. If there is no difference between the groups, we would expect the mean ranks between groups to be about the same. The Mann-Whitney test approximates a standard normal distribution, and so the z-test is used to obtain a p-value. In this example, the mean rank for males is 8.71 and the mean rank for females is 3.4. If there truly is no difference in heart rate between males and female patients, then the probability we could sample 12 patients and get the observed mean ranks is only 0.012 according to the test statistic. Since this p-value is below the alpha level of 0.05, we reject the null hypothesis of similar distributions and conclude males have higher heart rate than females. The Mann-Whitney U-test is a nonparametric analog to the independent samples t-test. There are other nonparametric tests that correspond with parametric tests used for comparing means. When the assumptions for analysis of variance for comparing 3 or more groups do not hold, one can use the nonparametric Kruskal-Wallis test instead. In place of the pair t-test for dependent samples, the nonparametric Wilcoxon-Sign rank test can be used. And similarly, when the assumptions for the repeated measures ANOVA are not valid, the nonparametric Freeman test can be used in its place. For all these nonparametric tests, the procedure is similar to how the Mann-Whitney U was calculated. The original scores are converted to ranks, and the ranks are compared between groups. The test statistic approximates a distribution, such as the z or chi-square distribution, and the p-value is obtained from the distribution. Recall the Pearson correlation coefficient measures the strength of the linear relationship between two continuous variables. Sometimes a researcher encounters situations when the two variables are not on a continuous scale, or the distribution of at least one of the variables is not normal or contains outliers. In such circumstances, the Pearson correlation may not give a good estimate of the relationship between the two variables. A better measure is the Spearman-Rank correlation. The Spearman-Rank correlation converts the scores from each of the two variables into ranks and then applies the Pearson correlation to the transformed ranks. It is a measure of the linear relationship between the rank scores, or you can think of it as a measure of consistency between the two variables. Like the Pearson correlation, the Spearman rank ranges from -1 to +1, where values close to -1 or +1 indicate a strong relationship, and values near 0, no relationship. Let's look at a simple example. Suppose in 8 male patients, body mass index and testosterone level measured in picograms per milliliter was measured. The parametric Pearson correlation between the two variables equals -0.8, and the linear relationship is deemed statistically significant since p is less than 0.05. However, a scatter plot of the two variables shows there is an outlier in the upper left corner in the figure. This outlier, which is patient 1, is distorting the relationship between the variables and causing the Pearson correlation to be inflated. If we ignore that patient, notice the relationship between BMI and testosterone for the remaining 7 patients does not appear as strong. This is a good situation to use the Spearman-Rank correlation. To calculate the Spearman correlation, first the scores for each variable are converted to ranks. Similar to the Mann-Whitney U-test, by converting to ranks, scores that were originally outliers are no longer far removed from the other scores. Notice the testosterone score for the first patient. The value of 11.97 is much higher than the second highest value of 7.31 observed for patient 5. When converted to ranks, the first patient has a rank testosterone score of 8, while the fifth patient has a rank score of 7, and the ranks are closer together. After converting the variables to ranks, the next step is to perform the usual Pearson correlation on the rank scores. In the example, the Spearman R equals negative 0.64, which is smaller than the Pearson R of negative 0.8 applied to the original variables. Also, the relationship is no longer statistically significant since p is above 0.05. When we look at the scatter plot of the transformed ranks, we no longer see the outlier, and the relationship does appear weaker than the scatter plot that was used for the original values. The SPSS output on the left shows the Spearman-Rank correlation of negative 0.643 and the p-value of 0.086. Notice the variable names BMI and testosterone. To demonstrate the Spearman correlation is just the Pearson correlation applied to rank data, the output on the right shows the Pearson correlation for the transformed ranked variables. Notice the variable names now include rank. It gives the same correlation in p-values as the Spearman-Rank correlation. The previous non-parametric tests that compared groups invoked the chi-square or z-distribution for hypothesis testing. The distribution of ranks asymptotically approaches those parametric distributions, and it was assumed the approximation was close enough for the test to be valid. For exact tests, the sampling distribution is known exactly, and there is no need to rely on asymptotic properties. When the samples are very small, and the approximation of the previous non-parametric test cannot be trusted, the exact test is recommended. Fisher's exact test shown earlier is one example of an exact test. As an example, suppose we want to compare males and female students on test scores, and the sample size is only 5 people. Without knowing the form of the population distribution, the sample is much too small to use the parametric t-test. And with only 5 observations, it is still too small to use the non-parametric Mann-Whitney U-test because the distribution of ranks cannot be assumed to be normal. Thus, we are left with an exact test. Looking at the scores, we see the first student had the highest score and is female. The second student had the lowest score and is male, and so forth. The idea behind the exact test is to enumerate every possible sample that can be generated given the number of people from each group in the observed scores. We then find what proportion of these generated samples is equal to or more extreme than the actual one observed. So to carry out the exact test, the scores are ordered in descending order without regard to group membership. Then the possible samples are enumerated. One possible sample is that the 2 highest scores are from females, and the 3 lowest scores come from males. Another possible sample is that the highest score is from a female, and the second highest score is from a male. Then the third highest score is a female, followed by the 2 lowest scores coming from males. We have now generated 2 possible samples given the observed data and group sizes. This continues until we have generated every possible sample. It can be shown that for a sample of 5 people, with 2 people in one group and 3 in the other group, there's a total possibility of 10 different samples. All the possible different combinations are listed in the table and vary from the first sample, where the 2 females have the highest score, to the 10th sample, where the 2 females have the lowest scores. We next find where the actual observed sample falls in this distribution of all possible samples. In the observed sample, the 2 highest scores did come from females. The proportion of samples that are equal to or more extreme than the observed sample is 1 out of 10, and thus the p-value equals 0.10. However, this was not a directional alternative hypothesis, and so the p-value needs to be multiplied by 2 to give the correct p-value for a two-tailed test. Of note, the number of possible samples in the sampling distribution quickly increases as the sample size gets larger. For instance, if there were 2 groups of 10 people each, for a total sample size of 20, the number of possible samples is 184,756. Fortunately, we can rely on parametric or non-parametric tests when the sample increases in size.